Summary of Langchain Community Vector Stores. TypeSense. A TypeSense vector store that utilizes Langchain for seamless integration with your application. Langchain provides a powerful framework for building language-based applications. TypeSense is a fast and scalable vector search engine. Combining these two tools allows you to efficiently store and search large amounts of textual data. For instance, you can build a chatbot that can retrieve relevant information from a vast corpus of documents. Or you can create a semantic search engine that returns results based on the meaning of the user's query, rather than just keyword matching. Inputs: textual data that you want to store and search. For instance, a collection of articles, product descriptions, or customer reviews. Embeddings are numerical representations of text that capture the semantic meaning of words and sentences. They are used to measure the similarity between different pieces of text. Outputs: a list of similar documents, ranked by their relevance to the search query. The textual data that matches the search query. Steps: initialize the TypeSense vector store, which sets up the connection to the TypeSense instance and creates the necessary indices. Add textual data to the vector store. This involves converting the text into embeddings and storing them in the TypeSense index. Perform similarity searches using the embeddings that you generated from the text. Prerequisites: TypeSense instance, a hosted or self-hosted TypeSense server that runs the TypeSense search engine. TypeSense package, a Python library for interacting with the TypeSense API. Embeddings model, a model that converts text into numerical embeddings. OpenAI's Text Embedding ADA 002 is a popular choice. OpenAI's Text Embedding ADA 002, a pre-trained model that can be used to generate embeddings for text. Fine-tune parameters. Similarity top k, the number of similar documents to return for each search query. Similarity search method, the algorithm used for searching the TypeSense index. Options include cosine similarity and dot product. Challenges and fixes. Index size limitations. If you have a large dataset, the size of the TypeSense index might be a concern. Use TypeSense index size parameter for indexing. You can use the TypeSense index size parameter to control the maximum size of the index. Slow search times. Search performance can be affected by the size of the index and the complexity of the search queries. Optimize index settings. Optimizing the index settings, such as using appropriate data structures and indexing strategies, can improve search times. Data inconsistency. Inconsistencies in the data can lead to incorrect search results. Ensure data integrity and version control. Use data validation and version control to maintain data consistency. Missing documentation. There may not be extensive documentation available for specific use cases or configurations. Refer to the TypeSense and Langchain documentation. Refer to the official TypeSense and Langchain documentation for detailed information and guides. Langchain Voyage AI Embedding Summary. This YAML document describes the functionalities, inputs, outputs, prerequisites, fine-tune parameters, and common challenges with fixes for Voyage AI embeddings is integrated with Langchain. A detailed description of embeddings for Voyage AI's proprietary language model. These embeddings are numerical representations of text data that capture semantic meaning and relationships between words and phrases. They are crucial for various natural language processing tasks like similarity search, clustering, and question answering. Voyage AI embeddings are designed to be highly accurate and efficient. Leveraging the power of Voyage AI's advanced language model. Inputs. Text. The input text that needs to be converted into a numerical embedding vector. This text can be a sentence, paragraph, or any other meaningful text string. For example, you could provide the text "The quick brown fox jumps over the lazy dog." Outputs. Numerical embedding vector, a vector of numbers representing the semantic meaning of the input text. Each element in the vector corresponds to a specific dimension of the embedding space. These vectors can be used for various tasks such as calculating the similarity between different texts or classifying text based on its content. For instance, the embedding vector for the text "The quick brown fox jumps over the lazy dog" could be represented as 0.23, 0.56, 0.12, where each number corresponds to a specific semantic feature. Steps. Text input is processed. The input text is first pre-processed to prepare it for the embedding process. This typically involves cleaning the text by removing punctuation, converting to lowercase, and handling special characters. Text is converted to numerical embedding vector. The preprocessed text is then converted into a numerical embedding vector by the Voyage AI language model. This involves mapping the text to a high-dimensional space where each dimension represents a specific semantic feature. Prerequisites. Voyage AI Application Programming Interface Key, a unique key that provides access to the Voyage AI API and its functionalities, including embedding generation. This key acts as a credential for authenticating and authorizing requests to the API. Voyage AI account. A registered account with Voyage AI is required to access and utilize their API and its services, including embedding generation. This account provides access control and management for various functionalities within the Voyage AI platform. Fine-tune parameters. Embedding model size. The size of the Voyage AI language model used for generating embeddings. Larger models typically require more computational resources but offer greater accuracy and semantic understanding. For example, you could choose between a small model, medium model, or large model depending on your specific requirements. Embedding dimension. The number of dimensions in the output embedding vector. The dimension size affects the complexity of the embedding space and the ability to capture fine-grained semantic distinctions. Higher dimensions generally allow for greater expressiveness but also require more computational resources. You might select a dimension of 128, 256, or 512 depending on your application and the level of detail required. Challenges and fixes. Error connecting to application programming interface. This error typically occurs when there is an issue with the provided API key, account details, or network connectivity. Verify application programming interface key and account details. Double-check the accuracy of API key and ensure that your Voyage AI account is active. Also, verify that there are no connectivity issues by testing your internet connection. Embedding dimension not supported. The requested embedding dimension might not be supported by the chosen Voyage AI language model. Choose a supported dimension. Review the available embedding dimensions supported by the selected Voyage AI language model and select a compatible dimension. Description of the World Vector Store and its attributes. This section outlines the configuration parameters used in querying a vector store. It details the inputs required, the outputs generated, the methodology employed, prerequisites, parameters for fine-tuning, metrics used for evaluation, visualization options, potential error scenarios, and common challenges along with their respective solutions. The text that the user wants to search for. This can be a sentence, a phrase, or even a single word. For example, what is the capital of France? An application programming interface API key that allows access to the vector store. This key is typically obtained from the Vectra platform and is used to authenticate requests. The search results returned by the Vectra vector store. These results typically include a list of documents that are most relevant to the given query text. The relevance is determined by a similarity function based on the underlying vector representations of the query and the documents. The process of querying the Vectra vector store involves sending the query text to the Vectra application programming interface API along with the required API key. This API then searches the indexed data to identify documents that are semantically similar to the query. These documents are ranked based on their similarity scores and returned to the user. The Vectra API retrieves documents that are most relevant to the given query text. This retrieval process leverages the vector representations of both the query and the documents, comparing their similarity to determine the best matches. A Vectra account is essential to access the Vectra vector store and its functionality. This account provides access to the API and the necessary resources for querying and retrieving data. The data to be searched must be preprocessed and indexed into the Vectra vector store. This indexing process transforms the data into a format that can be efficiently searched by the Vectra API, leveraging vector representations for similarity comparisons. The top K parameter specifies the desired number of search results to be returned. A higher value means more results, while a lower value returns fewer but potentially more relevant results. For instance, setting top K to 10 would return the top 10 most relevant documents. The similarity metric parameter determines the function used to calculate the similarity between the query text and the indexed documents. Different similarity functions are available, each with its own strengths and weaknesses. For example, cosine similarity and dot product are commonly used similarity metrics. Precision measures the proportion of retrieved documents that are actually relevant to the query. A high precision value indicates that the search results are mostly relevant. For example, if a search returns 10 documents and 8 of them are relevant, the precision is 810 or 80. Recall measures the proportion of relevant documents that are retrieved by the search. A high recall value indicates that the search captured most of the relevant documents in the index. For example, if there are 10 relevant documents and the search returns 8 of them, the recall is 810 or 80. Visualizing the distribution of search results can be helpful in understanding the overall relevance of the retrieved documents. This plot typically displays the similarity scores of the returned documents, providing insights into the quality of the search results. An invalid API key can lead to authentication errors, preventing access to the Vectra vector store. This typically occurs when the API key provided is incorrect or expired. If the query text does not match any documents in the indexed data, no relevant results will be returned. This can happen if the query is too specific or if the data does not contain information relevant to the query. Slow query response times can occur due to factors such as complex query text, large datasets, or inefficient similarity metrics. Optimizing the query text by simplifying the language, reducing ambiguity, and using more specific keywords can improve query response times. Using faster similarity metrics can also speed up the search process. Certain metrics are computationally more efficient than others, leading to quicker responses. Irrelevant search results can occur when the indexed data does not accurately reflect the semantic meaning of the query text or when the query parameters are not tuned properly. Improving the data indexing process by ensuring that the data is correctly preprocessed and mapped to relevant vector representations can enhance the accuracy of the search results. Refining the query parameters, such as adjusting the top K value or selecting a more appropriate similarity metric, can also improve the relevance of the search results. Langchain Community Vector Stores Vespa Store. Description of the vector store. This vector store is powered by Vespa, a robust search engine and application platform known for its scalability and performance. It enables efficient storage and retrieval of vector representations for text data, making it ideal for various search and recommendation tasks. Inputs. Text data to be indexed. The vector store requires text data as input to create its vector representations. This data can range from documents, articles, product descriptions, or any other textual content you wish to index and search. For example, if you are building a product recommendation system, you'd feed in product descriptions or customer reviews. Outputs. Vectors for text data. The output of the vector store is a set of vector representations for the input text data. Each vector represents a specific text entry, capturing its semantic meaning. These vectors can then be used for various downstream tasks, such as similarity search, clustering, and classification. Imagine you want to find products similar to a specific item. The vector representation of that item can be used to find other products with similar vectors, leading to effective recommendations. Working methodology. Upload text data to Vespa. The first step is to upload your text data to Vespa. This can be done through Vespa's application programming interface API or by using its provided tools. This data is then stored within Vespa's distributed architecture, ensuring high availability and scalability. Create a Vespa document type. For text data, you need to define a Vespa document type that corresponds to your text data structure. This involves specifying the fields that represent different aspects of your text data, such as title, content, author, etc. This step allows Vespa to understand and organize your text data efficiently. Define Vespa fields for vector embedding. To enable vector search, you need to specify specific Vespa fields for storing the generated vector embeddings. These fields are usually of type tensor, which allows Vespa to handle high-dimensional vectors efficiently. The specific tensor type depends on the embedding model and the dimensionality of the vectors you are using. Create a Vespa query to retrieve similar documents after the data is indexed with vector embeddings. You can create Vespa queries to retrieve similar documents based on the vector representations. These queries utilize similarity functions, like cosine similarity, to find documents with vectors closest to the query vector. This enables you to perform semantic search, finding documents with similar meaning to the query, rather than just exact keyword matches. Prerequisites. Vespa cluster setup. A Vespa cluster needs to be set up and running to use the vector store. This involves deploying Vespa nodes and configuring the cluster for optimal performance and scalability. You'd typically need a distributed setup to handle large amounts of data and search requests. Vespa application deployment. An application needs to be deployed on the Vespa cluster to handle the indexing and search tasks. This application defines the data schema, vector embedding logic, and search configuration for your specific use case. Fine-tune parameters. Vector embedding model. The choice of vector embedding model significantly impacts the quality of your vector representations and, subsequently, the accuracy of your search results. You can use various pre-trained models or fine-tune them on your specific data to optimize performance. For instance, you can choose between models like sentence transformers or OpenAI's embedding models. depending on your data and task requirements. VESPA search parameters. VESPA provides a rich set of parameters to fine-tune the search process, controlling aspects like similarity function, ranking criteria, and relevance scoring. By adjusting these parameters, you can optimize the search results for your specific use case. For example, you can adjust the weighting of different fields or use a specific ranking algorithm based on your understanding of the data and the desired search behavior. Metrics. Retrieval accuracy. This metric measures the effectiveness of the vector store in retrieving relevant documents based on a given query. It's typically evaluated using metrics like precision, recall, and F1 score, comparing the retrieved documents to a ground truth set of relevant documents. For example, you might evaluate how well the vector store retrieves documents relevant to a particular topic based on a set of predefined queries. Latency. This metric assesses the time it takes for the vector store to retrieve search results for a given query. It's crucial for ensuring a good user experience, especially when dealing with large datasets and high-volume queries. You might measure the average latency for specific queries or analyze the latency distribution over different query types. Visualization plots. Retrieval performance over time. This visualization shows how the retrieval accuracy of a vector store changes over time. It can help identify trends, potential issues, and the impact of updates or changes to the data or configuration. For example, you might observe a decline in accuracy after adding new data and need to adjust the vector embedding or search parameters to improve performance. Vector space visualization. This visualization helps you understand the relationships between different vectors in the vector space. It can be useful for exploring data clusters, identifying outliers, and understanding the semantic relationships between different documents. Techniques like TSNE or UMAP can be employed to project high-dimensional vectors into lower-dimensional spaces for visualization. Error analysis. Error in vector embedding. Errors in vector embedding can arise from various factors, including the quality of the embedding model, the training data used, or the specific embedding parameters. This can lead to inaccurate vector representations and affect the search results. You might need to investigate the causes of these errors and potentially retrain the embedding model with a better dataset or adjust the embedding parameters to improve accuracy. Error in search ranking. Errors in search ranking can occur if the VESPA search parameters are not appropriately configured or if the ranking algorithm is not suitable for the specific dataset and query types. This can lead to irrelevant documents being ranked higher than relevant ones, impacting the search results and user experience. You might need to analyze the search parameters, the ranking algorithm, and the data to identify the root cause of the errors and make necessary adjustments. Challenges and fixes. High latency during retrieval. High latency during retrieval can be caused by various factors, including inefficient search queries, overloaded VESPA nodes, or network issues. You can optimize VESPA search parameters to improve query performance, distribute the load across multiple VESPA nodes, and ensure proper network configuration to mitigate latency. Low retrieval accuracy. Low retrieval accuracy can be caused by several factors, including an inadequate vector embedding model, poorly tuned VESPA search parameters, or data quality issues. You can fine-tune the vector embedding model to improve the accuracy of vector representations. Adjust VESPA search parameters to match the specific data characteristics and query types, and ensure data quality to improve retrieval performance. Langchain Community Vector Stores. VESPA VESP Store Description of the inputs. A running Vespa cluster is required for storing and querying data. This can be a self-hosted cluster or a cloud-based service. For example, a self-hosted Vespa cluster can be deployed on a local machine or a virtual machine in a private cloud environment. Text data refers to the data that will be used for vector search. It could be news articles, product descriptions, scientific papers, or any other form of text. For example, a collection of product descriptions from an e-commerce website could be used as input to build a vector search system for product recommendations. Description of the outputs. Vector embeddings are numerical representations of the text data that capture its semantic meaning. They are generated using an embedding model that maps each text document to a vector of numbers. For example, a sentence like "the quick brown fox jumps over the lazy dog" might be represented by a vector with 512 dimensions, where each dimension corresponds to a specific feature of the sentence. Description of the working methodology. The text data is stored in the Vespa cluster using the Vespa Application Programming Interface (API). Vespa provides a way to create and manage documents within the cluster, including text data. For example, a set of product descriptions could be stored as documents in the Vespa cluster. Vespa has built-in functionality for generating vector embeddings. This means that you don't need to use a separate library or service to create these embeddings. Vespa uses a pre-trained embedding model to convert the text data into vectors. For example, the sentence transformers embedding model could be used to generate embeddings for the product descriptions. The generated vector embeddings are stored along with the original text data in the Vespa cluster. This allows for efficient vector search queries, as the embeddings are readily available within the cluster. For example, the product descriptions and their corresponding embeddings could be stored in the same Vespa document. Description of the prerequisites. A running Vespa cluster is necessary to use the Vesp store. This means that you need to have a Vespa cluster set up and running before you can start storing and querying data. The Vespa SDK for Python is required to interact with the Vespa cluster and perform operations such as storing data, generating embeddings, and running search queries. The SDK provides a convenient way to access the Vespa API and integrate with other Python libraries. Description of the fine-tune parameters. The embedding model is a crucial component that determines the quality of the vector embeddings. Different embedding models are available, each with its strengths and weaknesses. For example, the sentence transformers model is known for its performance on sentence embeddings, while the universal sentence encoder model is optimized for speed. The vector similarity metric defines how the similarity between two vectors is measured. Different metrics are available, including cosine similarity, Euclidean distance, and Manhattan distance. The choice of metric depends on the specific application and the properties of the embedding model. For example, cosine similarity is often used for measuring the similarity of text documents. Description of the metrics. Search accuracy refers to how well the vector search system can retrieve relevant results for a given query. It is measured by evaluating the system's ability to rank relevant documents higher than irrelevant ones. For example, a product recommendation system should be able to retrieve relevant products for a given search query. Latency refers to the time it takes for the system to process a search query and return the results. A low latency is crucial for real-time applications, such as online search or product recommendations. For example, a search engine should be able to return results within a few milliseconds. Description of the visualization plots. Search result visualization allows for visualizing the results of a vector search query, making it easier to understand the system's performance and identify potential issues. For example, a visualization could show the top 10 results for a given query, along with their relevance scores. Description of the error analysis. Incorrect embeddings can occur when the embedding model is not appropriate for the data or when the model has been trained on a dataset that is different from the data being used for search. For example, if an embedding model trained on news articles is used to generate embeddings for product descriptions, the results might not be accurate. Search result ranking issues can arise from various factors, including poor data quality, an inappropriate embedding model, or an incorrect similarity metric. For example, if the relevance scores assigned to the documents are not accurate, the search results might not be relevant. Description of the challenges and fixes. Large dataset size can pose a challenge for vector search, as it can lead to long processing times and high memory usage. To address this, the Vespa configuration can be optimized to handle large datasets more efficiently. For example, the number of nodes in the cluster can be increased or the data can be partitioned across multiple nodes. Complex search queries can be difficult to handle with traditional keyword-based search systems to address this. Vespa provides advanced query features, such as phrase matching, proximity search, and semantic search. These features allow for more nuanced and powerful search capabilities. For example, a user could use a complex search query to find documents that contain specific keywords and are related to a particular topic. Langchain Community Vector Stores VikingDB config. A configuration class that defines the parameters for setting up and using the VikingDB vector store. This configuration class helps in configuring and managing the vector store's functionalities. Inputs. Textual data that needs to be transformed into numerical representations vectors for storage and retrieval. This data could include documents, articles, code snippets, or any other text-based information. A pre-trained model that maps text to vectors. This model captures the semantic meaning of the text and converts it into numerical representations. Examples include sentence transformers, OpenAI's text embedding ADA 002, and others. Outputs. The numerical representations of the input text. These vectors capture the semantic meaning of the text and allow for efficient similarity searches. Additional information associated with each vector, such as the source document, creation date, or other relevant metadata. This metadata helps in understanding the context and origin of each vector. Working methodology. The text data is processed using the specified embedding model to generate its numerical representation. This process transforms text into a numerical form that can be understood by the vector store. The generated vectors, along with their associated metadata, are stored in the VikingDB database. VikingDB is a database optimized for storing and querying vector data, providing efficient retrieval and search functionalities. Prerequisites. The VikingDB client library must be installed and configured on the system. This library provides the necessary tools to interact with the VikingDB database and perform operations such as storing and retrieving vectors. A connection to the VikingDB database must be established. This involves configuring the database's host, port, username, password, and other relevant parameters to connect and interact with the database. Fine-tune parameters. The dimension of the vector embeddings represents the number of features or components in each vector. This dimension depends on the chosen embedding model and influences the complexity and accuracy of the vector representations. The number of shards determines the distribution of the data across different partitions within a database. This partitioning strategy aims to optimize storage and retrieval performance by distributing a data across multiple nodes or servers. Metrics. Storage efficiency refers to the effectiveness in storing and managing the vectors in the database. It assesses how efficiently the database utilizes storage resources to accommodate the vectors and metadata. Query latency measures the time it takes to retrieve relevant vectors based on a given query. This metric reflects the speed and efficiency of the vector search process, indicating how quickly results are returned to the user. Visualization plots. Visualizations of the vector distribution in embedding space can help understand the relationships and similarities between different vectors. These plots provide a visual representation of the semantic relationships captured by a embeddings. Plots of query performance statistics, such as latency distribution, can help identify potential bottlenecks or areas for optimization in the search process. These visualizations provide insights into the efficiency and performance of the vector search. Functionalities. Error analysis. Data inconsistency issues arise when there are discrepancies or conflicts in the stored vectors or metadata. These issues can occur due to errors during data processing or inconsistencies in the embedding model. Query performance degradation refers to a decline in the efficiency and speed of vector searches. This degradation can be caused by factors such as database performance issues, inefficient indexing strategies, or ineffective query optimization techniques. Challenges and fixes. Challenge 1. Database connection issues can occur due to incorrect connection parameters, network connectivity problems, or database server unavailability. Verify that the connection parameters, such as hostname, port, username, and password, are correct and match the database configuration. Check if the database server is running and accessible. Network connectivity issues or server downtime can prevent successful database connections. Challenge 2. Data indexing performance can be affected by factors such as the size of the data, the complexity of the embedding model, or inefficient indexing strategies. Optimize indexing parameters, such as the number of shards or the indexing strategy, to improve the efficiency of data indexing and retrieval. Consider using specialized indexing techniques, such as approximate nearest neighbor search and algorithms, to accelerate the search process and retrieve relevant vectors more efficiently. Langchain Community, Vector Stores, VikingDB, VikingDB config. Configuration of VikingDB config. Inputs. A string that contains the information required to connect to a VikingDB database. This string typically includes the database host, port, database name, username, and password. An example of a connection string for a VikingDB database could be VikingDB a password host port database. A list of functions that map text to numerical vectors, which represent the meaning of the text. These functions are used to embed the data in the database. Some common embedding functions include OpenAI's text embedding ADA002. This function is provided by OpenAI and uses a pre-trained model to embed text. Sentence transformers. This library provides a variety of pre-trained models for embedding sentences. Hugging Face hosts a variety of pre-trained models for embedding text, including the popular BERT model. Outputs. A data structure that allows efficient searching and retrieval of data based on semantic similarity. Vector stores are used in various applications, such as recommendation systems recommending products or content to users based on their past interactions. Question answering retrieving relevant documents to answer questions based on their semantic similarity. Document search searching for relevant documents based on their content and meaning. Working methodology. This configuration utilizes the provided VikingDB connection string to establish a connection to the VikingDB database. This connection enables communication with the database and allows for data storage and retrieval operations. This configuration uses the provided embedding functions to convert the data into numerical vectors, which represent the meaning of the data. These vectors are then stored in the VikingDB database along with the corresponding data. Prerequisites. A VikingDB database is a prerequisite for this configuration, as it provides the storage and retrieval mechanism for the embedded data. You can use various VikingDB services, such as the VikingDB Cloud Service, or self-host a VikingDB instance. A list of embedding functions is also a prerequisite, as these functions are essential for converting the data into numerical vectors that can be stored and searched in the database. Fine-tune parameters. The embedding function is a crucial parameter that determines how the data is represented as numerical vectors. Selecting the right embedding function is essential for achieving accurate and efficient search results. This choice depends on the specific data and application. Metrics. Latency for queries refers to the time taken to retrieve relevant data from the vector store in response to a user query. This metric is crucial for evaluating the performance of the vector store. Low latency indicates a fast and responsive system. Visualization plots. Visualizing the database structure can provide insights into the organization and relationships within the data. This visualization helps in understanding the data flow and identifying potential bottlenecks. Error analysis. An error related to the database connection indicates that the system is unable to connect to the VikingDB database. This error might occur due to an incorrect connection string, network issues, or access restrictions. Challenges and fixes. The database connection is not established. Check the connection string for accuracy, including the database host, port, database name, username, and password. Ensure that the database server is running and accessible. The embedding function is not valid. Verify that the specified embedding function is available and supported by the system. Check if the function is correctly imported and configured. The database is not accessible. Ensure that the system has the necessary permissions to access the VikingDB database. Verify that the user account associated with the connection string has the required privileges. Check if any firewalls or security settings are blocking access. Langchain Community Vector Stores. Zatha Vector Store. A vector store built on top of Zatha, a database ASA service. Zatha is a serverless database that provides a simple and scalable way to store and manage data. Inputs. Text data to be embedded. This can be any text data, such as documents, articles, or code. For example, you could embed the text of a news article or a blog post. Embedding function to embed text data. An embedding function takes text as input and outputs a numerical representation of the text. This numerical representation is called a vector. There are many different embedding functions available, each with its own strengths and weaknesses. One popular embedding function is OpenAI's Text Embedding ADA 002 model, which is a powerful model that can capture the meaning of text very well. Outputs. A vector store object that can be used to store and retrieve vectors. The vector store object provides a way to store and retrieve the vectors that were generated by the embedding function. It also provides a way to search for vectors that are similar to a given vector. Working methodology creates a table in Xatha to store the vectors. The vectors are stored in a table that is created in the Xatha database. Embeds the text data and stores the vectors in the table. The text data is embedded using the embedding function, and the resulting vectors are stored in the Xatha table. Prerequisites: an Xatha account. You will need an Xatha account to use the Xatha vector store. You can create a free Xatha account at https://xatha.io. An Xatha database. You will also need an Xatha database to store the vectors. You can create a new Xatha database by logging into your Xatha account and clicking the Create Database button. Fine-tune parameters. Embedding function. The embedding function to use. This parameter specifies the embedding function that will be used to embed the text data. As mentioned above, OpenAI's text embedding ADA 002 model is a popular choice. Table name. The name of the table to store the vectors. This parameter specifies the name of the Xatha table that will be used to store the vectors. For example, you could use the table name myVectors. Metrics. Latency of vector retrieval. This metric measures the time it takes to retrieve a vector from the vector store. A lower latency is better. Accuracy of vector search. This metric measures the accuracy of the vector search. A higher accuracy is better. Visualization plots. Distribution of vector distances. This visualization plot shows the distribution of vector distances between different vectors in the vector store. This can be helpful for understanding the relationships between different vectors. Error analysis. Check for errors in embedding function. This involves checking if the embedding function is working correctly and is generating valid vectors. Verify Xatha table schema. This involves verifying that the Xatha table has the correct schema to store the vectors. The schema defines the structure of the table, including the columns and data types. Challenges and fixes. Xatha table creation errors. These errors can occur if there is a problem creating the Xatha table to store the vectors. Check Xatha table permissions. Make sure that you have the necessary permissions to create the Xatha table. For example, you might need to be a database administrator or have write access to the database. Embedding function errors. These errors can occur if there is a problem with the embedding function. Ensure embedding function is properly configured. Make sure that the embedding function is properly configured and is working correctly. This might involve checking the API key or making sure that the embedding function is properly installed. Langchain Community Vector Stores vLite details. A lightweight vector store designed for fast indexing and retrieval. Built on top of the FICE library. FICE, an open-source library by Facebook AI Research, provides efficient similarity search and clustering algorithms, making it ideal for large-scale vector data. vLite leverages FICE capabilities to deliver high-speed indexing and retrieval, particularly beneficial for handling massive datasets. Inputs. Text data that needs to be transformed into numerical representations, known as embeddings, for efficient similarity search and retrieval. For instance, you could input a collection of articles, product descriptions, or customer reviews, each represented as a text document. Outputs. Embeddings of the input text, representing each text document as a numerical vector. These vectors capture the semantic meaning of the text, allowing for efficient comparison and retrieval. Index that stores the embeddings, enabling fast searching of similar embeddings based on their proximity in the vector space. Think of it as an organized storage system that allows you to quickly find the closest matches to a given query. Embedding. Working methodology. Embeddings are generated using a chosen embedding model, a machine learning model trained to map text into numerical vectors. The choice of embedding model depends on the specific application and the type of text being processed. For example, if you are dealing with scientific articles, a model trained on scientific text might be more suitable. Embeddings are stored in FICE index, a data structure optimized for efficient search and retrieval of similar vectors. FICE supports various index types, each offering different trade-offs between indexing speed and search accuracy. Prerequisites. FICE library installed. This library is crucial for vLite's efficient indexing and retrieval functionality. It's a prerequisite for running vLite and performing vector search operations. Fine-tune parameters. FICE index type, which determines the underlying data structure used for indexing and searching embeddings. Different index types offer various trade-offs in terms of speed and accuracy. Selecting the right index type is crucial for optimizing performance based on the specific use case and dataset characteristics. Embedding model used, which impacts the quality and effectiveness of the embeddings generated. Different models are trained on different datasets and have varying strengths and weaknesses. Choosing the appropriate embedding model is essential for achieving optimal results for a specific task. Metrics. Retrieval accuracy. Measuring how well the system retrieves relevant results based on the similarity of embeddings. This metric indicates the system's ability to find the most relevant documents or items based on a given query. Higher accuracy implies better search results. Indexing speed. Measuring the time required to build the index for a given dataset. This metric indicates the system's efficiency in storing and organizing embeddings, which directly impacts the responsiveness of the system. Faster indexing allows for quicker updates and processing of new data. Visualization plots. Retrieval accuracy vs. index size. Illustrating the trade-off between search accuracy and the size of the index. This plot helps understand how increasing the index size, potentially by adding more embeddings, impacts the accuracy of retrieval results. Indexing speed vs. dataset size. Showcasing the relationship between the dataset size and the time required to build the index. This plot highlights the efficiency of the indexing process as the dataset grows. It's crucial for understanding the scalability of the system and its ability to handle large datasets. Error analysis. FICE index mismatch. Occurring when the index structure used for searching is incompatible with the embeddings stored in the index. This can lead to inaccurate search results and retrieval errors. Embedding model incompatibility. Arising when the embedding model used for generating new embeddings is different from the one used to build the initial index. This inconsistency can lead to inaccurate comparisons and retrieval results. Challenges and fixes. Challenge 1. Slow retrieval for large datasets. A common challenge for vector stores when dealing with a massive number of embeddings. As the dataset size increases, searching for similar embeddings can become computationally expensive. Fixes to challenge 1. Optimize FICE index parameters. Adjusting the index structure and configuration to improve search efficiency. This involves fine-tuning parameters specific to the index type, such as the number of clusters and the search algorithm used. Challenge 2. Limited embedding model support. Restricting the choice of embedding models for generating embeddings. This limitation can hinder the system's ability to leverage the most suitable embedding model for specific tasks or domains. Fixes to challenge 2. Integrate additional embedding models, expanding the range of embedding models supported by the system. This allows users to choose the most appropriate embedding model for their specific needs and achieve optimal results. Langchain Community Vector Stores ZEP Collection Config. Collection configuration for ZEP. Inputs. The data used to construct the vector store could include text, code, or other structured data. A pre-trained embedding model that maps text or other data to numerical representations, enabling similarity comparisons. For instance, a model like Sentence Transformers or OpenAI's Text Embedding ADA 002. Outputs. A vector store that efficiently stores and retrieves data using its vector representations. Working methodology. Creating a ZEP collection, which is a specialized data structure designed for storing and retrieving vector embeddings. Storing the embeddings of the input data and associating them with the original data. Allowing for efficient retrieval based on semantic similarity. Prerequisites. ZEP, an open-source Python library specifically designed for working with vector embeddings, must be installed. Fine-tune parameters. The dimensionality of the vector embeddings used to represent data points, impacting the computational cost and the effectiveness of semantic similarity comparisons. The number of data points stored in the collection, influencing the storage requirements and retrieval performance. Metrics. The amount of data stored in the vector store, directly related to the memory usage and the capacity of the collection. The accuracy of the vector store in retrieving relevant data points based on semantic similarity. Queries. Visualization plots. Visual representations that help in understanding the distribution of the vector embeddings in a lower dimensional space, facilitating the analysis of data clusters. Plots that demonstrate the performance of the vector store in retrieving relevant data based on similarity queries, providing insights into the effectiveness of the embeddings and the search process. Error analysis. Cases where the calculated embeddings fail to accurately represent the semantic meaning of the data, leading to inaccurate retrieval results. Situations where the vector store returns irrelevant data points, potentially due to poor embedding quality, inadequate data representation, or issues in the search algorithm. Challenges and fixes. Large data volume, posing challenges in storing and retrieving data efficiently. Chunking the data into smaller segments to improve processing efficiency and reduce memory usage. Slow retrieval speed, especially for large datasets, impacting the user experience. Employing efficient search algorithms, like approximate nearest neighbor search techniques, to optimize retrieval performance and reduce search time. Langchain Community Vector Stores Yellowbrick. This is a detailed description of the Langchain Community Vector Stores Yellowbrick, which is a vector store built on Yellowbrick. Yellowbrick is a fast in-memory database that uses a columnar storage format and an optimized query execution engine. Inputs. This denotes the data that will be stored in the vector store, making it the core content for the vector store. The embedding function is a crucial component that determines how the data is converted into numerical representations called embedding vectors, which can be efficiently understood by the vector store. This is optional. Outputs. The vector store object is the end result of the process. This object enables the storage and retrieval of data within the vector store. It acts as the interface for interacting with the stored data. Working methodology. The data undergoes an initial transformation using the provided embedding function. This converts the data into embedding vectors, which are numerical representations of the data. The generated embedding vectors are then stored in the Yellowbrick database. This ensures that the data is stored efficiently and can be retrieved quickly for similarity search. Operations. Prerequisites. Before utilizing the Langchain Community Vector Store's Yellowbrick, you need to have the Langchain and Yellowbrick libraries installed in your environment. These libraries provide the necessary functionalities to interact with the vector store and pay. Database. A running Yellowbrick database instance is essential for the vector store to function properly. The Yellowbrick database provides the storage mechanism for the embedding vectors, enabling efficient query execution. Fine-tune parameters. The embedding function parameter defines the function used to convert the input data into embedding vectors. Choosing the right embedding function is crucial for achieving optimal performance and accuracy in the vector store. The embedding dimension parameter determines the dimensionality of the embedding vectors. This value influences the complexity and memory usage of the vector store. Selecting an appropriate dimensionality is important to balance accuracy and efficiency. Metrics. Latency refers to the time it takes for the vector store to respond to queries. Lower latency indicates faster response times, which is essential for real-time applications. Memory usage refers to the amount of memory consumed by the vector store. Minimizing memory usage is critical for efficient operation, especially when dealing with large datasets. Visualization plots. This visualization plot allows users to analyze the relationship between query time and the number of documents in the vector store. By examining this relationship, users can understand how query performance scales with the size of the dataset. Error analysis. Checking the Yellowbrick logs provides valuable information for debugging and troubleshooting any errors encountered during the operation of the vector store. This log analysis can help identify issues related to database connectivity, query execution, or storage. Ensuring that the provided embedding function is compatible with the Yellowbrick database is crucial for the vector store to function correctly. The embedding function must be able to process the data and generate embedding vectors that are compatible with the Yellowbrick database schema and data types. Challenges and fixes. Challenge 1. Slow query times can occur when the vector store is unable to process queries efficiently. This can happen due to various factors, such as an inefficient database configuration, inadequate indexing, or a large number of documents in the vector store. Fixes to Challenge 1. Optimizing the Yellowbrick database configuration can significantly improve query performance. This can involve tuning database parameters, such as the number of threads used for query execution, the size of the cache, and the indexing strategy. Challenge 2. High memory usage can be a problem when dealing with large datasets, especially if the embedding vectors are high-dimensional. This can lead to performance issues and resource constraints. Fixes to Challenge 2. Using a smaller embedding dimension can significantly reduce the memory footprint of the vector store. This can involve choosing a different embedding function that produces lower dimensional embedding vectors or using dimensionality reduction techniques to reduce the dimensionality of the existing embedding vectors. Using a different embedding function that is more efficient in terms of memory usage can also help mitigate high memory usage. ZEP Vector Store Details. A detailed description of the ZEP Vector Store. A vector store implementation leveraging the Xelitsa's ZEP Zero Effort Python framework. This vector store excels in its efficiency and ease of use, making it a powerful tool for tasks involving semantic search and information retrieval. Inputs. Text data intended for embedding. This could include articles, product descriptions, or any textual content you wish to analyze. For instance, You might feed in a collection of customer reviews for sentiment analysis or a corpus of scientific papers for topic modeling. A ZEP client instance, which acts as the intermediary between your application and the ZEP server. This client handles the communication and interaction with the ZEP framework, ensuring smooth data transfer and processing. Outputs: vector embeddings for each text input, representing the semantic meaning of the text in a numerical format. These embeddings are crucial for similarity comparisons and search operations, allowing you to find related content based on meaning rather than just keywords. Search results based on similarity to input query vectors. This output provides a ranked list of documents or text entries that are most similar to your query, reflecting their semantic proximity to your search intent. Working methodology: the ZEP vector store meticulously embeds text data using a specified embedding model. This model, trained on vast amounts of text, encodes the meaning of each text input into a vector representation. Popular choices include sentence transformers for sentence-level embeddings and OpenAI's application programming interface API for powerful text embeddings. The store then proceeds to organize these embeddings and associated metadata within a ZEP index. This index facilitates efficient search and retrieval, enabling rapid lookups for similar content based on the semantic similarity of embeddings. Prerequisites: the ZEP zero-effort Python framework needs to be installed. This framework provides a user-friendly interface for interacting with Zilitsa's vector database, simplifying the process of storing and searching vector embeddings. An embedding model, such as sentence transformers or OpenAI's application programming interface API, is essential. This model converts text inputs into meaningful vector representations, forming the foundation for similarity comparisons and search. Fine-tune parameters: the choice of embedding model plays a crucial role in defining the semantic representation of text. Selecting an appropriate model, whether sentence transformers or OpenAI's API, is critical for achieving accurate results in similarity searches. ZEP index configuration parameters allow you to optimize the performance and efficiency of a vector store. These parameters govern aspects like the indexing method, data structures used, and memory allocation, significantly impacting search speed and resource utilization. Metrics: retrieval accuracy gauges the effectiveness of the vector store in retrieving relevant documents. This metric measures how well the system identifies content that truly matches the user's search intent, reflecting the quality of the embeddings and the search algorithm. Search latency quantifies the time taken to execute a search query. This metric is crucial for ensuring a responsive user experience, particularly in applications where real-time search is critical, such as interactive search interfaces or recommendation systems. Visualization plots: dimensionality reduction plots provide a visual representation of the embedded vectors, facilitating insights into the underlying structure of the data. These plots help identify clusters, outliers, and relationships between different text inputs, enhancing understanding of the semantic relationships within the dataset. Search result ranking plots illustrate the ranking of search results based on their similarity to the query vector. This visualization helps assess the relevance and quality of retrieved documents, providing a visual representation of the search algorithm's effectiveness in identifying the most relevant content. Error analysis: incorrect embeddings can arise due to limitations in the chosen embedding model. These limitations might stem from the model's training data or its inherent bias, leading to inaccurate representations of text and ultimately impacting search results. Search performance issues can be attributed to suboptimal indexing configurations. Inadequate parameters, such as index size, data structures, and search algorithm choices, can lead to slow search times and hinder the overall efficiency of the vector store. Challenges and fixes. Challenge 1. ZEP client initialization errors can occur during the setup process, potentially hindering the seamless integration of the vector store with your application. These errors might arise from misconfigured environment variables, network issues, or incorrect installation of the ZEP framework. Fixes to challenge 1. Ensuring that ZEP is installed correctly is crucial, as a faulty installation can lead to initialization problems. Verify that the necessary dependencies are in place and that the framework is properly integrated into your environment. Verifying ZEP server connection details ensures that the client can communicate with the ZEP server effectively. Double-check the server's address, port, and credentials to ensure a stable connection. Challenge 2. Slow search performance can significantly impact the user experience, particularly in real-time applications. Factors such as inefficient indexing strategies, suboptimal embedding models, or hardware limitations can contribute to slow searches. Fixes to challenge 2. Optimizing ZEP index parameters can significantly enhance search performance. Experiment with different indexing methods, data structures, and memory allocation settings to find the optimal configuration for your specific needs. Using a faster embedding model can significantly reduce search times. Explore models specifically designed for speed, such as lightweight models trained on large-scale datasets or models optimized for specific domains. ZEP Vector Store Summary. ZEP Vector Store is a vector database that stores and retrieves embeddings for use in text-based applications. For example, you can use ZEP Vector Store to store and retrieve embeddings of documents, code, or other text data, and then use those embeddings to perform tasks such as semantic search, question answering, and text summarization. Inputs. Text data to be indexed and retrieved. This includes the text content itself, which can range from short phrases to entire documents. Metadata for the text data, such as the source or author. Metadata provides additional context and information about the text data, making it easier to organize, filter, and retrieve. For example, you might include metadata such as the document's title, author, publication date, or URL. Outputs. Embeddings of the text data. These are numerical representations of the text data that capture its semantic meaning. Embeddings are typically high-dimensional vectors that can be used to compare and search for similar text data. Search results for text queries. When you query the vector database with a text query, ZEP Vector Store returns a list of text documents that are most similar to the query based on their embeddings. This is often referred to as semantic search, as the search engine considers the meaning of the query and the text data, rather than just matching keywords. Steps. Initialize the ZEP Vector Store with an existing Zilli Milvus collection or create a new one. Milvus is an open-source vector database that stores and manages vectors efficiently. By initializing with an existing collection, you can leverage the pre-indexed data. If you create a new collection, you can define its structure and parameters. Add text data and metadata to the vector store. This step involves converting the text data into embeddings and storing them in the vector database, along with the associated metadata. Retrieve embeddings for text data by providing the document IDs. After the text data is indexed, you can retrieve its embeddings using its unique identifier, known as the document ID. Search for relevant text data based on a query using similarity search. This involves comparing the query's embedding with the embeddings of all the documents in the vector database. ZEP Vector Store returns the documents with the highest similarity scores, meaning those that are most semantically similar to the query. Prerequisites: Zilli Milverse database, a high-performance vector database, is necessary. Install Milverse by following the instructions on the official documentation at https://milverse io-docs install Milverse. ZEP Vector Store Library, a Python library that provides an interface for interacting with Milverse for vector storage and retrieval. Install ZEP Vector Store using pip install ZEP Vector Store. Fine-tune parameters. Similarity metric, a function that calculates the similarity between two vectors. Different metrics emphasize different aspects of the data. Cosine similarity calculates the cosine of the angle between two vectors. This is a common choice for semantic search as it considers the overall direction of the vectors, rather than just their magnitude. Euclidean distance calculates the straight line distance between two vectors. This is another common choice for vector similarity calculations, but it can be less robust to outliers than cosine similarity. Index type, which determines how the vector database stores and retrieves embeddings. Different index types offer different trade-offs in terms of performance, storage efficiency, and search accuracy. Flat index stores all embeddings in memory and performs a brute force search for similar vectors. This is the simplest and most straightforward index type, but it can be slow for large datasets. IVF flat index uses a technique called inverted file indexing to group similar embeddings together. This allows for faster search performance than flat indexing, as the database only needs to search through a smaller subset of embeddings. Challenges and fixes. Slow query performance for large datasets can occur because it takes time to calculate similarity scores for all vectors in the database. Optimize Milverse configuration and index type. For large datasets, it may be necessary to use a more efficient index type, such as IVF flat. You can also optimize the Milverse configuration parameters, such as the number of partitions and the number of shards, to improve query performance. Limited integration with other Langchain components can limit its flexibility. Use custom integrations or adapters to connect with other Langchain tools. For example, you can create a custom adapter that allows you to use ZEP Vector Store with Langchains. Conversational AI tools. Langchain Community Vector Stores Annoy Dependable Annoy Import. Annoy Vector Store is a vector database that leverages Annoy library for efficient similarity search, and is a part of the Langchain Community Library. Annoy Vector Store provides an efficient method to store and retrieve vectors based on their similarity to a query vector. This is particularly useful in applications like recommendation systems, document search, and image retrieval. Inputs. Data for storing vectors and their associated metadata. The input data consist of vectors representing the items to be stored and their corresponding metadata, which provides additional information about each item. For example, in a document search application, the vectors could represent the embedding of the document text, and the metadata could include the document title, author, and publication date. Annoys parameters, including number of trees, dimension of the vectors, metric used for distance calculation. Annoys parameters are crucial for optimizing the performance of the vector database. The number of trees determines the trade-off between search speed and accuracy. A higher number of trees results in more accurate search results but also requires more time to perform searches. The dimension of the vectors defines the number of features used to represent each item. The metric specifies the distance function used to calculate the similarity between vectors. Common metrics include cosine similarity and Euclidean distance. Outputs. Vector store object, allowing for operations like add, similarity search, and retrieval. The output is a vector store object that provides the necessary API for interacting with the stored vectors. This object allows you to add new vectors to the store, perform similarity searches, and retrieve vectors based on their metadata. Steps. Initialize Annoy vector store with Annoy's parameters. The first step is to initialize the Annoy vector store object with the desired parameters, including the number of trees, vector dimension, and distance metric. Add vectors and associated metadata to the store. Once the Annoy vector store object is initialized, you can add vectors and their associated metadata to the store. This process involves converting the input data into a format compatible with Annoy and storing it in the database. Perform similarity searches using Annoy's search functions. The primary function of the Annoy vector store is to perform similarity searches. This involves providing a query vector and retrieving the most similar vectors from the store based on the chosen distance metric. Prerequisites. Annoy library installed. Annoy library is a fast, efficient library for approximate nearest neighbor search. It is essential for the Annoy vector store to function correctly. Pip install Annoy. Installing the Annoy library is a simple process using the pip package manager. This command will download and install the necessary Annoy packages and dependencies on your system. Fine-tune parameters. Number of trees controls the trade-off between search speed and accuracy. The number of trees is a critical parameter that influences the search performance of Annoy. Increasing the number of trees improves accuracy but also increases search time. In real-world applications, the number of trees is typically chosen based on the desired balance between speed and accuracy. Considering factors like the size of the dataset and the criticality of search precision. Metric. Choose the appropriate metric for distance calculation, e.g., cosine, Euclidean. The choice of distance metric is crucial for determining the similarity between vectors. Cosine similarity is commonly used for measuring the angle between two vectors, while Euclidean distance calculates the straight-line distance between 2 points in space. The appropriate metric depends on the specific application and the characteristics of the data. Challenges and fixes. Annoy is known to be slow for large datasets. Annoy's performance can degrade for large datasets due to the computational complexity of nearest neighbor search. This limitation becomes more pronounced as the dataset size increases, leading to longer search times. Consider using other vector databases for larger datasets. For handling large datasets, it is recommended to explore other vector databases that are specifically optimized for scalability, such as FICE or HNSW. These databases often employ different indexing techniques and algorithms that are more efficient for large-scale similarity search. Potential issues with serialization and deserialization for large datasets. Serialization and deserialization are processes of converting data between different formats, such as converting an object to a byte stream for storage or transmission. In the context of Annoy vector store, serialization and deserialization can become problematic for large datasets, potentially leading to performance bottlenecks. Explore alternative serialization methods or use a different vector store. To address these issues, you can investigate alternative serialization methods that are more efficient for large datasets, such as using a binary format or employing specialized libraries for serialization. Alternatively, Using a different vector store designed for handling large datasets might be a more practical solution. Langchain Community Vector Stores FICE Dependable FICE Import. FICE Facebook AI Similarity Search is an open-source library for efficient similarity search and clustering of large datasets. Dependable FICE import is a utility to address a common issue in FICE: inconsistencies in import behavior due to versioning and environment setups. This method ensures a consistent and predictable way of using FICE inputs, a FICE index that has been previously built. This index contains a collection of data points and their corresponding embeddings, typically generated by a vector embedding model. A list of embeddings that you want to search against. These are the vectors representing the data points that you want to find similar counterparts for in the FICE index. Outputs: a list of the closest matches from the FICE index to the input embeddings. The output will contain a list of the data points from the index that are most similar to the input embeddings based on their vector representations. The corresponding distances between the input embeddings and the retrieved matches. The output will also contain a list of the distances between each input embedding and its corresponding match. This distance represents the similarity, with smaller distances indicating higher similarity. Steps: install FICE using pip. Specifying a specific version to avoid import issues. You can specify the desired version of FICE when installing it using pip. This ensures that you are using the exact version that you need and minimizes the risk of unexpected behavior caused by version incompatibilities. Import FICE from the specified version using the from version import format. This import statement ensures that you are importing the FICE module from the specific version you installed using pip. This helps to maintain consistency across different environments and avoids issues related to import paths or version mismatches. Prerequisites: a local installation of Python. This is necessary as FICE is a Python library and requires a Python environment to run. Python version 3.6 or higher. Python version 3.6 or higher is required for FICE. FICE installed on the system. You need to install FICE on your system using pip. This can be done by installing the appropriate version of FICE using pip install FICE CPU for CPU BASED implementations or pip install FICE GPU for GPU accelerated implementations. Fine-tune parameters. The specific version of FICE to use. The specific version of FICE you use can impact performance and functionality. It's important to choose a version that is compatible with your other libraries and dependencies and that provides the features you need. The number of nearest neighbors to retrieve. This parameter specifies how many of the closest matches from the FICE index you want to return as results. A larger number of nearest neighbors will provide a more comprehensive set of potential matches, but may increase search time. Challenges and fixes. Import errors or inconsistencies in FICE behavior. It is important to ensure that FICE is imported consistently across different environments. By specifying the version explicitly and using the from version import format, you can avoid import issues related to version mismatches or conflicting paths. Version conflicts with other libraries or dependencies. Version conflicts can occur when different libraries have conflicting dependencies on different versions of FICE. To resolve this, you can install a specific version of FICE that is compatible with all other libraries in your project. Langchain Community Vector Stores ZEP Vector Store. a vector store implementation based on the ZEP library, designed to enable efficient vector search and similarity matching using the ZEP server. ZEP Vector Store leverages the ZEP server's capabilities to store and retrieve vectorized representations of data, enabling applications like document search, recommendation systems, and question answering. Inputs: textual data, raw text content that will be transformed into vectors and stored in the vector store. For example, this could include articles, blog posts, product descriptions, or any other textual information. Metadata: additional information associated with the textual data, such as author, publication date, topic, or any other relevant context. Metadata can enhance search relevance by providing more insights into the content. Outputs: embeddings, numerical representations of the textual data, created using embedding models, e.g., BERT, sentence transformers. These embeddings capture semantic meaning and relationships between words, allowing for more accurate similarity comparisons. Search results: the output of a search operation, containing a list of documents or items ranked based on their similarity to the query. Search results provide the most relevant content matching the user's intent. Steps: initialization: the ZEP vector store is initialized by providing the ZEP server URL and the database name. This step establishes a connection to the ZEP server and prepares the vector store for data ingestion. For example, you might initialize the vector store with the URL http://myspserver.com and the database name my documents. Data ingestion: textual data along with its associated metadata is ingested into the ZEP server, creating a vector index. During ingestion, the data is converted into numerical embeddings, which are then stored within the ZEP server's database, allowing for efficient search and retrieval. For instance, you could ingest a collection of scientific articles with their respective authors, publication dates, and keywords. Embedding generation: the ZEP vector store utilizes embedding models to generate numerical representations of the textual data. These embeddings capture semantic relationships between words and phrases, enabling similarity search based on meaning rather than just lexical matching. The chosen embedding model should be suitable for the type of data and the intended use case. For example, if you are dealing with scientific articles, you might choose a model specialized in scientific literature. Search: the vector store performs a similarity search based on query embeddings retrieved from the query text. This search operation leverages the vector index to efficiently find documents or items most similar to the query, allowing users to discover relevant content based on their search intent. For instance, a user might search for machine learning algorithms, and the vector store would return a list of articles or documents relevant to this topic. Prerequisites: ZEP server: a running instance of the ZEP server is required, configured with appropriate database settings. The ZEP server acts as a backend for the vector store, handling data storage, indexing, and search operations. For example, you might need to configure the ZEP server to use a specific database engine and define access permissions. ZEP library: the ZEP Python library must be installed within the environment to interact with the ZEP server and perform vector store operations. This library provides the necessary functions for data ingestion, search, and other vector store management tasks. You can install the ZEP library using a package manager like pip install ZEP. Fine-tune parameters. ZEP server configuration: the ZEP server configuration determines the connection details, such as the server URL, database name, and any authentication credentials, Optimizing the server configuration can improve performance and stability. For example, you can configure the database engine, specify storage settings, and adjust network parameters. Indexing parameters control how the vector index is built and optimized for search. These parameters can include options for dimensionality reduction techniques, index structure, and search algorithms. For example, you might adjust the number of dimensions used for embedding vectors, select a specific indexing algorithm, and choose the appropriate search algorithm for your use case. Challenges and fixes. Server connectivity issues. Connection errors between the client Zep vector store and the Zep server can occur due to network problems, server outages, or misconfigured connection settings. To resolve these issues, verify network connectivity, confirm server availability, and reconfigure the connection settings if needed. In real-world scenarios, you might need to check for firewall restrictions, ensure the server is reachable, and double-check the provided URL and port numbers. Indexing performance degradation. Slow indexing or search operations can be caused by various factors, including inefficient indexing parameters, high dimensionality of embeddings, or unoptimized embedding models. To address these issues, optimize indexing parameters, e.g., adjust indexing algorithms, experiment with different dimensionality reduction techniques, consider using more efficient embedding models, and explore alternative indexing strategies for improved performance. In real-world scenarios, you might need to analyze the data distribution, optimize embedding model selection, and adjust the index structure based on the specific characteristics of your data. Langchain Community Vector Stores. LanceDB import. LanceDB summarized. This component imports embeddings into a LanceDB vector store, enabling efficient similarity search and retrieval based on embedding vectors. Inputs. Lists of floating point numbers representing the embeddings for each data point. Each inner list represents an embedding vector. Example 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. List of strings representing unique identifiers for each data point. These IDs are used to retrieve corresponding embeddings in metadata. Example Document 1, Document 2. Dictionary containing metadata associated with each data point. The keys of the dictionary represent metadata fields, and the values are lists of corresponding values for each data point. Example Author John Doe, Jane Doe. Date 20,230,101. 20230201. Outputs. A LanceDB vector store object, which provides methods for searching and retrieving data based on embeddings and metadata. Steps. A new LanceDB vector store is created, specifying the table name and connection URI to connect to the LanceDB instance. The embeddings, IDs, and metadata are added to the newly created LanceDB vector store. The embeddings are stored as vectors in the LanceDB table, linked to their corresponding IDs and metadata. Prerequisites. Install the LanceDB library using pip. This step downloads and installs the necessary components for interacting with LanceDB. Install the Python client for LanceDB using pip. This client provides the Python API application programming interface for working with LanceDB from Python code. Fine-tune parameters. A callable function that takes a piece of text as input and outputs a numerical embedding vector, representing the text's semantic meaning. The embedding function is used to generate embeddings for new data points before adding them to the vector store. A dictionary containing configuration parameters for the index used to organize and search. Embeddings in the LanceDB vector store. The specific parameters depend on the chosen index type, such as FICE or HNSW, and can include parameters like the number of neighbors to consider during search, the dimensionality of the embeddings, and other optimization parameters. Name of the table in the LanceDB database where the embeddings, IDs, and metadata will be stored. Choosing a descriptive table name helps organize your data and makes it easier to manage different data sets. Connection string used to establish a connection to the LanceDB database instance. This string typically includes information like the host address, port number, database name, and any authentication credentials required. Challenges and fixes. Issues connecting to the LanceDB database instance. This could be due to an incorrect connection URI, network connectivity problems, or permission issues. To resolve connection issues, check the connection URI for accuracy and ensure that the LanceDB database is reachable and accessible. Problems during index creation within the LanceDB vector store. This might occur due to an invalid index configuration, insufficient resources, or conflicting parameters. To fix index creation failures, carefully verify the index configuration parameters and adjust them as needed. Ensure the index parameters are compatible with the data and the chosen index type. Also, consider increasing available resources if necessary. Langchain Community Vector Stores Neo4j Vector Check if not null summary. Verifies that the Neo4j database connection and the vector store configuration are valid. Returns an error message if either is invalid. Inputs. Neo4j URI explanation. The Uniform Resource Identifier URI of the Neo4j database. This URI is used to establish a connection to the database instance. For example, the URI can be bold localhost 7687 for connecting to a Neo4j instance running locally on port 7687. Neo4j auth explanation. The authentication credentials for accessing the Neo4j database. This includes the username and password for accessing the database instance. These credentials are used to verify the identity of the user attempting to access the database. Neo4j label explanation. The label used to identify the nodes in the Neo4j database that represent the vector store. This label is used to retrieve and update the stored vectors in the Neo4j database. Outputs. None explanation. The function does not return any explicit output. It simply verifies the connection details and configuration of the Neo4j vector store. Steps. Check if provided Neo4j connection details are valid. Explanation. The function attempts to establish a connection to the Neo4j database using the provided URI and authentication credentials. If the connection cannot be established, an error message is returned. Check if vector store configuration is valid. Explanation. The function verifies the vector store configuration details, including the Neo4j label used to identify the nodes representing the vectors. If the configuration is invalid or missing, an error message is returned. Prerequisites. Neo4j database instance explanation. An instance of the Neo4j database needs to be running in accessible to the application. The instance should be properly configured and ready to accept connections. Neo4j 4.4 or later explanation. The Neo4j database instance should be version 4.4 or later. Older versions might not support all the features required by the vector store implementation. Neo4j driver for Python explanation. The Neo4j driver for Python needs to be installed in the environment where the application runs. This driver provides the necessary API for interacting with the Neo4j database from Python. Install using pip explanation. The Neo4j driver can be installed using the package manager pip. This ensures the correct version of the driver is available for use. Fine-tune parameters. Neo4j URI explanation. The URI of the Neo4j database can be adjusted based on the specific deployment environment. Neo4j auth explanation. The authentication credentials can be updated to match the actual username and password for accessing the database. Neo4j label explanation. The Neo4j label used to identify the nodes in the database can be customized to fit the specific implementation of the vector store. Challenges and fixes. Incorrect Neo4j connection details explanation. If the provided URI or authentication credentials are incorrect, the connection to the Neo4j database will fail. Verify the connection details including the Neo4j URI authentication credentials and the label for the vector store explanation. The connection details should be carefully verified to ensure they match the actual configuration of the Neo4j database. This includes checking the URI, the username and password, and the label used for the vector store. Invalid vector store configuration explanation. If the configuration details of the vector store are incorrect or incomplete, the application might not be able to correctly store or retrieve vectors from the Neo4j database. Check the configuration including the Neo4j label embedding dimension and the index configuration. Explanation. The vector store configuration needs to be reviewed to ensure all parameters are set correctly. This includes verifying the label used to identify the nodes, the embedding dimension of the vectors, and the indexing strategy used to efficiently retrieve vectors. Langchain Community Vector Stores Neo4j Vector Combine Queries. This component describes how to combine multiple queries for a Neo4j vector store. Inputs. The first query to be combined, which could be a natural language question or a structured query. For example, find all documents about the history of artificial intelligence. The second query to be combined. For example, find all documents about the impact of artificial intelligence on society. Outputs. A single, combined query that incorporates the information from both input queries. This combined query is then used to retrieve relevant data from the Neo4j vector store. Steps. The first query is passed into its individual components to identify keywords and relationships. The second query is also passed into its individual components. The passed components from both queries are combined to create a single, coherent query that reflects the intent of both input queries. The combined query is executed against the Neo4j vector store, which retrieves documents that match the combined query based on their vector representations. Prerequisites. A Neo4j database is required to store the vector representations of documents and facilitate efficient querying. The Neo4j database should be version 4.4 or later to support the vector store functionality. A Neo4j vector store needs to be created within the Neo4j database to store and retrieve vector embeddings of documents. A vector store is created by indexing documents with their vector representations, which enables fast and efficient similarity searches. Fine-tune parameters. The similarity threshold parameter controls how similar two documents need to be considered a match. A higher threshold requires a greater degree of similarity, while a lower threshold allows for more loosely related documents to be retrieved. The query expansion strategy parameter determines how the combined query is expanded to include additional related terms. This strategy can be used to broaden the search and retrieve a more comprehensive set of documents. Challenges and fixes. Inconsistent query syntax can lead to incorrect parsing in query execution. To address this challenge, it is important to standardize the query syntax by defining a set of rules and conventions that are consistently applied across all queries. Data schema inconsistencies can arise from variations in the way data is structured and represented across different documents. To ensure consistent data schema, it is essential to establish a clear and well-defined data model that is followed consistently when indexing documents into the vector store. Summary of Langchain Community Vector Store's Langchain Get Embedding Store. This Langchain Community Vector Store method retrieves an embedding store from Langchain, a vector database that supports high-dimensional data. Inputs: a vector store that contains the embedding data. In this case, the vector store is assumed to be a Langchain vector store. Outputs: an embedding store, which is a specialized data structure used to store and access embedding vectors. Steps: retrieve the embedding store from the Langchain vector store. This involves interacting with the Langchain application programming interface API to access the necessary data. Return the retrieved embedding store. Prerequisites: Langchain is a vector database that stores high-dimensional embedding data efficiently. The method requires a Langchain vector store, which is a specific type of vector store that utilizes Langchain for storage and retrieval of embedding data. Langchain is an open-source vector database that utilizes Pinecone as its underlying storage mechanism. Pinecone is a cloud-based vector database service. The Langchain library needs to be installed to use its functionality. This involves installing it using the Python package installer pip. Pip install Langchain installs the necessary packages to access and utilize the Langchain API. Fine-tune parameters. This method does not require any fine-tuning parameters, as it primarily focuses on retrieving an existing embedding store from a Langchain vector store. Challenges and fixes. If the embedding store is not found, it implies that the desired store is either not present in the Langchain vector store or the method is unable to locate it. This could be due to a mismatch in names or a misconfiguration during the store creation process. It is essential to ensure that the embedding store name used in the method matches the name of the store actually present within the Langchain vector store. You can check if the embedding store is available in the Langchain vector store. Langchain Community Vector Store's Neo4j Vector Dict to YAML Summary. This YAML document describes a process of converting a Python dictionary into a YAML string using Neo4j Vector and Langchain. This process converts a Python dictionary into a YAML string representation. A Python dictionary is the input for the process. A dictionary is a collection of key-value pairs. Each key in the dictionary should be unique. Real-world example. Users. Name John Doe. Age 30. City New York. The output of this process is a YAML string. YAML is a human-readable data serialization language. It is often used for configuration files and data interchange. Real-world example. Users. Name John Doe. Age 30. City New York. The Python dictionary is converted to a YAML string. This involves converting the key-value pairs in the dictionary into YAML syntax. Neo4j database, a graph database that stores data in the form of nodes and relationships. Neo4j Vector is a plugin for Neo4j that provides vector search capabilities. Driver, a software library that allows you to connect to and interact with a Neo4j database. Python library, a collection of code that provides additional functionality for Python. PyYAML, a Python library that allows you to convert Python objects to YAML strings and vice versa. None. This indicates that no fine-tuning parameters are required for this process. Challenge 1. Invalid dictionary. If the input dictionary is not a valid Python dictionary, the conversion process will fail. Fixes to challenge 1. Ensure the dictionary is a valid Python dictionary. A valid Python dictionary should have unique keys and values that are valid Python objects. Challenge 2. Error converting to YAML string. If the py-YAML library is not installed or if there is an error during the conversion process, the output will be an error message instead of a YAML string. Fixes to challenge 2. Check the py-YAML library is installed. You can install it using the following command: bash pip install pyal. Ensure the dictionary is valid. A valid Python dictionary should have unique keys and values that are valid Python objects. Langchain community vector stores Neo4j vector construct metadata filter. This function constructs a metadata filter that is used to filter documents stored in a Neo4j vector store. This filter can be used to narrow down the set of documents retrieved from the vector store based on specific criteria defined in the metadata associated with each document. Inputs. Neo4j driver. This input is a reference to a Neo4j driver object. This driver is used to establish a connection to the Neo4j database. It acts as an intermediary between the application and the database, facilitating communication and data exchange. Metadata filter template. This input is a template string that outlines the conditions used to filter documents. It uses placeholders that are replaced with actual values during the filtering process. This template specifies the metadata fields and criteria used for filtering documents. For example, a template might specify filter documents with a publication date after 2020. Outputs. Metadata filter. The output is a metadata filter that is generated from the template. This filter can be applied to the Neo4j database to retrieve only those documents that match the specified criteria. Steps. The construct metadata filter function first takes the Neo4j driver and the metadata filter template as input. It then uses the provided template to create a Neo4j Cypher query. Cypher is a graph query language used to interact with Neo4j databases, allowing for complex and efficient data retrieval. The generated query will incorporate the metadata filter conditions specified in the template. This query is then used to filter documents based on the specified metadata. The query is executed against the Neo4j database and only those documents that meet the filter conditions are retrieved. Prerequisites. Neo4j driver. This prerequisite refers to the Neo4j driver object. It is essential to have a driver instance established before using the construct metadata filter function. The driver is used to connect to the Neo4j database and perform operations on the data stored within it. Metadata filter template. This prerequisite indicates the need for a metadata filter template to be provided. This template provides the structure and criteria for filtering documents based on their metadata attributes. Without a template, the function cannot generate the filter required to select the desired documents. Fine-tune parameters. None. This indicates that there are no fine-tuning parameters available for this function. Challenges and fixes. Incorrect metadata filter template. If the metadata filter template contains syntax errors, it will result in an invalid query. In this case, it is essential to review the template string carefully, identify the errors, and correct them to ensure a valid and functional query. For example, if the template contains a missing closing parenthesis or incorrectly formatted metadata field name, this can lead to a query error. Missing metadata fields in the database. If the metadata filter template references metadata fields that are not present in the database, the filter will not work correctly. In this case, it is important to verify that the metadata fields specified in the template actually exist within the database. For example, if the template specifies filtering documents by author field, but the database does not have an author field, the filter will fail to filter documents effectively. Langchain community vector stores MyScale has mul sub-str. This function checks if a string contains multiple substrings. Inputs. The input string is the text that will be searched for the substrings. The list of substrings is a collection of strings that will be searched for within the input string. Outputs. A Boolean value indicating whether all the substrings are present in the input string. Steps. The function will iterate through each substring in the list of substrings. For each substring, the function will check if it is present in the input string. Prerequisites. Python 3.7 or higher is required to run this function. Langchain is a framework for building and deploying language models, and this function utilizes its capabilities. The MyScale library is a Python library specifically for interacting with the MyScale vector store. This library is necessary to use this function. Fine-tune parameters. There are no specific fine-tuning parameters for this function. Challenges and fixes. One challenge with this function is handling case sensitivity. To address case sensitivity, both the input string and the substrings can be converted to lowercase or uppercase before comparison. This ensures that the comparison is case insensitive and avoids issues arising from different capitalization. Another challenge is handling overlapping substrings. A more sophisticated substring matching algorithm that considers overlapping substrings is necessary. This involves carefully accounting for the positions of the substrings within the input string, especially when they share common characters. Langchain community vector stores Oracle vs Create Index. This YAML document describes the process of creating a vector index within an Oracle database using Langchain, a powerful framework for building and deploying language models. Inputs. The text data that will be indexed. This could be a collection of documents, articles, or any text-based data that you wish to make searchable or analyze. For example, a dataset of customer reviews, news articles, or technical documentation. The connection details necessary to establish a connection with the Oracle database. These details typically include the database host name or IP address, the port number, the username, and the password for the user account with appropriate privileges. Outputs. A vector index that is stored within the Oracle database. This index allows for efficient similarity searches based on the text data that has been indexed. It enables retrieving relevant documents or information based on queries that are semantically similar to the indexed text, rather than requiring exact keyword matching. Steps. Establish a connection to the Oracle database using the provided connection details. This step involves verifying the connection settings and ensuring that the user account has the necessary permissions to perform the subsequent operations. Create a vector store using Oracle VS. This involves initializing a vector store within the database, which will hold the text data and its corresponding vector representations. The choice of vector store depends on the specific use case and requirements, with options such as FAISS, HNSW, or ANOI available for different performance and storage characteristics. Add the text data to the newly created vector store. This involves converting the text data into numerical vectors using a suitable embedding model. such as sentence transformers or OpenAI's text embedding API. These vectors capture the semantic meaning of the text data, enabling efficient similarity searches based on semantic relationships. Create a vector index on the data that has been added to the vector store. This step involves defining the indexing strategy and parameters to optimize search performance based on the data characteristics and query patterns. For instance, you can choose from different index types, e.g., KD tree, ball tree, and configure parameters like the number of nearest neighbors to consider during search. Prerequisites. An Oracle database instance is required for storing and indexing the text data. The database version should be 12c or later, as earlier versions may lack support for some of the necessary features or may require additional configuration. An active subscription to Oracle Cloud Infrastructure (OCI) is needed to access and manage the Oracle database instance. OCI tenancy provides the necessary infrastructure and resources to host and operate the database. Fine-tune parameters. The name of the vector store to be created. This name is used to identify and reference the store within the database. A descriptive name, such as customer reviews or technical docs, can aid in understanding the purpose and content of the vector store. The name of the vector index to be created. This name is used to refer to the index within the database and distinguish it from other indices. A descriptive name, such as Reviews Similarity Index or Docs Semantic Index, can help in identifying the specific index based on its purpose and the indexing method employed. Parameters that define the specific characteristics and properties of the vector index. These parameters may include the type of index, such as a KD tree or ball tree, the number of nearest neighbors to consider during search, the distance metric used for similarity calculations, e.g., cosine similarity, Euclidean distance, and any other specific configurations relevant to the chosen indexing method. Challenges and fixes. Issues establishing a connection to the Oracle database. This could arise due to incorrect database credentials, incorrect host name or IP address, or issues with the database service itself. To address this, carefully verify the connection details provided, including the username, password, host name, and port number. Ensure that the database is accessible and that the provided user account has the required privileges to connect and perform the desired operations. Insufficient database privileges for the user account. The user account attempting to create the vector store and index might not have sufficient permissions to perform these actions within the database. To resolve this, ensure that the user account has the necessary privileges, such as create any index, create any table, and create any view to create and manage indices and tables. Consult the Oracle database documentation for specific privilege requirements and grant the necessary permissions to the user account. Errors encountered during the creation of the vector index. These errors could stem from incorrect index parameters, limitations of the chosen indexing method, or other database-specific issues. To diagnose and address these errors, review the database logs for specific error messages. Consult the Oracle documentation for troubleshooting guidance, and carefully examine the chosen index parameters. Verify that the index parameters are compatible with the chosen indexing method and the characteristics of the data being indexed. If necessary, experiment with different index parameters and indexing methods to find the most suitable configuration for your specific use case. Langchain Community Vector Stores Oraclef's Drop Index if exists. This component is designed to check if a given index exists in an Oracle database and drop it if found. Inputs: name of the index to be checked and dropped, For example, IDX customer name. Outputs. No output is generated if the index is dropped successfully. If the index does not exist, there is no output. Steps. The component will first check if the index exists in the Oracle database. If the index exists, the component will attempt to drop the index. Prerequisites. A valid connection to the Oracle database is required. This could be a connection string or a configured connection object. The connection string should contain the necessary details for connecting to the Oracle database, such as hostname, port, username, and password. The Oracle driver must be installed and configured on the system running the component. Oracle Instant Client is a lightweight and portable version of the Oracle client software that can be downloaded and installed separately. Fine-tune parameters. No fine-tuning parameters are required or supported by this component. Challenges and fixes. If the index does not exist in the database, no action is taken by the component. This is not considered an error, it simply means that the index was not found. If the index is currently being used, the drop operation will fail. In this case, you will need to wait until the index is no longer in use before attempting to drop it. If the user running the component does not have sufficient privileges to drop the index, the operation will fail. You will need to use an account with the appropriate privileges to drop the index. This typically includes the drop any index privilege. Langchain Community Vector stores Oracle's drop table purge. This step outlines the process of permanently removing an Oracle table and its associated data from the database, ensuring that the data is irrecoverable. It involves two key operations: dropping the table and then purging it from the recycle bin. Inputs. The name of the table to be deleted. This is a critical input, as it directly identifies the specific table that will be removed from the database. For instance, in a scenario where you have a table named customer details, the input value would be customer details. This input value must be a valid table name existing within the Oracle database. Outputs. This step does not directly return any output, as its primary function is to modify the state of the database by removing the specified table. Steps. This step involves executing an SQL command to drop the table, effectively removing it from the database schema. This action immediately removes the table structure and the data it contains, but the data remains in the recycle bin for potential recovery. This step involves purging the deleted table from the recycle bin, making the data removal permanent. This action is essential to ensure that the data is completely removed and cannot be recovered. Prerequisites. A valid connection to the Oracle database is required, allowing access to execute SQL commands and manage tables within the database. This connection is established using connection parameters like hostname, port, username, and password, ensuring secure and reliable communication with the database. For example, if you have an Oracle database hosted on a server DB server at port 1521, and your database user is admin with a password secret, you would need to provide these details for connection setup. The user executing the drop and purge operations must have sufficient privileges to perform these actions. The user requires the drop privilege to remove the table from the database. This privilege is usually granted to database administrators or specific roles with permission to manage database objects. Fine-tune parameters. This step does not have any specific tunable parameters, as its functionality is focused on performing a straightforward drop and purge operation. However, the overall execution time can be influenced by factors like the size of the table being dropped, the database server load, and network latency. Challenges and fixes. If the table being dropped doesn't exist in the database, the operation will fail. The challenge lies in ensuring that the table name provided is correct, and the database is properly connected to access the correct schema. The solution involves implementing error handling mechanisms to gracefully catch this scenario. For example, you can use SQL exists function to check if the table exists before attempting to drop it. If the user attempting the operation lacks the necessary privileges, it will result in an error. To address this, the user must be granted the drop privilege, either directly or through an assigned role, enabling them to perform the table removal operations. This can be achieved by contacting the database administrator or following the database security guidelines for privilege management. Langchain community vector stores Redis base check index exists. This component checks if a Redis index exists. The component verifies whether an index with the given name exists within the Redis database. Inputs. This input parameter is the name of the index that the component is designed to search for within the Redis database. It functions as an identifier for the specific index within the Redis instance. For example, an index might be named product descriptions to hold information about different products. Outputs. This output represents the result of the index existence check. It is a Boolean value, indicating whether the specified index was found within the Redis database. If the index exists, it will return true, otherwise, it will return false. Steps. This step involves establishing a connection to the Redis database. The component uses a Redis client library to connect to the specified Redis server. The connection details, such as the host name, port, and potential password, are provided as part of the configuration. This step checks if the index exists within the connected Redis database. It utilizes the Redis client library to query the database for the presence of the index with a specified name. The result of this query determines whether the index is present. Prerequisites. The component requires a Redis client library to interact with the Redis database. The client library provides functions for establishing a connection, sending commands, and receiving results. There are several popular Redis client libraries available in various programming languages. For example, the Redis library is widely used in Python. To establish a connection with the Redis database, the component requires details about the Redis server. This includes the host name or IP address of the Redis server. The port number that the Redis server is listening on. This is typically 6379. Password if the Redis server is password protected. The password is required for authentication. Fine-tune parameters. To fine-tune the component's behavior, you can adjust the Redis connection details. This includes the host name or IP address of the Redis server. This setting allows you to specify the location of the Redis server. For example, if you are using a cloud-based Redis service, you would provide the host name or IP address of the server in the cloud. The port number that the Redis server is listening on. This setting allows you to change the port if the Redis server is configured to use a different port. Password. The password used to authenticate with the Redis server. You can modify this setting to match the password of your Redis server, if it is password protected. Challenges and fixes. If the component encounters an error during the connection to the Redis database, it is likely due to an issue with the Redis connection details. This could be because the Redis server is not running. The hostname or IP address is incorrect. The port number is incorrect. The password is incorrect or not provided. To resolve these issues, ensure that the Redis server is running and that the hostname, port, and password are correct. You can also check the Redis server logs for any error messages that may provide more details. If the component cannot find the specified index in the Redis database, it indicates that the index might not exist. To resolve this issue, check the index name for any errors. Ensure that the name matches the index that you created in the Redis database. Summary of Langchain Community Vector Stores Oraclef's Drop Table Purge. This operation removes an existing table from an Oracle Cloud database. This is a permanent action, and the table's data will be lost. Inputs: the name of the table to be deleted. This is the identifier used by Oracle Cloud to locate the specific table within the database. Outputs: the operation's outcome, indicating whether the table was successfully deleted or if an error occurred. Steps: establish a secure connection to the Oracle Cloud database. This involves authentication using valid credentials and authorization to perform database operations. Execute the SQL command to drop the specified table. This command removes the table structure and all associated data from the database. Commit the changes made to the database, making the table deletion permanent. This step ensures that the database reflects the removal of the table. Prerequisites: valid Oracle Cloud credentials are required for authentication to access the database. This includes a valid Oracle Cloud username, which uniquely identifies the user attempting to connect to the database. A strong password associated with the username for secure authentication. Information about the specific Oracle Cloud database instance is necessary for establishing a connection. This includes the name of the Oracle Cloud instance, which identifies the specific database server within the Oracle Cloud environment. The endpoint or connection string, which provides the network address and port used to connect to the database instance. Fine-tune parameters. The specific table name is crucial for accurately identifying the table to be dropped. A typo or incorrect name will result in an error. Challenges and fixes. If the specified table does not exist in the database, the drop operation will fail. To resolve this, carefully verify the table name for any typos or inconsistencies with the actual table name in the database. The user attempting to drop the table might not have the necessary privileges to perform this operation. To resolve this, ensure that the user has the drop privilege, which grants permission to delete database objects like tables. This privilege may need to be granted by a database administrator. Langchain Community Vector Stores Quadrant Sync Call Fallback Summarization. This YAML file describes the Langchain Community Vector Stores Quadrant Sync Call Fallback summarization method, which uses a synchronous call with a fallback to an asynchronous call in case of failure. It details the inputs, outputs, steps, prerequisites, fine-tune parameters, and challenges with fixes for this method. Inputs. A Quadrant client object. This is an object that represents the connection to a Quadrant server. Quadrant is an open-source vector database. The object allows you to interact with the Quadrant server's features, such as adding documents, searching for similar documents, and managing your data. A list of documents to be added. This is a list of documents that you want to add to the vector database. Each document should be a dictionary containing the necessary information, such as the text content, metadata, and any other relevant fields for your specific use case. Outputs. A list of IDs of the documents added after adding the documents to the Quadrant server. You get a list of IDs for each document added to the database. These IDs serve as unique identifiers for each document in the database, allowing you to easily retrieve them later. Steps. Attempt to add documents synchronously using Qdrant client. This step involves trying to add documents to the Qdrant server using a synchronous call. A synchronous call means that the process waits for the operation to complete before continuing. This approach ensures that the document is added to the database before proceeding with further steps. If synchronous call fails, attempt to add documents asynchronously in case the synchronous call fails. For example, due to a network issue or a timeout. This method then attempts to add the documents asynchronously. An asynchronous call allows the process to continue without waiting for the operation to complete. This provides a more robust solution as it can handle potential delays or failures without blocking the entire process. Prerequisites: Qdrant client installed. For this method to work, you must install the Qdrant client library using pip. This library provides the necessary tools to connect to and interact with a Qdrant server. Pip install Qdrant client. This command will install the Qdrant client library. Qdrant server running. You need a running Qdrant server. A Qdrant server is a database server specifically designed for storing and retrieving vector data. It is essential for the method to function correctly. Fine-tune parameters. Sync timeout. Timeout for synchronous calls. This parameter sets a time limit for the synchronous call. If the call does not complete within this time limit, it will be considered a failure, and the method will switch to the asynchronous approach. For example, if you set the timeout to 5 seconds, and the synchronous call takes longer than 5 seconds, the method will automatically switch to asynchronous execution. Async timeout. Timeout for asynchronous calls. This parameter sets a time limit for the asynchronous call, similar to the synchronous timeout. If the asynchronous call takes longer than this specified timeout, it will be considered a failure. This parameter helps to prevent the method from waiting indefinitely for a response from the Qdrant server, especially if the asynchronous call is experiencing issues or delays. Challenges and fixes. Synchronous calls can be slow. One challenge associated with synchronous calls is that they can be slow, especially for large datasets or when the Qdrant server is under heavy load. Use a smaller sync timeout to address this challenge. You can use a smaller value for the sync timeout parameter. This reduces the amount of time the method waits for the synchronous call to complete, potentially reducing the overall execution time. Asynchronous calls may fail. Another challenge is that asynchronous calls may fail, especially if there are network issues or if the Qdrant server is unavailable. Retry asynchronous calls with a larger async timeout to handle potential failures in asynchronous calls. You can use a larger async timeout value. This gives the method more time to complete the asynchronous operation, potentially overcoming temporary network issues or server unavailability. Langchain Community Vector Stores Scan. Dependable Scan. Import. Import Dependable Scan, a library for efficient approximate nearest neighbor and search, to create a vector store for fast similarity search. Inputs: a pre-trained scan index file containing the learned embeddings and associated metadata. This index is often created using a training dataset to learn optimal similarity search parameters. Outputs: a dependable scan vector store instance, which is an object that provides methods for storing, retrieving, and searching vectors based on their similarity. This instance allows you to perform efficient searches for similar vectors based on a query vector. Steps: load the scan index file into memory. This step reads the pre-trained index data from the specified path and makes it available for use. Create a dependable scan vector store instance using the loaded scan index. This step initializes the vector store with the index data and configures its search parameters. Prerequisites: Ensure that the dependable scan library is installed. This library provides the necessary functionality for working with scan indexes and performing similarity searches. You can install it using pip install dependable scan. Fine-tune parameters. The path to the scan index file. This should be the location of the pre-trained index data on your system. The number of threads to use for similarity search. This parameter determines how many CPU cores will be used to perform parallel searches, which can significantly speed up the search process. Challenges and fixes. If the specified scan index path is incorrect, ensure the provided path is valid and that the index file exists. Double-check the file name and location. Verify that the provided path points to the correct location of the scan index file. Check for typos, case sensitivity, and ensure the file exists. If the index loading fails, it might be due to incompatibility between the installed scan library version and the index file. Check the scan library version and update it if necessary. Verify that the installed scan library version is compatible with the version used to create the index file. Older scan versions might not be able to load indexes created with newer versions. You might need to install a compatible version of the scan library. Langchain Community Vector Store's Redis filters check operator misuse. This tool is designed to analyze Langchain Community Vector Store code and its Redis filter configurations to detect and prevent operator misuse. It aims to ensure the correct and efficient usage of Redis filters within vector stores, ultimately improving the performance and reliability of data retrieval. Inputs. This input refers to the code of Langchain Community Vector Store, specifically the parts that interact with and utilize Redis filters. The code may include functions, classes, or modules that define and apply these filters for data retrieval and filtering within a vector store. Redis filter configurations represent the set of rules or parameters defined for filtering data in Redis. This input consists of the specific configurations used for filtering data within the vector store, such as filter types, conditions, and other relevant parameters. Outputs. The report generated by this tool will detail the potential misuse of operators found in the analyzed Langchain code and Redis filter configurations. It will highlight areas where operators are not being used correctly or efficiently. Code suggestions provided in this output aim to rectify any identified misuse of operators within the Langchain vector store code. The suggestions will offer revised code snippets or strategies for implementing operators in a more efficient and reliable manner. Steps. The initial step involves parsing the Redis filter configurations provided as input. This process analyzes and extracts the relevant information from the configurations, such as filter types, conditions, and other parameters. Analyzing Langchain code for filter usage involves examining how Redis filters are implemented within the code base. This step identifies the functions, classes, or modules responsible for defining and applying these filters. This step aims to identify any potential misuse of operators based on the analysis of filter configurations and their usage within the Langchain code. Misuse could include incorrect filter syntax, mismatched filter types, excessive complexity, or lack of validation. The report generated will summarize the findings of the analysis, outlining the detected instances of operator misuse. The report should provide clear and concise descriptions of each issue, explaining the cause and potential consequences. Based on the identified misuse, the tool provides code suggestions for fixing the issues. These suggestions offer revised code snippets or strategies for implementing filters in a way that avoids misuse and enhances the overall efficiency and reliability of the vector store. Prerequisites. A thorough understanding of Redis filters is crucial for effectively using and interpreting them. Within Langchain vector stores, this knowledge includes understanding how filters work, their various types, and their specific syntax for defining filtering conditions. Knowledge of Redis filter syntax includes understanding the various operators, arguments, and conditions used in defining Redis filter rules. This knowledge allows you to accurately interpret filter configurations and identify potential issues with syntax or logic. Examples of common Redis filter operators include an, OR, NOT, GT, LT, GE, LR, etc., each of which has its specific syntax and functionality. Experience with Langchain vector store implementations is essential to analyze the code and its interactions with Redis filters. This experience includes understanding how vector stores are constructed and the specific components involved in filtering data, particularly in conjunction with Redis. Familiarity with different vector store types and their capabilities is also beneficial. Familiarity with Langchain Application Programming Interface API is crucial for effectively analyzing and modifying the vector store code. Understanding the API allows you to interact with the vector store, access its functions, and modify its behavior as needed to address filter misuse or implement validation. This includes understanding how to define, apply, and manage filters using the Langchain API. Fine-tune parameters. The operator misuse detection threshold parameter controls the sensitivity of the tool in detecting potential misuse. A lower threshold indicates stricter detection, potentially flagging more minor issues. A higher threshold indicates a more relaxed detection, potentially missing some subtle misuse cases. This parameter can be adjusted based on the desired level of rigor in the analysis. The severity level for reporting misuse determines how serious the reported issues are considered. A high severity level indicates that the identified misuse has a significant impact on vector store's performance or reliability. A low severity level indicates that the issues are relatively minor and might not require immediate attention. This parameter helps prioritize issues based on their potential impact. Challenges and fixes. Incorrect filter usage can manifest as errors in the syntax, logic, or application of filter rules. This can result in unexpected filter behavior, leading to inaccurate data retrieval or inefficient filtering operations. Refactoring filter logic to match the correct syntax involves reviewing the filter definitions within the Langchain code and ensuring they adhere to the standard Redis filter syntax. This includes verifying operator usage, argument placement, and overall structure of filter expressions. For instance, if a filter uses a NOT operator incorrectly, it needs to be adjusted to the correct syntax. Mismatched filter types occur when the filters defined in the configuration do not align with the intended filtering operations performed by the vector store. This could lead to incorrect filtering, resulting in unexpected or inaccurate data retrieval. Ensuring filter types align with vector store operations involves checking that the types of filters defined in the configuration match the types of filters expected by the vector store code. For example, if the vector store code expects filters based on a specific data field, the configuration must also define filters for that field. Mismatches between the filter types used in the configuration and the vector store code can lead to unexpected filtering results. Unnecessary filter complexity arises when filters are overly intricate or contain redundant rules, potentially hindering performance. This can occur due to excessive use of operators, nested conditions, or overly specific filters. Simplifying filters for improved performance involves identifying and removing unnecessary complexity from the filter definitions. This can include streamlining conditions, eliminating redundant rules, and using efficient filter operators for the desired filtering logic. For example, a filter with multiple nested and conditions can potentially be simplified by combining those conditions into a single expression. Missing filter validation can lead to incorrect filter execution, resulting in unexpected data retrieval or system errors. This is especially important when the filters are user-defined or dynamic. Implementing filter validation before execution ensures that the filter definitions are valid and consistent with the vector store's requirements. This involves checking for correct syntax, data type consistency, and overall feasibility of the filter expressions. By implementing validation, you can prevent potential issues arising from invalid or malformed filter configurations. Langchain Community Vector Store's StarRox debug output provides a detailed breakdown of the debugging steps for the Langchain Community Vector Stores. StarRox integration inputs connection details for accessing the StarRox database. This includes information like the database hostname, port number, username, and password. Textual data that needs to be indexed. This could be anything from a collection of articles, product descriptions, or customer reviews. Outputs. Vector store index stored in the StarRox database. This index allows for efficient search and retrieval of relevant documents based on semantic similarity. Steps. Establish a connection to the StarRox cluster. This typically involves using a StarRox client library, which provides the necessary functions for interacting with the database. Create a table in StarRox to store the data. This table must have columns for the text data and the generated vector embeddings. Insert the text data into the StarRox table. The data should be formatted in a way that is compatible with the table schema. Generate vector embeddings for the text data. This process converts the text into numerical representations that capture its meaning. The choice of embedding model depends on the specific needs of the application. Insert the vector embeddings into the StarRox table. These embeddings are stored alongside the corresponding text data, allowing for fast and accurate semantic search. Prerequisites. Setup of a functional StarRox cluster. This includes installing and configuring StarRox on the desired infrastructure, ensuring that the cluster is accessible and properly running. Installation of the necessary StarRox client libraries for your programming language or environment. These libraries provide the functions needed to connect and interact with the StarRox database. Fine-tune parameters. The choice of embedding model to be used for generating vector representations. Different embedding models have varying strengths and weaknesses, and the best choice depends on factors like the size of the dataset, the desired accuracy, and the computational resources available. The dimensionality of the generated vectors. This refers to the number of dimensions in the vector representation of each text document. Higher dimensionality typically leads to more complex representations but can also increase computational requirements. Challenges and fixes. Encountering errors during the connection process to the StarRox cluster. Verify that the StarRox connection details are correct and that there are no network connectivity issues. Check firewall settings and ensure that the StarRox server is accessible from the client. Application. Facing errors while creating a table in StarRox. Double-check the table schema, ensuring that it is compatible with the requirements of the StarRox database. Verify the necessary permissions for creating the table and ensure that the user has sufficient privileges. Encountering errors during the insertion of data into the *rocks table. Confirm that the data format is consistent with the *rocks table schema and that the data types are correctly defined. Check for any data integrity issues or data validation errors. Encountering errors during the embedding generation process. Verify the embedding model configuration and ensure that the input data is formatted correctly. Check the model parameters and the input data format to ensure compatibility. Encountering errors during the insertion of embeddings into the *rocks table. Verify the *rocks table schema and ensure that the embedding data format is consistent with the table schema. Check for any data type mismatches or issues with the data structure. Langchain Community Vector Stores *rocks has mul sub-str summarization. This function checks if a given string contains multiple substrings. It iterates through a list of substrings, verifying if each substring is present within the provided string. This functionality is useful for tasks like searching for keywords in a text document or filtering data based on specific terms. Inputs. The input string that needs to be examined for the presence of multiple substrings. For instance, this could be a paragraph of text, a product description, or a news article. A list of substrings that the function will search for within the input string. This list could include keywords, phrases, or any combination of characters to be found in the input string. Outputs. A Boolean value indicating whether all of the substrings in the provided list are present within the input string. A true value signifies that all substrings were found, while a false value indicates that at least one substring was not present. Steps. The function will iterate through each substring in the provided list. This means it will process each substring one by one, performing a search within the input string. For each substring in the list, the function will check if it is present within the input string. This check is likely performed using a string comparison algorithm, which efficiently compares characters to determine if a substring exists within the larger string. Prerequisites. A *rocks database instance is required for this functionality. *rocks is an open-source distributed database known for its high performance and scalability. It allows for efficient data storage and retrieval, making it suitable for large-scale data processing. The *rocks database must contain a table that includes a string column. This column will store the input string that will be searched for the presence of multiple substrings. The table structure should be designed to optimize the search process, ensuring efficient access to the relevant string data. Fine-tune parameters. No fine-tuning parameters are available for this function. This indicates that the function is designed to operate effectively without the need for manual adjustments or configuration. Challenges and fixes. If the list of substrings is very large, the search process can become computationally intensive, potentially affecting performance. To address this challenge, the function can utilize optimized string search algorithms. These algorithms, such as the Boyer-Moore or Rabin-Karp algorithms, are designed to efficiently locate pattern substrings within a larger string, reducing the search time and improving performance, especially when dealing with a large number of substrings. Performance issues can arise if the database queries are not optimized. Slow query execution can significantly impact the overall execution time of the function. To optimize database query performance, it's crucial to create appropriate indexes on the string column in the *rocks table. Indexes allow the database to efficiently locate relevant data, reducing the time required to search for substrings. Additionally, Optimizing the query structure itself can significantly improve performance by minimizing unnecessary operations and selecting the most efficient execution path. Langchain Community Vector Stores *aux has mul sub str summary. This function checks if multiple substrings are present within a given string. It's a fundamental operation with applications in text processing, data analysis, and search functionalities. For instance, imagine a scenario where you are searching a database for documents containing specific keywords. This function would be instrumental in identifying those documents. Inputs. This input represents the string that will be searched for the presence of multiple substrings. It could be a sentence, a paragraph, or even a larger text document. For example, this string could be the quick brown fox jumps over the lazy dog. This input is a list of substrings that we are looking for within the string provided as the first input. Each substring represents a specific word or phrase we want to check the existence of in the given string. For example, this list could be quick, lazy, cat. Outputs. The output of this function is a Boolean value, either true or false. It indicates whether all substrings in the provided list are present in the given string. If all substrings are found within the string, the function returns true. Conversely, if even a single substring is not found, the function returns false. Steps. This step involves iterating through each substring in the list of substrings provided as input. The function goes through each substring one by one, systematically examining it against the given string. For each substring in the list, the function checks whether it is present within the given string. It uses a string search algorithm to efficiently determine if the substring is a part of the string. After checking all the substrings in the list, the function returns true if all the substrings were found within the string. If any substring is not present in the string, the function returns false. Prerequisites. This function requires a *aux table containing vector data to function properly. *aux is a distributed, column-oriented database designed for high-performance analytics. It provides a robust platform for storing and querying large datasets. In this context, the presence of vector data within the *aux table is essential for enabling efficient search operations. Vector data represents data points in a multi-dimensional space, allowing for faster search and similarity calculations. Challenges and fixes. A potential challenge arises when the function searches for substrings that are not present in a given string. This can lead to errors or unexpected behavior. To handle this, the function is designed to gracefully handle such situations. When a substring is not found, it does not generate an error but simply returns false, indicating that not all substrings were present. This ensures that the function operates smoothly even when encountering missing substrings. Performance issues can arise when dealing with large strings and extensive lists of substrings. The search operation might become computationally expensive, leading to delays in the execution of the function. To address this, the function employs optimized search algorithms. These algorithms are designed to efficiently scan through large strings and locate substrings. By minimizing the computational effort required for the search, these algorithms ensure that the function performs well even when handling large input datasets. Summary of Langchain Community Vector Stores TileDB Get Documents Array URI. This section describes the function that retrieves a document array URI from TileDB. Inputs. A uniform resource identifier URI pointing to a TileDB array. This URI is a string that identifies the specific location of the TileDB array data on a storage system. A unique identifier for the document. It is used to locate the desired document within the TileDB array. Outputs: the URI of the document array containing the requested document. It is a string that points to the location of the array on a storage system and allows for accessing and retrieving the data associated with the document. Steps: the function fetches the document array URI from TileDB using the provided TileDB array URI in pay. Document ID: it utilizes the TileDB library to access the data within the array and retrieve the URI of pay. Specific document array. Prerequisites: a TileDB array URI. This is the URI for the TileDB array, which holds the document data. For instance, TileDB my TileDB array. This URI identifies the location of the TileDB array on a storage system. A document ID, representing a unique identifier for the document. For example, 1234. It is used to locate the correct document within the TileDB array. Fine-tune parameters: none. This indicates that there are no additional parameters that can be configured or customized for this function. Challenges and fixes: the provided TileDB array URI could be incorrect or invalid. Verify the TileDB array URI by checking its correctness and availability in the TileDB system. This can involve ensuring the URI follows the correct format and that the specified TileDB array exists at the given location. The document ID might not be present in the TileDB array. This implies that the specified ID does not match any document within the array. Check the document ID against the available document IDs within the TileDB array. Confirm the correctness and accuracy of the document ID. Langchain Community Vector Stores TileDB Dependable TileDB Import. This document details a robust and dependable vector store built upon TileDB for use with the Langchain framework. Inputs: a collection of vector embeddings, each uniquely identified by a corresponding ID. These embeddings represent data points in a multi-dimensional space, enabling similarity searches and other vector-based operations. For example, a set of document embeddings and their respective document IDs could be used to perform semantic search. The URI Uniform Resource Identifier of the TileDB array that will store the embeddings. This URI can be a local file path or a remote URL. Along with the URI, you can optionally provide configuration parameters to fine-tune the TileDB array's behavior. These parameters could include specifying the desired storage format, compression techniques, and indexing strategies. Outputs: the result is a fully functional vector store powered by TileDB. This store provides an efficient and scalable mechanism for storing and retrieving embeddings, enabling various downstream applications like semantic search, recommendation systems, and anomaly detection. Steps: the first step involves importing the TileDB library, which provides the necessary tools for managing and querying TileDB arrays. You then establish a connection to the TileDB storage, whether it's on your local machine or a remote server. This ensures you can interact with the TileDB array and perform operations like writing and reading data. Create a TileDB array tailored to store your embeddings and associated IDs. The array schema defines the structure of your data, specifying dimensions like the embedding vector size, data types, and potential indexing strategies. For instance, you would define a multi-dimensional array with a dimension for the embedding vector and a separate dimension for the unique IDs. This step involves inserting your vector embeddings and their corresponding IDs into the TileDB array. This process populates the array with your data, making it available for search and retrieval operations. Efficient data organization is crucial for fast query performance. To search for similar embeddings, you define search functionality using TileDB queries. This step involves defining a query based on a specific embedding and specifying the distance metric like cosine similarity to measure similarity. The TileDB engine then efficiently retrieves the most similar embeddings from the array based on your query. Prerequisites: TileDB must be installed and configured on your system. This includes setting up any necessary environment variables and ensuring that your system has the required dependencies for TileDB to function correctly. TileDB can be installed via package managers or from the official website. The required Python packages are TileDB for interacting with TileDB arrays and Langchain for integrating the vector store with Langchain's powerful language models and tools. Fine-tune parameters. This parameter specifies the dimensionality of the embeddings you will be storing in the vector store. It defines the number of dimensions in the vector space that represents each embedding. This parameter indicates the specific type of embedding model used to generate the embeddings. Different embedding models produce vector representations with varying characteristics, which might influence the quality of similarity searches. Popular embedding models include sentence transformers, OpenAI's text embedding ADA002, and Google's Universal Sentence Encoder. Challenges and fixes. When dealing with vast datasets, the performance of loading, storing, and searching for embeddings within the TileDB array can become a bottleneck. To improve performance, carefully optimize the TileDB array's configuration. This could involve choosing an efficient storage layout, enabling compression algorithms to reduce storage space, and creating appropriate indexes to accelerate search queries. Indexes create shortcuts for quickly finding relevant data without scanning the entire array, leading to significant performance improvements. Robust error handling and data validation are essential for ensuring the reliability and integrity of the vector store. Implement error handling mechanisms to catch and manage potential errors during data loading, storage, and retrieval. Thorough data validation ensures that the embeddings and their associated IDs are correctly stored and formatted, maintaining the consistency of the vector store. This could involve verifying the dimensions of embeddings, checking for duplicate IDs, or using data type validation to ensure data integrity. Langchain Community, Vector Stores, TileDB.get Vector Index URI from Group. This function retrieves the uniform resource identifier URI of a TileDB vector index within a group. This function is used to access TileDB vector indexes efficiently within a group structure. Inputs. Name of the TileDB group that contains the vector index. This is a textual identifier used to organize and access TileDB data within a particular context. Name of the TileDB vector index. This is a textual identifier that uniquely identifies a specific vector index within a TileDB group. Outputs. URI of the TileDB vector index. This is a string that specifies the location and access information for the TileDB vector index. It provides a way to locate and interact with the index within the TileDB system. Steps. Retrieve the TileDB group URI based on the group name. This step involves querying the TileDB system to locate the URI associated with the specified group name. Construct the URI of the TileDB vector index by appending the vector index name to the group URI. This step involves combining the retrieved group URI with the vector index name, resulting in a complete URI that uniquely identifies the vector index within the TileDB system. Prerequisites. Installation of the TileDB library. TileDB is a data management library that provides efficient storage and access to multidimensional arrays. This prerequisite ensures that the necessary components for interacting with TileDB are available on the system. TileDB. Creation of a TileDB group. A TileDB group is a container for organizing and storing TileDB arrays. This prerequisite ensures that the specified group exists in the TileDB system and is accessible for retrieving the vector index. TileDB group. Fine-tune parameters. No fine-tuning parameters are available for this function. It operates directly based on the provided group and vector index names. Challenges and fixes. If the specified group or vector index is not found within the TileDB system, this indicates an error in the provided names or a potential inconsistency in the data organization. To resolve this, verify the group and vector index names for accuracy and ensure that they correspond to existing entities within the TileDB system. Check group and vector index names. TileDB connection issues can arise due to problems with the TileDB installation, configuration, or network connectivity. To troubleshoot this, verify that TileDB is correctly installed and configured on the system. Ensure that the necessary dependencies are met, and that the TileDB server is running and accessible. Verify TileDB installation and configuration. Langchain Community Vector Stores USearch Dependable USearch Import. A USearch vector store requires the USearch library to be installed and imported as a dependency. Inputs. The input data for the vector store. This is the raw data that will be converted into vector representations. Metadata associated with the data, such as the source, timestamp, or any other relevant information. Outputs. A USearch vector store that can be used for similarity search, retrieval, and other tasks. Steps. Install the USearch library. This can be done using package managers like pip. Import the USearch library into the Python code. Initialize the USearch vector store with the provided data and metadata. Prerequisites. Python is required for using USearch vector stores. A Python version of 3.6 or higher is recommended for compatibility with the USearch library and other Langchain components. The USearch library needs to be installed using pip before using the USearch vector store. Install USearch using the command pip install USearch in the terminal or command prompt. Fine-tune parameters. The dimensionality of the vector space, which defines the number of features used to represent each data point. The distance metric used to calculate the similarity between vectors. Common options include Euclidean distance, cosine similarity, or Manhattan distance. Challenges and fixes. Encountering errors while importing USearch can occur if the library is not installed correctly or if there are conflicts with other dependencies. Ensure that USearch is installed correctly using the appropriate command for your package manager. Verify that the installation was successful and that the library is present in your Python environment. Problems during vector store initialization can arise from missing dependencies, incorrect configuration settings, or incompatible data formats. Double-check that all necessary requirements are installed, including any specific packages or libraries required by the USearch vector store. Review the configuration parameters used to initialize the vector store, making sure they are correct and compatible with the data and your use case. Langchain Community Vector Stores TileDB Get Vector Index URI from Group Summary. This function retrieves the TileDB URI for a given vector index group. It is designed to work with the TileDB vector store, a storage and retrieval system for embedding data. Inputs. The name of the TileDB group containing the vector index. which is a unique identifier for the group. A TileDB context object, which provides access to the TileDB group that holds the vector index. Outputs. The TileDB URI, a unique address that identifies the location and structure of the vector index within the TileDB system. Steps. This function uses the provided group name to access the TileDB group within the TileDB context object. Then, it retrieves the URI for the vector index within the group using the TileDB application programming interface API. Prerequisites. A TileDB context object, which is an essential component for interacting with TileDB. It acts as a connection to the TileDB system and provides access to various TileDB features, including the ability to access and manage vector indices. This context must be properly configured with the specific TileDB group that houses the target vector index. The name of the TileDB group that holds the vector index. This name is used as a unique identifier to locate the group within the TileDB system. It is essential for the function to locate the specific vector index within the TileDB system. Fine-tune parameters. This function does not have any fine-tuning parameters, meaning it operates with fixed settings that cannot be adjusted. Challenges and fixes. If the TileDB group, which is a collection of vector indices, cannot be located within the system, the function raises an error, indicating that the provided group name is incorrect or the group does not exist. If the vector index cannot be found within the specified group, the function raises an error, implying that the vector index may not exist within the group or the provided group name is incorrect. Langchain Community Vector Stores utils maximal marginal relevance. The maximal marginal relevance technique is a method for selecting a subset of documents from a larger set that are most relevant to a given query while maximizing diversity and minimizing redundancy. This technique is particularly useful when dealing with large collections of documents and aiming to retrieve a concise and informative set of results that cover different aspects of the query. Inputs. Text query that specifies the information to retrieve. This query serves as the basis for finding relevant documents. For example, you could use a query like "What are the main causes of climate change?" A vector store that stores the documents and their embeddings. The vector store acts as a database containing the documents and their corresponding vector representations. The embeddings allow for efficient retrieval based on semantic similarity. Vector stores commonly used with maximal marginal relevance include FAISS and OpenEye embeddings. Outputs. A list of document IDs representing the most relevant and diverse documents retrieved. This list provides a ranked order of the documents that are most relevant to the query while ensuring a balanced representation of different viewpoints or perspectives. Steps. Calculate similarity scores between the query and all documents in the vector store. This step involves measuring how similar each document is to the query based on their vector representations. The similarity scores provide an initial ranking of relevance. Iteratively select documents that maximize the marginal relevance. This step involves selecting documents not only based on their similarity to the query but also considering how much additional information they contribute beyond the already selected documents. The goal is to select documents that provide diverse and valuable insights while minimizing redundancy. Prerequisites. A vector store with pre-computed embeddings for documents. This vector store should contain pre-calculated vector representations for each document, enabling efficient retrieval based on semantic similarity. Common vector stores used in this context include FAISS and OpenEye embeddings. These vector stores provide optimized algorithms for storing and searching large sets of vectors, making the retrieval process faster and more efficient. A well-defined text query. A well-defined text query is essential for ensuring that the retrieval process effectively captures the user's intent. It should be clear, concise, and specific, allowing the algorithm to accurately identify relevant documents. Fine-tune parameters. Number of documents to retrieve. This parameter determines the size of the document subset that will be returned. A larger value will result in a more comprehensive set of results, while a smaller value will prioritize retrieving a concise set of relevant documents. A parameter that controls the balance between relevance and diversity. This parameter allows you to adjust the importance of retrieving documents that are highly relevant to the query versus ensuring a diverse set of results. A higher value for lambda will prioritize diversity, while a lower value will focus on relevance. Challenges and fixes. Selecting appropriate lambda parameter. Choosing the appropriate lambda parameter is crucial for achieving the desired balance between relevance and diversity. Adjusting lambda based on the specific application is key. For example, in a news aggregation system, you might prioritize diversity to present different perspectives on a given event. However, in a medical question answering system, you might prioritize relevance to provide accurate and reliable information. Dealing with large document sets. When working with large document sets, efficiency becomes a major concern. Considering using efficient search algorithms and vector stores is important. For example, using FAISS for approximate nearest neighbor search or leveraging the optimized vector store. Functionalities provided by OpenAI can significantly improve performance and scalability. By employing efficient techniques, you can ensure that the retrieval process remains manageable even with large amounts of data. Langchain Community Vector Stores VDMS Client. VDMS is a vector database service that provides a simple and efficient way to store, query and manage vector data. It enables users to store and retrieve high-dimensional vectors, often used to represent text or image data, enabling similarity search functionalities. Inputs. Raw text data. For example, articles, product descriptions, or social media posts. Vector embeddings representing the text data. These embeddings are usually generated using pre-trained models like sentence transformers or OpenAI's embedding API. Outputs. Stored vector embeddings. These embeddings are persisted within the VDMS database. Similarity search results. These results return the closest matches to the query based on the chosen similarity metric and search radius. Steps. Connect to the VDMS server. Establish a connection to the VDMS service using the appropriate libraries and credentials. Upload embeddings. Upload the generated vector embeddings to the VDMS database for storage and retrieval. Perform similarity searches. Submit queries to the VDMS server using a specified vector embedding representing the query. Retrieve matching results. Retrieve the closest vector embeddings to the query based on the configured similarity metric and search radius. Prerequisites. VDMS server. This includes a running VDMS instance and a configured database. Application Programming Interface Credentials. This includes the VDMS server API key for accessing the server's services. Fine-tune parameters. Similarity metric. This refers to the metric used to calculate the distance between vectors. Common metrics include cosine similarity, Euclidean distance, and Manhattan distance. Search radius. This defines the maximum distance from the query vector to consider results. A larger search radius yields more results but potentially introduces more irrelevant entries, while a smaller radius returns fewer results with potentially higher precision. Challenges and fixes. Connection issues. This includes situations where the VDMS server is unreachable or network connectivity is disrupted. Verify network connectivity and check the status of the VDMS server to resolve these issues. Upload errors. This can arise from incorrect embedding formats or invalid application programming interface keys. Verify the embedding format and ensure that the API key is valid. Search performance. This can be affected by factors like embedding quality, the chosen similarity metric, and the search radius. Optimize embedding generation by fine-tuning the embedding model. Experiment with different similarity metrics, and adjust the search radius. Data scaling. This can become a challenge as the volume of data grows. Utilize VDMS sharding capabilities for horizontally scaling the database or explore distributed architectures to handle larger datasets. Langchain Community Vector Stores VDMS embedding 2 bytes summarized. This component converts an embedding to a byte string. An embedding is a vector of numbers that represents the meaning of a piece of text. This embedding can be used to find similar text or to perform other tasks. For example, you could use an embedding to find other documents that are similar to a given document. This embedding can be stored in a database and can be retrieved later for comparison. The conversion to bytes is necessary for storing and retrieving the embedding from the database. Inputs. Embedding is a vector of numbers that represents the meaning of a piece of text. It is the result of an embedding model, which is a machine learning model trained to map text to numbers. This embedding can be used to find similar text or to perform other tasks. For example, you could use an embedding to find other documents that are similar to a given document. You can use various embeddings such as sentence transformers or OpenAI embeddings. Outputs. Bytes are a sequence of 8-bit values that represent data. This byte string is the representation of the embedding, which can be stored and retrieved later. For example, you can store this byte string in a database and then retrieve it later for comparison. Steps. Converting embedding to bytes involves taking the embedding, which is a vector of numbers, and converting it to a sequence of 8-bit values. This is done by using a standard encoding, such as the UTF-8 encoding. The resulting byte string can then be stored and retrieved later. Prerequisites. The VDMS Vector Database Management System library needs to be installed. VDMS is a library that is used to manage vector databases, which are databases that store and retrieve vectors. You can install VDMS by running pip install VDMS in your terminal. Fine-tune parameters. There are no fine-tuning parameters for this component. This is because the component is simply converting an embedding to bytes, and there is no need to adjust the conversion process. Challenges and fixes. Challenge 1. The embedding may be invalid. For example, the embedding may not be a valid vector or it may be too large to be converted to bytes. Fixes to challenge 1. You can check if the embedding is valid by checking its type and size. You can also check if the embedding is too large to be converted to bytes. If the embedding is too large, you can try to reduce its size or use a different encoding. Challenge 2. The resulting bytes may not be valid. For example, the bytes may not be in the correct format or they may be corrupted. Fixes to challenge 2. You can check if the bytes are valid by checking their format and size. You can also check if the bytes are corrupted by comparing them to the original embedding. If the bytes are corrupted, You can try to regenerate them or use a different encoding. Langchain experimental agents agent toolkits pandas base create pandas data frame agent. This agent toolkit provides functionality to create a pandas data frame from given data. It uses the pandas library, a powerful tool for data manipulation and analysis in Python. Inputs: the input data to create the data frame. This data can be in various formats like lists, dictionaries, or even external data sources. For example, you could provide a list of customer names and their corresponding purchase amounts. The column names for the data frame. These names should match the structure of the provided data and represent the different categories or attributes of your data. For instance, if you are working with customer data, the column names could be customer name, purchase amount, and purchase date. Outputs: a pandas data frame, which is a two-dimensional data structure. It represents data in a tabular format with rows and columns, making it easy to analyze and manipulate data. Steps: the agent first retrieves the input data from the user or from a specified source. This data is then processed and prepared for creating the data frame. The agent converts the input data into a list format. This ensures that the data is structured in a way that is compatible with pandas data frames. The agent uses the converted list data and the provided column names to create the pandas data frame. This step combines the data and the structure to build the final data frame. Prerequisites: the pandas library needs to be installed on your system. You can install it using the command pip install pandas. Pandas provides the core functionalities for creating and working with data frames in Python. The Langchain library needs to be installed as well. Langchain provides the framework for integrating different components and tools like pandas into a larger workflow for data processing and analysis. Fine-tune parameters. This agent toolkit does not require any fine-tuning parameters. It is designed to be a general-purpose tool for creating data frames from various data sources. Challenges and fixes. One challenge might be that the data type of the input data does not match the expected type for the data frame. For instance, you might have strings representing numbers, which need to be converted to numeric data types. To address this, you can use type conversion functions provided by pandas to convert the data to the appropriate types. This ensures that the data is stored and manipulated correctly within the data frame. Another challenge could be providing incorrect column names that do not match the structure or the number of columns in the input data. To resolve this, you need to carefully check the provided column names and ensure they align with the data. If the names are incorrect, you need to provide the correct names to create a valid data frame. Langchain experimental agents agent toolkits.csv base create CSV agent. A detailed description of the function create CSV agent, which is part of the Langchain experimental agents agent toolkits.csv base module. This function facilitates the creation of a CSV agent, a specialized agent designed to interact with and process data from comma-separated value CSV files. Inputs: the path to the CSV file that the agent will interact with. This path could be a local file system path or a remote path accessible through a network protocol, like HTTP or FTP. The prompt, or set of instructions, that will be given to the CSV agent. This prompt guides the agent's behavior and specifies what actions it should take on the CSV data. It could be a question, a request to perform a specific task, or a combination of both. Outputs: the CSV agent itself. This is a specialized agent capable of understanding and processing data from CSV files. It can be used to perform a variety of tasks like extracting data, analyzing trends, or generating reports based on the CSV file's contents. Steps. The first step in creating a CSV agent is reading the CSV file. This involves accessing the specified file path and loading the CSV data into memory. This step might require dealing with different CSV file formats and handling any potential errors that could occur during the file reading process. Once the CSV data has been loaded, the next step is to create the CSV agent. This involves configuring the agent with the necessary tools and settings, such as the prompt and any relevant parameters. The agent might also be initialized with a specific language model, depending on the intended use case. Prerequisites. The CSV tool. A specialized tool from the Langchain experimental agents, agent toolkits.csv, base module, is necessary for interacting with the CSV data. This tool provides the functionality to read, write, and manipulate CSV files. A language model LM from the Langchain LLMS module is required. The LM is used to understand and process the prompt and generate appropriate responses based on CSV data. The LM could be a powerful language model like GPT-3 or a simpler model tailored for specific tasks. Fine-tune parameters. The CSV tool parameter is used to specify the specific tool that will be used for interacting with the CSV file. This allows users to choose a tool that best suits their needs, whether it's a basic tool for simple CSV manipulation or a more advanced tool for handling complex CSV structures. Challenges and fixes. One potential challenge is that the CSV file might be too large to fit in memory. This could happen if the CSV file contains millions of rows or has a very complex structure. The solution to this challenge is to use a tool that can handle large CSV files. These tools might employ techniques like chunking or streaming to process the CSV data in smaller segments, avoiding memory overload. Another challenge is that the CSV file might not be properly formatted. This could involve missing or inconsistent data, incorrect delimiters, or other formatting issues. The solution is to use a tool that can handle poorly formatted CSV files. These tools might be able to identify and correct errors in the CSV data, or provide mechanisms for handling missing or inconsistent data, allowing for more robust and reliable processing. Langchain experimental agents agent toolkits XOrbits base create XOrbits agent. A function that creates an XOrbits agent. XOrbits is a tool for building agents that can interact with the world, such as a simple chatbot that can answer questions about the weather. This agent can be customized with different tools and large language models. Inputs. A large language model LLM is a type of artificial intelligence model that is trained on a massive amount of text data and can generate text, translate languages, write different kinds of creative content, and answer your questions in an informative way. For example, GPT-3 is a well-known LLM that can be used to create chatbots. A list of tools that the XOrbits agent will use to interact with the world. These tools could include web search, API access, or other functions that allow the agent to get information or perform actions. For example, if the agent needs to get the current weather, the tool could be a weather API. Outputs. The function returns an XOrbits agent. This agent can then be used to interact with the world and complete tasks. Steps. First, the function will instantiate an XOrbits agent. This is the basic structure of the agent that will be used to interact with the world. Next, the function will set the agent to use the provided tools. This will allow the agent to access the tools and use them to complete tasks. Finally, the function will set the agent to use the provided LLM. This will allow the agent to generate text and use its knowledge to complete tasks. Prerequisites: install the necessary packages to use the XOrbits agent. This can be done using the pip package manager. Pip install Langchain XOrbits. Import the necessary classes from the Langchain experimental agents and Langchain experimental agents agent toolkits modules to create and use the XOrbits agent. From Langchain experimental agents import toolkits. From Langchain experimental agents agent toolkits import XOrbits. Fine-tune parameters. The agent's max iterations parameter can be set to limit the number of iterations for each run of the agent. This parameter helps to prevent the agent from getting stuck in an infinite loop and helps to control the complexity of the agent's tasks. The agent's max execution time parameter can be set to limit the time of each run of the agent. This parameter helps to prevent the agent from running for too long and helps to control the resources used by the agent. Challenges and fixes. The agent may not be able to complete the task due to insufficient context. The LLM may not have enough information about the task or the world to complete the task. Increase the context window of the LLM. This will allow the LLM to access more information and may help to improve the agent's performance. The agent may be stuck in an infinite loop. This can happen if the agent is unable to complete a task or if the agent is given a task that is too complex. Increase the max iterations or max execution time parameters. This will allow the agent to run for longer and may help to prevent the agent from getting stuck in an infinite loop. Summary of Langchain experimental agents agent toolkits XOrbits base create XOrbits agent. This function creates an XOrbits agent, a powerful tool for building intelligent agents that can interact with the real world using specified tools and configuration. Inputs: a list of tools that the agent can utilize, such as an application programming interface API to access external data or a search engine to retrieve relevant information. A dictionary containing configuration settings for the agent, including parameters like the agent's name, its memory capacity, and the specific instructions that guide its behavior. Outputs: an instance of an XOrbits agent that is ready to be used for tasks like question answering, information retrieval, or even creative writing. Steps: the function first initializes an XOrbits agent instance using the provided tools and configuration. It then configures the agent's policy for how it uses these tools, such as which tools to use for different situations and in what order to utilize them. Prerequisites: the Langchain experimental package must be installed in the environment where this function is used. This package can be installed using the pip package manager with the following command: pip install Langchain experimental. The XOrbits server needs to be running for the agent to function correctly. You can start the XOrbits server using the command xorbits server start. Fine-tune parameters. Tool names: a list of the names of tools that will be available to the agent. These names must correspond to the actual tools defined in the agent's environment. For example, you might have a tool named Search that performs web searches and another named Calculator for basic calculations. Configure a dictionary containing various configuration settings that influence the agent's behavior. This could include parameters like the maximum number of steps the agent can take in performing a task, or the specific instructions that guide the agent in its decision-making process. Challenges and fixes. If the Zorbot server is not running, the agent will not be able to connect to it and will fail to function. You can resolve this by starting the Zorbot server using the command xorbot server start. If the tool names or configuration settings are incorrect or invalid, the agent might not work as expected. To fix this, carefully verify the tool names and configuration settings against the Zorbot's documentation. Ensure that the tool names are correct, that they match the actual tools defined in the agent's environment, and that the configuration settings are within the expected ranges and formats. Langchain Experimental Agents, Agent Toolkits, Python, Base. Create Python Agent Summary. None. This function creates a Python agent that uses Langchain tools to execute Python code. This means the agent can leverage external tools and libraries to interact with the world, making it more versatile and powerful than a simple text-based agent. The function to be executed by the agent, which is the core piece of code that the agent will try to execute. This function defines the specific task that the agent is meant to accomplish. The tools that the agent can use are external utilities that provide the agent with capabilities beyond basic Python code execution. These could include tools like making API requests, interacting with databases, or accessing file systems. Langchain provides a library of tools that can be readily integrated with the agent. The language model to use is the underlying AI component that powers the agent. This model is responsible for understanding the user's input, generating code, and interacting with the tools. Popular options include OpenAI's GPT models. The agent type specifies the specific type of agent that will be created. Different agent types have different strengths and weaknesses, such as a conversational agent designed for dialogue-based interactions, or a tool using agent designed for task-oriented execution. The verbose flag controls how much information the agent outputs during its operation. Setting this to true will provide more detailed logging, which can be useful for debugging or understanding the agent's reasoning process. The max iterations is a limit on the number of attempts the agent will make to execute the function. This prevents the agent from running indefinitely in cases where it might get stuck in a loop. The max execution time is a limit on the amount of time the agent is allowed to spend executing the function. This prevents the agent from consuming excessive resources or taking too long to complete a task. The starting memory is a data structure that the agent starts with to keep track of its state and context. This can be used to store intermediate results, user input, or other relevant information that can help the agent complete its tasks more effectively. The callbacks are functions that are executed at specific points during the agent's operation. These can be used for logging, monitoring, or controlling the agent's behavior. The agent executor is the component that manages the execution of the agent. It handles the interaction with the language model, the tools, and the execution of the provided function. The agent executor quarks are additional parameters that can be passed to the agent executor to customize its behavior. A Python agent that can execute Python code, equipped with the tools and capabilities defined in the input parameters. This agent is a self-contained entity that can be used to perform a variety of tasks based on the provided function and tools. The function that the user wants the agent to execute is passed to the agent. This function might be provided as code, or as a natural language description that the language model will then translate into code. The tools that the agent can use are passed to the agent. This allows the agent to access information, perform actions, or manipulate data using external resources. The language model to use is passed to the agent. This is the core AI component that will be responsible for the agent's reasoning, planning, and code generation. The agent type is passed to the agent. This determines the specific type of agent that will be created and how it will interact with the world. The verbose flag is passed to the agent, which controls how much information is output during the agent's operation. This can be useful for debugging or understanding the agent's internal reasoning. The max iterations is passed to the agent, which sets a limit on the number of attempts the agent will make to execute the function. This helps prevent the agent from getting stuck in an infinite loop. The max execution time is passed to the agent, which sets a limit on the amount of time the agent is allowed to spend executing the function. This helps prevent the agent from consuming excessive resources or taking too long to complete a task. The starting memory is passed to the agent, which is a data structure that the agent uses to keep track of its state and context. This can be used to store intermediate results, user input, or other relevant information that can help the agent complete its tasks more effectively. The callbacks are passed to the agent, which are functions that are executed at specific points during the agent's operation. These can be used for logging, monitoring, or controlling the agent's behavior. The agent executor is passed to the agent, which is the component that manages the execution of the agent. It handles the interaction with the language model, the tools, and the execution of the provided function. The agent executor quarks are passed to the agent, which are additional parameters that can be passed to the agent executor to customize its behavior. Python 3.7 or higher is required for the Langchain library to function correctly. Install Langchain using the pip package manager. Bash pip install Langchain. A language model is needed to power the agent's reasoning and code generation capabilities. Popular options include OpenAI's GPT models, which can be accessed through their Application Programming Interface API. To use OpenAI's GPT models, you will need an API key, which can be obtained by signing up for an OpenAI account. Tools to be used by the agent are necessary for the agent to interact with the world beyond simple Python code execution. Langchain provides a library of tools that can be readily integrated with the agent. Or you can create your own custom tools to suit your specific needs. The function to be executed by the agent can be adjusted to change the specific task that the agent is meant to accomplish. This could involve modifying the logic of the function or changing the inputs and outputs that it uses. The tools that the agent can use can be customized to fit the requirements of the specific task. This could involve adding new tools, removing existing tools, or changing the way that the tools are used by the agent. The language model to use can be switched to a different model with different capabilities or performance characteristics. This could involve using a different model from the same provider, or exploring models from other providers. The agent type can be changed to create an agent with different strengths and weaknesses. For example, you could choose a conversational agent for dialogue-based interactions or a tool using agent for task-oriented execution. The verbose flag can be set to true or false to control how much information the agent outputs during its operation. This can be useful for debugging or understanding the agent's internal reasoning. The max iterations can be adjusted to set a limit on the number of attempts the agent will make to execute the function. This helps prevent the agent from getting stuck in an infinite loop. The max execution time can be adjusted to set a limit on the amount of time the agent is allowed to spend executing the function. This helps prevent the agent from consuming excessive resources or taking too long to complete a task. The starting memory can be customized to provide the agent with different initial information or context. This could involve adding specific data, changing the structure of the memory, or using different types of memory. The callbacks can be modified to customize the behavior of the agent during its execution. This could involve adding new callbacks, removing existing callbacks, or changing the logic of the callbacks. The agent executor can be changed to use a different execution strategy. This could involve using a different underlying library or implementing a custom executor. The agent executor quarks can be adjusted to fine-tune the behavior of the agent executor. This could involve changing parameters that control the interaction with the language model, the tools, or the execution of the provided function. The agent may not be able to execute the function correctly due to errors in the code, mismatches between the function and the tools, or limitations in the language model's understanding of the function. To resolve these issues, carefully check the function code and ensure that it is correctly written and compatible with the tools that the agent is using. Also, make sure that the language model is capable of understanding the function and generating appropriate code to execute it. The agent may not be able to use the tools correctly due to errors in the tool definitions, misunderstandings about how to use the tools, or limitations in the language model's ability to reason about the tools. To address these issues, carefully check the tools and their documentation to ensure that they are correctly defined and understood by the agent. Also, make sure that the language model is capable of reasoning about the tools and using them appropriately. The agent may not be able to use the language model correctly due to misunderstandings about the model's capabilities, limitations in the model's ability to understand the user's intentions, or errors in the way the model is being used. To address these issues, carefully check the language model documentation and understand its capabilities and limitations. Also, make sure that the user's input is clear and unambiguous, and that the model is being used in a way that is consistent with its intended purpose. The agent may not be able to handle errors correctly due to missing or inadequate error handling mechanisms, misunderstandings about the potential errors that might occur, or limitations in the language model's ability to reason about errors. To address these issues, carefully check the error handling code and ensure that it is comprehensive and robust. Also, make sure that the language model is capable of understanding the potential errors that might occur and generating appropriate code to handle them. Summary of Langchain Experimental Agents Agent Toolkit CSV Base Create CSV Agent. This agent is a Langchain tool that can be used to create a CSV agent. A CSV agent can be used to access and analyze data from a comma-separated values CSV file. Inputs. Path to the CSV file. This is the location on your computer where the CSV file is stored. For example, it might be a path like C users John documents my data.csv or home John documents my data.csv. Outputs. This tool creates a CSV agent, which is a tool that can be used to perform various operations on a CSV file. These operations can include extracting data from the file, filtering data based on specific criteria, and performing calculations on the data. Steps. Read the CSV file into memory using the appropriate libraries. This involves parsing the file contents and understanding the data structure within it. often with the help of libraries like pandas. Create a CSV agent using the Langchain framework. This involves configuring the agent to utilize the CSV data you've loaded. This may involve defining how the agent can interact with the data, what questions it can answer, and what actions it can perform. Prerequisites. The Langchain library needs to be installed. Langchain is a framework for building powerful language models and agents. To install Langchain, use the following command in your terminal: pip install Langchain. The pandas library needs to be installed. Pandas is a powerful Python library for data analysis and manipulation. To install pandas, use the following command in your terminal: pip install pandas. Fine-tune parameters. The CSV path parameter specifies the path to the CSV file you want to use. For example, this might be C users John documents my data.csv. The delimiter parameter specifies the character that separates the values in the CSV file. The most common delimiter is a comma, but other delimiters are possible, like a semicolon or a tab T. Challenges and fixes. If the CSV file is not found, make sure that the path specified in the CSV path parameter is correct. This includes verifying the file name and location. If the CSV file is not readable, check the file format. Make sure the file is a valid CSV file and not corrupted. You can also try opening the file in a text editor to inspect its contents and see if there are any issues. If the delimiter is not specified, the agent might not be able to properly interpret the data in the CSV file. You can specify the delimiter using the delimiter parameter. For example, if the CSV file uses a semicolon as a delimiter, you would specify delimiter in your agent configuration. Langchain Experimental Autonomous Agents. Langchain Experimental Autonomous Agents is a framework for constructing artificial intelligence (AI) agents that can independently finish tasks by utilizing tools and language models. These agents are designed to operate without direct human intervention, leveraging their knowledge and capabilities to accomplish given objectives. Inputs. A natural language description of the task that the AI agent is expected to complete. This input serves as the initial instruction for the agent, outlining the goal and desired outcome. Optional context or additional information related to the task. This can include relevant background information, constraints, or any specific details that could aid the agent in understanding the task and achieving its objective. Outputs. The completed task, often presented as a specific output or an action taken by the agent. This output represents the result of the agent's efforts to fulfill the task description, showcasing the outcome of its autonomous actions. Optional log of the agent's reasoning and actions. This detailed log provides insights into the agent's internal thought processes and decision-making during task execution. It outlines the steps taken, the rationale behind each step, and any challenges encountered along the way, offering transparency and understanding of the agent's behavior. Steps. Agent receives task input. The agent begins its task by receiving the initial input, which provides the instructions and context for its actions. Agent parses input and identifies tools or information needed. The agent analyzes the received task input, identifying any relevant tools or information sources required to complete the task effectively. This step involves understanding the task's requirements and matching them to available resources. Agent interacts with tools or information sources. Based on the identified tools and information sources, the agent interacts with them to gather the necessary data or execute the required actions. This step involves engaging with external resources, such as application programming interfaces (APIs), databases, or online services, to retrieve relevant information or complete specific operations. Agent generates output based on gathered information. After gathering the necessary information and completing the required interactions with tools, the agent synthesizes its findings and generates the final output for the task. This involves processing the acquired information, drawing conclusions, and producing the desired outcome according to the task description. Agent logs its reasoning and actions. Throughout the entire process, the agent keeps a log of its reasoning and actions. This log documents the agent's thought process, including the steps taken, the reasoning behind each step, and any encountered challenges or decisions made. This log provides valuable insights into the agent's behavior and facilitates debugging or understanding its decision-making process. Prerequisites: knowledge of Langchain, including tools and language models. A fundamental understanding of Langchain, a framework for building applications powered by language models, is essential. This includes familiarity with the available tools and language models within the Langchain ecosystem, allowing for informed selection and utilization of these resources by the AI agent. Basic understanding of AI agent concepts. A basic understanding of AI agent concepts is crucial for comprehending the functionalities and limitations of autonomous agents. This involves familiarity with key concepts like goal-oriented behavior, environment interaction, and decision-making processes, enabling effective design and evaluation of AI agents. Fine-tune parameters. Agent's memory and reasoning abilities. This parameter refers to the agent's capacity to retain and recall information over time, influencing its ability to learn from past experiences and apply acquired knowledge to new situations. It also encompasses the agent's ability to reason logically and draw conclusions based on available information, impacting its decision-making process. Agent's tool selection and usage strategies. This parameter involves the agent's ability to select and effectively utilize the appropriate tools for a given task. It encompasses the agent's understanding of the capabilities and limitations of different tools, allowing it to make informed decisions regarding tool selection and application. Challenges and fixes. Agent getting stuck in infinite loops or failing to converge on a solution. This challenge arises when the agent's actions repeatedly lead to the same state without reaching a desired outcome. A potential fix involves implementing timeout mechanisms, which limit the agent's execution time for a specific task. Introducing task completion criteria provides clear goals for the agent to achieve, guiding it toward a successful conclusion. Agent choosing incorrect tools or making inefficient decisions. This challenge occurs when the agent selects inappropriate tools or takes actions that are not optimal for the task at hand. Addressing this challenge requires refining the agent's tool selection strategies, incorporating better reasoning capabilities to evaluate tool efficacy, and leveraging more comprehensive training data to improve its decision-making. Agent not being able to handle unforeseen situations. This challenge arises when the agent encounters unexpected situations or events that were not explicitly included in its training data. Designing robust error handling mechanisms allows the agent to gracefully handle unexpected situations, preventing task failure. Training the agent on a wider range of scenarios, including diverse and unexpected situations, equips it with greater adaptability and resilience in handling unforeseen circumstances. Summary of Langchain Experimental Autonomous Agents AutoGPT Output Parser Base AutoGPT Output Parser This parser is designed to interpret the output generated by AutoGPT, a powerful tool that leverages language models to automate tasks. AutoGPT utilizes a combination of natural language processing and code execution to perform actions. In the real world, the output from AutoGPT, which typically includes both textual descriptions and code snippets, is processed by the base AutoGPT output parser to extract meaningful information and determine next steps in the automation process. Inputs. Tool code: the code generated by AutoGPT, which represents an action or task to be performed. Intermediate steps: a record of the actions already executed by AutoGPT, providing context for the current step. Outputs. Final output: the final result of the executed code or action, presented in a user-friendly format. Next action: the action to be taken next based on the analysis of the current output and previous actions. Steps. Parse output: the parser analyzes the raw output from AutoGPT, identifying relevant information such as code snippets, textual descriptions, and potential errors. Extract tool code: the code generated by AutoGPT is extracted and analyzed to determine the type of action being requested. Determine next action based on the extracted code and the context provided by the intermediate steps. The parser determines the next appropriate action. Prerequisites. Tool code format: the code generated by AutoGPT must adhere to a specific format, typically Python code. This format ensures that the parser can accurately interpret and execute the code. Action format: the actions performed by AutoGPT are predefined and consistent. This standardization allows for the parser to anticipate and interpret the actions based on code generated. Fine-tune parameters. Tool code regex: a regular expression used to identify and extract the code from the output. The tool code regex can be fine-tuned to match the specific code format used by AutoGPT. Action regex: a regular expression used to identify and extract the actions from the output. The action regex can be fine-tuned to match the specific action format used by AutoGPT. Challenges and fixes. Unrecognized tool code: if the parser encounters code that doesn't match the expected format or is not recognized, it will default to a predefined action. This ensures that the automation process continues even when encountering unexpected code. Invalid action: if the parser encounters an action that is not valid or cannot be executed, it will reevaluate the code and potentially attempt to generate a new action based on the context. This allows for error handling and recovery during the automation process. A summary of AutoGPT agent in Langchain. NaN. A comprehensive description of the AutoGPT agent within Langchain. A powerful tool for building autonomous agents. AutoGPT is an experimental agent designed to leverage the capabilities of AutoGPT for complex and goal-oriented tasks. Inputs. A clear and well-defined goal or objective that the agent should accomplish. For instance, write a blog post about the benefits of using Langchain for building autonomous agents. Optional contextual information or starting point for the agent. This could include existing research on the topic, relevant articles, or specific requirements for the goal. Outputs. A series of actions and outputs generated by the agent towards the specified goal. These outputs could include code, text, or other relevant information. For example, the agent could generate a Python script to scrape relevant data, draft a blog post outline, and then create the final blog post content. An evaluation of the agent's performance and effectiveness in achieving the goal. This evaluation could include metrics such as the accuracy of the generated content, the time taken to complete the task, and the overall success in meeting the stated goal. Steps. The agent receives the goal and any initial context. This could be provided through user input or by reading from a file. The agent breaks down the goal into smaller, manageable tasks. This helps to simplify the problem and make it easier for the agent to solve. For example, the agent could break down the blog post writing task into subtasks like data gathering, research, outlining, writing, and editing. The agent uses a language model to generate code, text, or other outputs relevant to the current task. This could involve using the language model to generate Python code for data scraping, write the blog post outline, or even create the final blog post content. The agent executes the generated code or instructions. This step ensures that the agent can take concrete actions and move towards achieving the goal. For example, the agent could execute the Python script to scrape data, then use the scraped data to generate the blog post outline. The agent evaluates the results of each task and iteratively refines its approach. This feedback loop allows the agent to learn from its mistakes and improve its performance over time. For example, if the generated blog post outline is not satisfactory, the agent could reevaluate its approach, adjust the language model's parameters, or seek additional context to improve the output. The agent repeats steps 35 until the goal is achieved or a termination condition is met. The agent could continue to generate code, execute tasks, and refine its approach until it has successfully written the blog post or until it reaches a predefined time limit or other termination criteria. Prerequisites. Access to a powerful language model, e.g., GPT-4. This requires an API key from OpenAI for accessing their GPT models or a suitable model from Hugging Face. A suitable programming environment for code execution. This could be Python, Node, JS, or another suitable language with access to libraries and frameworks for interacting with language models and executing code. Fine-tune parameters. Agent's memory size and persistence. This refers to the amount of information the agent can store and retain over time. A larger memory allows the agent to remember more context and improve its reasoning abilities. Level of creativity and risk-taking in code generation. This parameter allows the user to control how creative and experimental the agent's code generation is. A higher level of creativity could lead to more innovative solutions, while a lower level emphasizes more conventional and reliable approaches. Constraints and safety guidelines for code execution. This parameter allows the user to define limitations and safeguards for the agent's code execution. This could include restrictions on accessing sensitive data, limits on the amount of resources the agent can consume, or specific safety checks to prevent the execution of harmful or malicious code. Challenges and fixes. Agent may get stuck in a loop or fail to progress towards the goal. This could happen if the goal is poorly defined, the agent lacks sufficient context, or the agent encounters unforeseen challenges. To address this, the user could reevaluate the goal, provide more specific instructions, or introduce external feedback mechanisms to guide the agent's progress. Agent may generate incorrect or unsafe code. This could occur if the language model is not adequately trained, the agent has limited context, or it lacks robust code verification steps. To mitigate this, the user could implement code verification steps, provide clear safety guidelines, and use a robust code execution environment that includes security checks and safeguards. agent may encounter limitations in its knowledge or abilities. This could be due to the limitations of the language model, the availability of external data sources, or the lack of specialized tools and APIs. To address these challenges, the user could provide access to external data sources, integrate specialized tools and APIs, and allow for human intervention when necessary to augment the agent's capabilities. AutoGPT Action Summarization. An action that AutoGPT can perform. This action is used by the output parser to transform the output of a large language model (LLM) into a format that AutoGPT can understand and carry out. Inputs. The output of an LLM or another tool, which is processed into an AutoGPT action. For instance, if an LLM suggests opening a website or running a command, this output would need to be passed into a format that AutoGPT can utilize. Outputs. An AutoGPT action object, which can be executed by the AutoGPT agent. This object essentially represents a specific action, like opening a web page or sending an email. Steps. Analyze the output from the LLM using the output parser. This step involves breaking down the LLM's output into meaningful components that can be understood by AutoGPT. Transform the parsed output into an AutoGPT action object. This entails converting the LLM's output into a structured format that AutoGPT can readily execute. Perform the action defined by the AutoGPT action object. This is the final step where AutoGPT takes the action based on the parsed and structured information from the LLM. Prerequisites. The LLM output must be in a format that can be converted into an AutoGPT action. This means the output must be structured in a way that can be easily understood and parsed. A suitable output parser must be available for the specific LLM used. The parser must be able to interpret the LLM's output format and translate it into a format that AutoGPT can utilize. Fine-tune parameters. Action type specifies the type of action that needs to be performed. Examples include opening a URL, sending an email, or executing a command. Action input. The input data required for the action. This could be a URL for a web page, the recipient's email address, or the command to be executed. Challenges and fixes. Challenge. The LLM output might not be formatted in a way that can be directly converted into an AutoGPT action. For example, the LLM's output may be unstructured or use a different format than what AutoGPT expects. Fixes. Adjust the output parser to handle the LLM's specific output format. This might involve modifying the parser's logic or rules to recognize and process the unique format of the LLM's output. Challenge. The generated AutoGPT action object may not be executed correctly. For instance, there could be errors in the action's definition, such as incorrect URLs, email addresses, or command syntax. Fixes. Debug the AutoGPT action object and the execution logic. This may involve inspecting the object's properties, verifying the accuracy of the input data, and testing the execution process to identify and fix any errors. Summary of Langchain Experimental Autonomous Agents. Baby Aji, Baby Aji, Baby Aji. This text describes the Baby Aji agent, an experimental autonomous agent. The agent is designed to complete tasks in a goal-driven manner, meaning it focuses on accomplishing a specific objective. Baby Aji utilizes various tools and steps to achieve this, aiming to be an effective task completion agent. Inputs. The Baby Aji agent takes a goal or task as input. This task could be anything from writing a poem to summarizing a research paper. The agent then uses its capabilities to break down the task into smaller, manageable subtasks and ultimately complete the goal. Outputs. The output of the Baby Aji agent is a set of completed tasks. Each task is a subtask that contributes to achieving the original goal. By completing these subtasks, the agent effectively fulfills the overall goal or task. Steps. The first step of the Baby Aji agent involves breaking down the given task into smaller, more manageable subtasks. This step ensures that the agent can tackle the task in a systematic and organized way, improving its chances of success. Once the task is broken down into subtasks, the Baby Aji agent prioritizes these subtasks. This prioritization helps ensure that the agent focuses on the most important tasks first, leading to an efficient and focused approach to task completion. After prioritizing subtasks, the Baby Aji agent executes each subtask using a tool. The tools used can range from APIs, which allow the agent to interact with other applications and services, to scripts, which are small programs that automate specific actions. The final step in the Baby Aji agent process is reviewing the results of each completed subtask and iterating based on the outcome. The agent can learn from its experiences and adjust its approach to improve its efficiency and effectiveness. Prerequisites. The Baby Aji agent relies on a large language model (LLM) as a core component. LLMs are advanced AI systems trained on vast amounts of text data, enabling them to understand and generate human-like text. Popular examples of LLMs used with Baby Aji include OpenAI's GPT-3 and Google's Palm 2. In addition to an LLM, the Baby Aji agent requires a set of tools to execute tasks. These tools could include application programming interfaces (APIs) that allow the agent to interact with other services, or scripts, which are small programs designed to automate specific actions. The tools chosen depend on the nature of the tasks the agent is designed to complete. Fine-tune parameters. The choice of the LLM used in the Baby Aji agent is a critical parameter that influences its performance and capabilities. Different LLMs have different strengths and weaknesses, and selecting the right one is essential for optimizing the agent's ability to perform the desired tasks. The tools used by the Baby Aji agent are also an essential factor determining its performance. Choosing the right tools ensures that the agent has the necessary resources to complete its assigned tasks effectively. Challenges and fixes. One of the challenges faced by the Baby Aji agent is difficulty in understanding the initial goal. This can be addressed by redefining the goal in simpler terms, breaking it down into smaller, more easily understood parts. Another challenge is limited memory of past tasks. This can be overcome by using a memory to store previous tasks. This memory can help the agent learn from past experiences and make more informed decisions in the future. The Baby Aji agent may struggle to handle complex tasks. This can be mitigated by breaking down complex tasks into simpler ones. This approach allows the agent to tackle each component separately, ultimately making the complex task more manageable. The Baby Aji agent may lack context awareness. Providing more context to the LLM can help address this challenge. By providing additional information about the task and its surroundings, the agent can better understand the context and perform tasks more effectively. Langchain Experimental Autonomous Agents Baby Aji Task Creation Chain. Task creation chain is a crucial component of Baby Aji, an innovative framework that empowers the creation of autonomous agents. It plays a pivotal role in driving the agent's continuous progress by generating new tasks based on The outcomes of previously completed tasks. Imagine a virtual assistant tasked with researching a new product for a business. The task creation chain would analyze the results of the initial research tasks, such as gathering market data or competitor analysis, and then generate follow-up tasks like compare features of similar products or identify potential target audience groups. This iterative process allows the agent to adapt and refine its actions based on evolving information. Inputs. The task creation chain requires two main inputs to function effectively. The first is a dictionary that encapsulates the results of the preceding task. This dictionary acts as a repository of information gleaned from the previous action, providing context for the creation of new tasks. For instance, if the previous task was search for articles about artificial intelligence, the results dictionary might contain the URLs of relevant articles, their titles, and key excerpts. The second input is a string representing the overarching goal of the agent. This goal acts as a guiding principle for the task creation chain, ensuring that the generated tasks are aligned with the agent's intended outcome. In the example of a virtual assistant tasked with researching a new product, the goal string might be conduct a comprehensive market analysis for a new smartphone. Outputs. The output of the task creation chain is a list of new tasks that are ready to be added to the agent's task queue. These tasks represent the next steps in the agent's journey towards achieving its goal. In the context of the smartphone research example, the output might include tasks like analyze customer reviews of existing smartphones or identify potential marketing channels for the new product. Steps. At the heart of the task creation chain lies a language model that possesses the ability to comprehend and generate natural language text. This model first analyzes the results of the previous task, extracting relevant information that will inform the creation of new tasks. In the case of a virtual assistant analyzing articles about artificial intelligence, the language model might identify key themes, emerging trends, and specific technologies discussed in the articles. Once the language model has identified relevant information, it then leverages another language model to generate new tasks based on the extracted data and the agent's overarching goal. This process involves the model understanding the agent's goal and decomposing it into a series of smaller, more manageable tasks. In our example, the model might generate tasks like compare the features of different AI models or investigate the potential impact of AI on various industries. Prerequisites. A fundamental prerequisite for the task creation chain is the presence of a language model that can effectively understand and generate natural language text. This model serves as the foundation for the chain's ability to extract information and generate new tasks. The language model should be capable of performing tasks such as text summarization, sentiment analysis, and question answering. Fine-tune parameters. The task creation chain can be fine-tuned to generate tasks that are more specific or more general, depending on the needs of the agent and the complexity of the goal. This fine-tuning process involves adjusting the parameters of the language models used within the chain to influence the types of tasks that are generated. For example, if the agent is working on a complex project with many subtasks, the task creation chain can be fine-tuned to generate more specific tasks, breaking down the overarching goal into smaller, more manageable steps. Conversely, if the agent is working on a simpler task, the task creation chain can be fine-tuned to generate more general tasks, providing a high-level overview of the next steps. Challenges and fixes. Challenge 1. One potential challenge associated with the task creation chain is that it may generate tasks that are not directly relevant to the agent's current goal. This can happen when the language model misinterprets the extracted information or fails to fully understand the agent's overarching goal. For instance, in the smartphone research example, the task creation chain might generate a task like research the history of mobile phones, even though this task might not be directly relevant to the current goal of analyzing the market for a new smartphone. Fixes to challenge 1. This challenge can be addressed by fine-tuning the task creation chain to ensure that it generates more relevant tasks. This fine-tuning process involves providing the language model with more context and training data that is specifically tailored to the agent's goal. For example, the model could be trained on a dataset of tasks that are relevant to the smartphone industry, which would help it to better understand the context and generate more relevant tasks. Challenge 2. Another challenge is that the task creation chain may generate tasks that are either too complex or too simple for the agent to complete. This can occur if the language model does not accurately assess the agent's capabilities or the complexity of the task. For instance, the task creation chain might generate a task like conduct a comprehensive analysis of global smartphone markets for an agent that is only capable of performing simple web searches. Fixes to challenge 2. This challenge can be addressed by fine-tuning the task creation chain to generate tasks that are appropriate for the agent's capabilities. This fine-tuning process involves providing the language model with information about the agent's capabilities and limitations. For example, the model could be trained on a dataset of tasks that the agent has successfully completed in the past, which would help it to understand the agent's abilities and generate tasks that are within its reach. Elaborated description of task creation chain in Baby AGI framework. The task execution chain is a component within the Baby AGI framework, responsible for carrying out specific tasks based on given instructions. It acts as the operational core, translating instructions into actionable steps and executing them using appropriate tools and chains. Inputs. Task instructions. This refers to the detailed instructions provided to the task execution chain. These instructions define the specific task to be executed, outlining the desired outcome and any relevant context. For instance, an instruction might be research the top 5 restaurants in New York City and summarize their reviews, clearly outlining the goal and scope of the task. Intermediate steps. This represents the list of steps already completed during the execution of a larger task. This allows the task execution chain to maintain context and efficiently manage a sequence of steps within a broader workflow. For example, if a task involves gathering information from multiple sources, this list would track which sources have already been consulted, preventing redundancy. Outputs. Output. This is the result of executing the task. It can be any form of data, depending on the nature of the task. For example, it could be a summary of restaurant reviews, a list of contacts, or a generated creative text. Intermediate steps. This is the updated list of completed steps, reflecting the progress made during the task execution. It ensures that the chain keeps track of its progress and avoids repeating steps. Continuing the restaurant review example. This output would include the updated list of sources consulted, reflecting the completion of the current step. Steps. 1. Pass the task instructions into a list of individual steps. This involves breaking down the overall task into a series of smaller, more manageable steps. For example, the task research the top 5 restaurants in New York City and summarize their reviews could be broken down into steps such as identify top 5 restaurants in New York City, gather reviews for each restaurant, and summarize the gathered reviews. 2. Identify the current step that needs to be executed. This involves determining which step in the list of past steps should be executed next. The task execution chain uses the list of intermediate steps to determine which step is yet to be completed and requires execution. 3. Execute the current step using the appropriate tool or chain once the current step is identified. The task execution chain selects and utilizes the appropriate tool or chain to carry out the step. This could involve using a search engine to gather information, an API to interact with external services, or a language model to generate content. 4. Update the list of completed steps after executing the current step. The task execution chain updates the list of completed steps, marking the just executed step as complete. This ensures the chain maintains a record of its progress, enabling it to move efficiently through subsequent steps. 5. Return the output of the task execution and the updated list of steps finally. The task execution chain returns the output of the executed step, providing the results of the task, along with the updated list of completed steps. This allows the chain to communicate its progress and output to higher-level processes or agents. Prerequisites. Langchain. Langchain is a powerful Python library specifically designed for working with language models (LMs). It provides a framework for building applications that utilize LMs, offering functionalities for data access, model interaction, and chain creation. For example, using Langchain, you could build a system that uses a language model to analyze documents, extract information, and generate summaries. Task instructions. For the task execution chain to function effectively, clear and concise task instructions are crucial. These instructions guide the chain, defining the specific task to be executed, its desired outcome, and any relevant context. For instance, an instruction could be write a short story about a robot who falls in love with a human, clearly outlining the task and its desired outcome. Fine-tune parameters. Tools. This parameter defines the list of tools that the task execution chain can utilize during task execution. Tools could include search engines like Google Search for gathering information, APIs for accessing external data, or even custom-built tools for specific functionalities. Having a diverse set of tools allows the task execution chain to handle a wider range of tasks efficiently. Chains. This parameter specifies the list of chains that the task execution chain can utilize during task execution. Chains, in the context of Langchain, are a sequence of components designed to execute a specific task. For example, a chain could involve retrieving information from a database, processing it with a language model, and then formatting the output for presentation. Having a variety of chains allows the task execution chain to adapt to different task requirements and leverage predefined workflows for specific operations. Challenges and fixes. Challenge 1. The task instructions may be ambiguous or incomplete. Ambiguity and incompleteness in task instructions can hinder the task execution chain's ability to correctly understand and execute the task. For instance, a task instruction like write a story without further context or specifications leaves room for interpretation and can lead to undesired results. Fixes to challenge 1. To address this challenge, it's essential to provide clear, concise, and unambiguous task instructions. The instructions should explicitly define the task, desired outcome, and any relevant context. For example, instead of write a story, A clearer instruction could be write a short story about a robot who falls in love with a human. Set in a futuristic city. This eliminates ambiguity and provides the necessary context for the task execution chain to correctly understand and execute the task. Challenge 2. The tools or chains may not be able to execute the task properly. A task execution chain relies on tools and chains to carry out specific steps. However, these tools and chains may not always be perfectly equipped to handle all task requirements. For instance, a tool designed for simple text generation might struggle with complex tasks involving data analysis or logical reasoning. Fixes to challenge 2. To mitigate this challenge, it's crucial to select tools and chains that are appropriate for the specific task at hand. This involves carefully considering the task requirements and choosing tools and chains that have the capabilities to execute the task effectively. If no existing tool or chain is suitable, developing custom tools or chains tailored to the task-specific needs can provide the necessary functionality. Langchain experimental, autonomous agents, Baby AGI, task prioritization chain. A chain that prioritizes tasks based on their importance and urgency. The importance and urgency are determined by an underlying language model, which assigns weights to each task based on the specified criteria. For instance, a task requiring immediate completion might be assigned a high urgency weight, while a task with significant impact on long-term goals could receive a high importance weight. This chain is particularly useful when dealing with a large number of tasks, as it allows for the efficient allocation of resources and attention. Inputs: a list of tasks that need to be prioritized. Each task is represented as a string, which can be a description of the task, a title, or a brief summary of the task's objective. For example, a list of tasks for a project manager could include draft a project proposal, schedule a team meeting, and finalize budget allocation. Outputs: a prioritized list of tasks, sorted based on their importance and urgency. The chain outputs a list of strings, where each string represents a task. The tasks are ordered in descending order of priority, with the most important and urgent tasks appearing at the top of the list. This prioritization helps the user focus on the most crucial tasks first, ensuring efficient task completion and improved productivity. Steps: the chain uses a language model to assess the importance and urgency of each task. The language model analyzes the text description of each task and assigns scores for its importance and urgency. These scores are determined by the model's understanding of the task's context, its impact on the overall goals, and its time sensitivity. This process involves extracting key information from the task descriptions and utilizing the model's knowledge of language and task management principles to determine the relative importance and urgency of each task. The chain ranks the tasks based on their importance and urgency. The ranking algorithm typically assigns a weighted score to each task, considering both the importance score and urgency score. The weights can be adjusted based on the specific requirements of the user and the context of the tasks. For example, in a critical situation, the urgency weight might be increased, giving priority to tasks with immediate deadlines. The tasks are then sorted in descending order based on their weighted scores, resulting in a prioritized list of tasks. This prioritization process ensures that the most important and urgent tasks are tackled first, maximizing efficiency and productivity. Prerequisites: a list of tasks to be prioritized. This is the input to the chain, and it's essential for the chain to function. The tasks can be provided in any format that allows for clear identification and description. Fine-tune parameters. Importance weight. This parameter determines the relative weight assigned to the importance score of each task. A higher importance weight indicates that the importance of the task plays a greater role in determining its priority. For instance, a higher importance weight might be used in scenarios where strategic goals and long-term impact are paramount. Urgency weight. This parameter controls the weight assigned to the urgency score of each task. A higher urgency weight signifies that the task's deadline and time sensitivity are more influential in determining its priority. This parameter might be increased in situations where immediate action is required or time constraints are critical. Challenges and fixes. The language model may not be able to accurately assess the importance and urgency of all tasks. For instance, the model might struggle with subjective tasks where the importance and urgency are based on individual perspectives or complex, nuanced information. To address this challenge, the language model can be fine-tuned on a dataset of tasks and their corresponding importance and urgency. This dataset can be manually curated or generated using a combination of expert input and crowdsourcing techniques. By training the model on a diverse set of task examples, the model can learn to better understand the context and nuances associated with different task types, improving its ability to accurately assess importance and urgency. The ranking algorithm may not be optimal. The ranking algorithm is a critical component of the task prioritization chain, as it determines the final ordering of tasks based on their assigned weights. However, different ranking algorithms have different strengths and weaknesses, and the optimal algorithm may vary depending on the specific context and requirements. To overcome this challenge, different ranking algorithms can be experimented with to identify the most suitable option for a particular task set. This process might involve comparing the performance of different algorithms on benchmark datasets, or testing them on real-world task sets to evaluate their effectiveness in different scenarios. Experimentation with various algorithms can help optimize the prioritization process and ensure that the most relevant tasks are prioritized effectively. Langchain experimental autonomous agents Hugging GPT response generation chain. This YAML file describes the Langchain experimental autonomous agents Hugging GPT response generation chain, which is a chain that uses Hugging GPT as the response generator. It takes in a prompt and generates a response using Hugging GPT. Inputs. A textual input to be processed by the Hugging GPT instance to generate the response. For example, a question, a statement, or a request. Outputs. The text generated by the Hugging GPT instance in response to the prompt. For example, an answer to the question, a response to the statement, or a fulfillment of the request. Steps. Creates a Hugging GPT instance. Hugging GPT is a large language model (LLM) that is designed to be used for dialogue applications. The instance will be used to process the prompt and generate the response. Passes the prompt to the Hugging GPT instance. The prompt is the input text that the Hugging GPT instance will use to generate the response. Generates the response. The Hugging GPT instance processes the prompt and generates the response. The response is the output text that is returned by the Hugging GPT instance. Prerequisites. Hugging GPT is a large language model that is designed to be used for dialogue applications. It is trained on a massive dataset of text and code, and can be used to generate text, translate languages, write different kinds of creative content, and answer your questions in an informative way. For example, If you ask Hugging GPT what is the capital of France, it will respond Paris. Langchain is a framework for building and deploying LLM applications. Langchain provides a set of tools and libraries that make it easy to integrate LLMs into your applications. For example, you can use Langchain to build a chatbot that uses Hugging GPT to generate responses to user queries. Fine-tune parameters. The name of the language model to be used for response generation. For example, GPT 3.5 Turbo. The temperature parameter controls the randomness of the generated text. A higher temperature value will result in more creative and unpredictable responses, while a lower temperature value will result in more predictable and consistent responses. For example, if you set the temperature to 0.5, the responses will be more consistent with the prompt, while if you set the temperature to 1.0, the responses will be more creative and unpredictable. The top K parameter controls the number of most likely tokens to consider when generating a response. A higher top K value will result in more diverse and creative responses, while a lower top K value will result in more predictable and consistent responses. For example, if you set the top K to 10, the responses will be more diverse, while if you set the top K to 1, the responses will be more predictable. The top P parameter controls the probability of sampling tokens from the distribution of possible tokens. A higher top P value will result in more diverse and creative responses, while a lower top P value will result in more predictable and consistent responses. For example, if you set the top P to 0.9, the responses will be more diverse, while if you set the top P to 0.1, the responses will be more predictable. The maximum length of the generated response in tokens. For example, if you set the max length to 100, the generated response will be no longer than 100 tokens. Challenges and fixes. Hugging GPT may not be available. Install Hugging GPT using the appropriate package manager for your operating system. For example, if you are using pip, you can install Hugging GPT by running the following command: pip install Hugging GPT. Hugging GPT may not be able to generate a response. Ensure that the prompt is well-formed and contains the necessary information for Hugging GPT to generate a response. For example, if you are asking a question, make sure that the question is grammatically correct and complete. If you are asking for a specific piece of information, make sure that the prompt provides enough context for Hugging GPT to understand what you are looking for. Summary of Langchain Experimental Autonomous Agents Hugging GPT Response Generator. Response generation chain generates text from a Hugging Face model. This chain utilizes a pre-trained model from the Hugging Face library to produce text based on the provided input. The model can be any transformer-based language model, allowing for a wide range of text generation capabilities. Inputs. Input text to the model. This is the text that the model will use as context for generating new text. It could be a prompt, a question, or any other piece of text. For example, you could provide the model with a sentence like "The quick brown fox jumps over the lazy dog." The model to use. This refers to the specific pre-trained language model from Hugging Face that will be employed for text generation. Some popular examples include GPT-3, BERT, and Roberta. These models have been trained on vast amounts of text data, enabling them to generate coherent and relevant text based on the provided input. Outputs. The generated text. This is the output produced by the Hugging Face model based on the input text and the selected model. The generated text will be a continuation or expansion of the input text, reflecting the model's understanding and capabilities. Steps. Initialize the Hugging Face model. This step involves loading the pre-trained language model from Hugging Face. It is essentially setting up the model and preparing it for text generation. This process includes loading the model's weights and parameters, which contain the knowledge learned during training. Call the model on the input text. This is where the actual text generation occurs. The input text is fed to the model, and the model generates new text based on its learned knowledge and the input's context. The output of this step is the generated text. Prerequisites. Hugging Face model. This refers to a pre-trained language model available on the Hugging Face platform. These models are developed and trained by researchers and developers, making them readily accessible for various text-based tasks. Examples of popular Hugging Face models include GPT-3, BERT, and Roberta, which excel in different aspects of language understanding and generation. Example values for Prerequisite 1: GPT-3, BERT, Roberta. GPT-3, BERT, and Roberta are prominent examples of pre-trained language models available on Hugging Face. GPT-3 Generative Pre-trained Transformer 3 is known for its impressive text generation abilities, while BERT bidirectional encoder representations from transformers excels in language understanding, tasks like question answering and sentiment analysis. Roberta, a robustly optimized BERT pre-training approach, is a variant of BERT that has been fine-tuned to achieve even better performance. These models are versatile and widely used in natural language processing (NLP) applications, enabling tasks like text summarization, machine translation, and chatbot development. Fine-tune parameters. Temperature. This parameter influences the creativity and randomness of the generated text. A higher temperature value encourages the model to explore more diverse and unexpected outputs, while a lower value results in more predictable and coherent text. Top K. This parameter controls the number of possible outputs considered by the model during text generation. A higher top K value allows the model to explore a wider range of options, leading to more diverse outputs. A lower value restricts the model's choices, resulting in more predictable and focused text generation. Challenges and fixes. Model may not be available. This challenge occurs when the specific Hugging Face model required for text generation is unavailable or inaccessible. This could be due to network connectivity issues, model maintenance, or other factors. Fixes to challenge 1. Check if the model is available on the Hugging Face Hub. The Hugging Face Hub is the central repository for pre-trained language models and datasets. By checking the availability of the model on the hub, users can verify if the model is accessible and ready for use. If the model is not found on the hub, it might indicate that the model is not publicly available or has been removed. Model may not be able to generate text. This challenge arises when the chosen Hugging Face model is not specifically designed for text generation. While some models excel at understanding and analyzing text, others are primarily focused on tasks like sentiment analysis or question answering. Fixes to challenge 2. Ensure that the model is a text generation model. To overcome this challenge, it's crucial to select a model that is explicitly designed for text generation. This can be determined by checking the model's documentation on the Hugging Face Hub or consulting with online resources. Models like GPT-3 and GPT-2 are specifically designed for text generation and are suitable for generating creative and coherent text. Example values for Prerequisite 2: GPT-3, GPT-2, GPT-3 and GPT-2 are popular examples of pre-trained language models that are specifically designed for text generation. GPT-3, in particular, is known for its impressive abilities to generate human-like text, write different kinds of creative content, and answer your questions in an informative way. GPT-2 is a slightly older version of GPT-3 but still demonstrates strong text generation capabilities. Both models are valuable tools for various text-based applications, including content creation, chatbot development, and language translation. Summary of Langchain Experimental Autonomous Agents Baby AGI Task Execution Chain. This is a comprehensive description of the task execution chain, which is a component within the Langchain framework designed for executing tasks in an autonomous manner. Inputs. This is a description of the input to the task execution chain, which is a task to be completed. An example of such a task could be generate a summary of the latest advancements in the field of artificial intelligence. Outputs. This is a description of the output of the task execution chain, which is a result. The result will be the culmination of the steps that the task execution chain executes. Steps. This is a description of the first step involved in the task execution chain, identifying the task to be completed. The task could be something like writing a blog post on a given topic or summarizing a news article. This is a description of the second step involved in the task execution chain, breaking down the task into smaller steps. These smaller steps are meant to be simpler and more manageable. As an example, a blog post might be broken down into smaller steps such as research, outlining, writing, editing, and publishing. This is a description of the third step involved in the task execution chain, executing each step using appropriate tools. This involves leveraging various tools available to the agent, such as a search engine for research, a text generator for writing, or a code execution tool for data processing. This is a description of the fourth step involved in the task execution chain, combining the results of each step to produce the final output. This step ensures that the individual results of each step are integrated effectively to form a complete outcome. Prerequisites. This is a description of the prerequisite involved in the task execution chain, a task to be completed. This is the core input to the task execution chain and serves as the starting point for the entire execution process. For example, a user might ask the agent to write a blog post about the latest advancements in language models, which would be considered the task to be completed. This is a description of the prerequisite involved in the task execution chain, access to tools that can be used to complete the task. These tools are crucial for the task execution chain to successfully execute each step of the task. They could range from simple tools like Google search for information retrieval to more specialized tools like text generators for creative content or code execution tools for data analysis. For example, an agent might require access to Google search for research, a text generator for creating content, and a code execution tool for processing data. Fine-tune parameters. This is a description of the fine-tune parameter tools, which represents a list of tools that can be utilized to complete the task. These tools could include search engines for information retrieval, text generators for content creation, code execution tools for data processing, and many others. The agent utilizes these tools to perform the necessary tasks to reach the final outcome. This is a description of the fine-tune parameter verbose, which is a parameter that controls the level of detail in the output of the task execution chain. When the verbose parameter is set to true, The agent will print out the steps it takes as it completes the task. This can be helpful for debugging and understanding the agent's decision-making process. Challenges and fixes. This is a description of the challenge and fix unable to find a tool to complete a step. This challenge arises when the task execution chain encounters a step that cannot be fulfilled by the available tools. To overcome this challenge, the agent would try to utilize the most related tool available, even if it might not be a perfect fit. This allows the agent to continue executing the task even with limited tools. This is a description of the challenge and fix tool fails to complete the step. This challenge occurs when the agent encounters a step where the selected tool is unable to produce the expected result. The fix for this challenge is to try a different tool. This approach allows the agent to explore alternative options and improve the likelihood of successfully completing the step. This is a description of the challenge and fix tools are not available. This challenge arises when the agent lacks the necessary tools to perform certain steps. To address this, relevant tools need to be added to the agent's configuration. This ensures that the agent has access to the required resources for successful task execution. Langchain Experimental Autonomous Agents Hugging GPT Task Executor. A description of the Hugging GPT Task Executor and its purpose. The Hugging GPT Task Executor is an experimental autonomous agent designed for completing tasks by leveraging a variety of language models. Inputs: a human-readable, natural language description of the task to be completed by the Hugging GPT Task Executor. For example, a user might ask the task executor to summarize the main points of the article at this URL. A list of relevant files, URLs, or other data inputs required for the task executor to successfully complete the task. These inputs could include text documents, images, audio recordings, or even code. Outputs: the final output of the task execution, returned to the user in a format determined by the nature of the task. For instance, a summary task might yield a concise bullet point list, while a code generation task could produce functional code. A log detailing the steps taken by the task executor to execute the task. This log can be useful for debugging or understanding the reasoning process behind the task executor's decisions. The log typically includes information such as the chosen language models, their inputs, outputs, and any relevant error messages. Steps: the task executor receives a natural language task description from the user, outlining what they want to achieve. The task executor breaks down the complex task into a sequence of smaller, more manageable subtasks. This helps to ensure that the task is completed in a systematic and efficient manner. For example, a summarize an article task might be broken down into subtasks like extract key sentences, identify important concepts, and generate a concise summary. The task executor identifies the most suitable language model from a collection of models for each subtask. The task executor might select a model specialized in summarizing text for the extract key sentences subtask, and a different model for generating concise summaries for the final subtask. This ensures that the task executor utilizes the most appropriate tool for each part of the task. The task executor executes the subtasks using the chosen language models, feeding them the relevant inputs and receiving their outputs. For example, the task executor would feed the article text to the chosen extract key sentences model and use the model's output to inform the generator concise summary model. The task executor combines the results of the subtasks to produce the final output for the original complex task. This could involve merging the results of multiple subtasks, applying further processing to refine the output, or simply presenting the results in a structured format. Prerequisites: the Langchain and Hugging Face libraries must be installed to use the Hugging GPT task executor. This can be accomplished by running the following command in a suitable terminal environment. Pip install Langchain transformers. Access to the Hugging Face hub is required to utilize the task executor. The hub is a platform that hosts a vast collection of pre-trained language models. Access can be granted through an API token or an access key to a specific Hugging Face model. Fine-tune parameters. A key parameter for tuning the performance of the task executor is the model selection strategy. This strategy determines how the task executor chooses the most suitable language model for each subtask. Different strategies might consider factors such as model accuracy, performance, cost, or the specific task requirements. Another critical parameter is the subtask decomposition algorithm, which dictates how the task executor breaks down the complex task into manageable subtasks. This algorithm should be carefully designed to ensure that the subtasks are logically connected, provide a clear path to the final goal, and are suitable for execution by available language models. Challenges and fixes. A major challenge for the task executor is ensuring that the correct language model is chosen for each subtask. If the wrong model is selected, it might lead to incorrect or suboptimal results. To address this, the model selection strategy can be modified to incorporate more factors or use a more sophisticated approach. The decomposition of the task into subtasks should be carefully designed. Errors in task decomposition can lead to inconsistent or incomplete results. Adjusting the subtask decomposition algorithm, possibly incorporating more domain-specific knowledge or using a more robust decomposition strategy, can mitigate this challenge. Language models, despite their sophistication, are not infallible. They can encounter errors during execution, resulting in failure to complete subtasks. To handle this, the task executor can implement mechanisms to gracefully manage these errors, such as retrying the subtask, using a different model, or providing the user with a relevant error message. Combining the results of multiple subtasks into a cohesive final output can be a complex task. The task executor may need to perform additional processing or analysis to integrate the results effectively. To address this, the task executor can implement robust result aggregation strategies that consider the nature of pay, subtasks, the expected output format, and any potential inconsistencies or redundancies. A crucial aspect of task execution is context awareness. Without sufficient context, the task executor may make incorrect decisions or produce inaccurate outputs. To improve context awareness, the task description can be augmented with relevant background information, or the task executor can be designed to access and utilize external information sources. Unclear task specifications can lead to misunderstandings and incorrect execution. Providing more precise task instructions, including clear objectives, constraints, and expected output format, can help avoid ambiguity and ensure that the task executor accurately understands the user's intentions. Limited access to external information can hinder the task executor's ability to complete certain tasks. To address this, external information sources, such as knowledge bases, databases, or search engines, can be integrated into the task executor's infrastructure, allowing it to access and utilize a broader range of knowledge. Security is a vital concern for any system that interacts with sensitive data or executes tasks on behalf of users. To mitigate security risks, the task executor can implement appropriate security measures, such as access control mechanisms, data encryption, and regular security audits. These measures can help to ensure the safety and integrity of the system and protect users from unauthorized access or data breaches. Langchain Experimental Autonomous Agents Hugging GPT Task Planner Base Planner Summary. A base planner that uses a Hugging GPT model to generate a plan. The Hugging GPT model, a large language model LLM with access to various application programming interfaces (APIs), can be used for various tasks, including planning. This planner utilizes the Hugging GPT model to take a user's goal and context as input, and then generates a plan that addresses the user's goal. The generated plan is then used to create a list of tasks that can be executed to achieve the goal. Inputs: user's goal, the user's desired outcome or objective, such as write a poem about a cat. Optional context: additional information that may be relevant to the user's goal. This could be anything from background information about the task to specific constraints or preferences. For example, the context could specify that the poem should be written in a specific style or that it should be no longer than 50 words. Outputs: list of tasks, a set of individual steps that must be completed to reach the user's goal. The tasks will be specific to the user's goal and the provided context. For example, a task list generated for the goal write a poem about a cat could include tasks such as research cat-related themes, choose a rhyme scheme, and write the poem. Steps: 1. Generate a plan using Hugging GPT. The planner uses Hugging GPT to create a plan that outlines the steps necessary to achieve the user's goal. This plan might involve various tools and APIs depending on the nature of the task. 2. Return a list of tasks. The planner converts the generated plan into a list of individual tasks that can be executed. Each task represents a specific step that must be completed to achieve the user's goal. Prerequisites: Hugging GPT model, a large language model that can access and utilize various application programming interfaces (APIs). The Hugging GPT model is essential for generating plans and providing access to the tools needed for execution. Langchain, an open-source framework that allows for the creation and execution of complex chains of tasks. Langchain provides the infrastructure needed to manage the planner, execute the tasks, and handle data flow. Fine-tune parameters. Hugging GPT model parameters. The planner may need to adjust the Hugging GPT model parameters to fine-tune its performance for specific tasks. This could involve modifying parameters related to the model's size, training data, or output format. Task planner parameters. The planner itself may have various parameters that can be adjusted to optimize its performance. These parameters could relate to the planning algorithm, task prioritization, or the level of detail provided in the generated plans. Challenges and fixes. Challenge 1: Hugging GPT might not be able to generate a plan. The Hugging GPT model may struggle to generate a plan if the user's goal is too complex, too specific, or if there is insufficient context provided. Fixes to challenge 1: use a different model with a broader knowledge base or specialized in a specific domain may be better suited to generating a plan for the user's goal. For example, a model trained on code could be more effective for generating a plan related to software development. Provide more context, providing more information about the user's goal, desired outcome, and any relevant constraints can help the model understand the task and generate a more accurate plan. Challenge 2. The plan might not be feasible. The plan generated by Hugging GPT may not be practically executable. For example, the plan may require resources that are not readily available, involve steps that are impossible to complete, or violate specific constraints. Fixes to challenge 2. Modify the plan. The planner may need to modify the generated plan to make it feasible. This could involve removing or replacing certain tasks, adjusting the order of the tasks, or introducing new constraints. Add more constraints. Adding more constraints to the planning process can help ensure that the generated plan is more realistic and easier to execute. Challenge 3. The plan might not be complete. The generated plan might not cover all aspects of the user's goal or may omit certain steps that are necessary for successful completion. Fixes to challenge 3. Add more tasks. The planner may need to add more tasks to the generated plan to ensure that it is comprehensive and covers all necessary steps for achieving the user's goal. Use a more comprehensive model. A larger or more specialized model could be better equipped to generate a more detailed and complete plan. For example, a model with a broader knowledge base or trained on a specific domain may be able to provide a more thorough understanding of the task and its requirements. Langchain Experimental Autonomous Agents Hugging GPT Task Planner Plan. This plan outlines the design and functionality of an experimental autonomous agent that leverages the Hugging GPT framework and Langchain for task planning. The agent aims to seamlessly translate user instructions into structured task plans and subsequently generate Python code to execute these plans. Inputs. The user's input, representing the desired action or goal. This can be a simple request like summarize this article or a more complex command like write a Python program to extract data from a website and analyze it. Contextual information that aids in understanding the user's intent and the environment the task is executed in. This can be supplementary text, a URL, or any data relevant to the task. Outputs. A structured task plan, outlining the sequence of steps needed to complete the user's instruction. This plan breaks down the high-level goal into smaller, manageable subtasks. Python code generated to execute each subtask within the task plan. The code is generated based on the specific task and the available libraries and tools. Steps. The agent interprets the user's intent by analyzing the instruction and the provided context. This involves identifying the task type, relevant entities, and potential constraints. The agent decomposes the overall task into a series of smaller subtasks that are more manageable. This process leverages the available knowledge and tools to define a logical workflow. For each subtask, the agent generates Python code using the Hugging GPT framework. This involves selecting the most appropriate model and parameters for the task and then using natural language prompts to guide the code generation. Prerequisites. The Hugging Face Transformers library is a crucial prerequisite for this agent. This library provides a wide range of pre-trained models and tools for natural language processing. Tasks, including text summarization, translation, and code generation. Install the Hugging Face Transformers library using a package manager like pip install. Transformers. The Langchain library facilitates the creation and management of chains of language models and other tools. It provides features for connecting models, integrating external APIs, and building sophisticated AI agents. Install the Langchain library using a package manager like pip install Langchain. Fine-tune parameters. The type of model used for code generation is a critical parameter. Factors like the model's size, architecture, and training data influence the code generation quality. For example, one could choose between a large language model like GPT-3 or a model specialized for code generation. The number of steps or subtasks in the task plan can be adjusted to balance the complexity of a task and the granularity of the plan. A more complex task may require a greater number of steps for a clear and detailed plan. Challenges and fixes. Task complexity can pose a challenge for the agent. Complex tasks may require more sophisticated subtasks and potentially multiple iterations of a planning process. To address this, the agent can utilize more fine-grained subtasks or decompose the task into smaller, more manageable steps. Ambiguity in user instructions is a common issue in human-machine interactions. The agent may require clarification to accurately understand the intent and context of the user's input. To handle ambiguity, the agent can employ prompting techniques to clarify the user's intent. This can involve asking clarifying questions, providing examples, or presenting options for the user to choose from. Code generation errors can occur due to various factors such as limitations in the model, incorrect prompts, or issues with the execution environment. To address code generation errors, the agent can utilize debugging tools to identify and resolve code issues. This may involve stepping through the code, inspecting variables, and using debugging libraries. Langchain experimental autonomous agents Hugging GPT Task Executor. A description of the capabilities of this agent. It executes tasks using pre-trained models from Hugging Face, a popular platform for sharing and deploying machine learning models. Inputs. A detailed description of the task to be performed by the agent. This should be clear and specific to ensure that the agent can properly interpret and execute the task. Any data required for the task. This could be raw text, structured data, or any other format that the selected model can accept. Outputs. The result of executing the task using the selected model. This could be text, a classification label, or any other format produced by the model. Steps. The agent first needs to understand the task description. This involves parsing the text, identifying the key elements, and determining the appropriate action to take. Based on the task description and the available input data, the agent selects an appropriate model from the Hugging Face Model Hub. This selection is based on the model's capabilities and the task requirements. Once a model is selected, the agent executes the model using the provided input data. This involves sending the data to the model and receiving the output. Prerequisites. The Hugging Face Transformers library is a Python library that provides access to a wide range of pre-trained models and tools for working with them. This library is essential for using Hugging Face models with Langchain. This refers to the Python package named Transformers, available for installation via pip. It offers utilities for loading and using pre-trained models, processing text, and performing various NLP tasks. Example: pip install Transformers. The Hugging Face Model Hub is a centralized repository for sharing and deploying machine learning models. It provides a vast collection of models, including pre-trained models for tasks such as text classification, translation, summarization, and more. This refers to the website Hugging Face Co-Models. Users can browse, download, and use these models for their projects. Fine-tune parameters. This refers to the name of the specific pre-trained model to be used. Each model has its own unique name and is associated with specific capabilities and training data. For instance, GPT-2 or BERT base encased are model names. These are the adjustable parameters specific to the chosen model. Model parameters control its behavior, like the number of layers, learning rate, and other hyperparameters. For instance, adjusting the temperature parameter in a text generation model can control how creative or predictable the generated text is. Challenges and fixes. If the required model is not available on the Hugging Face Model Hub, the agent may need to search for an alternative model or download the model directly from a source, like GitHub. For example, if the agent is tasked with a specific NLP task but the corresponding pre-trained model is not on the Hugging Face Model Hub, it may search for a similar model from other sources. If the selected model fails to execute properly, the agent should check the inputs and outputs, ensuring they match the model's requirements. For instance, if the model expects a specific format of input data, the agent needs to ensure that the provided data is correctly formatted. Adjusting model parameters can sometimes fix execution issues. For example, changing the learning rate or the number of layers might improve model performance. Debugging the code, checking for errors and inconsistencies, can identify the root cause of the problem. If the issue persists, it's recommended to report it to the Hugging Face team for further investigation and possible fixes. Langchain Experimental, Autonomous Agents, Hugging GPT, Task Planner, Base Planner Summarization. Base Planner for Hugging GPT Autonomous Agent. Base Planner is the core planning component for the Hugging GPT Autonomous Agent, which is designed to understand and execute user instructions by leveraging the capabilities of various Hugging Face models. It outlines the fundamental steps and considerations involved in planning and executing tasks within the Hugging GPT framework. Inputs. The user prompt is the initial input to the base planner, containing the user's request or instruction. It serves as the starting point for the planning process, defining the desired outcome. For example, a user prompt could be write a poem about a cat or generate a Python script to analyze a dataset. Outputs. The output of the base planner is a list of tasks, which represent the individual steps needed to fulfill the user's request. Each task is a well-defined unit of work that can be independently processed by the Hugging GPT agent. These tasks are generated based on the analysis of the user prompt and the capabilities of Hugging Face models available within the system. Steps. The first step in the planning process is to pass the user prompt into a list of tasks. This involves understanding the user's intent, identifying the key components of the request, and breaking it down into manageable subtasks. This step leverages natural language processing techniques to extract meaning from the user prompt. For instance, the prompt "write a poem about a cat" might be broken down into tasks like identify the relevant cat-related concepts, generate rhyming lines, and structure the poem. Once the tasks are defined, the base planner generates code for each task. This code is specific to the selected Hugging Face models and their functionalities. The code instructs the models to perform the necessary operations to complete the tasks. For example, the task generate rhyming lines could be implemented using a language model like GPT-2, while the task analyze a dataset might require a model trained for data analysis. After generating the code, the base planner executes the code. This involves invoking the chosen Hugging Face models and passing the generated code as input. The models then process the code, perform the designated actions, and produce the desired outputs. These outputs could be text, code, images, or any other format supported by the models. Prerequisites. The Hugging GPT model is a prerequisite for the base planner to function. It serves as the central orchestrator, coordinating the interaction between different Hugging Face models. The Hugging GPT model itself might be based on a large language model like GPT-3, providing the ability to understand complex user instructions and map them to appropriate model capabilities. Fine-tune parameters. Model size refers to the number of parameters in the Hugging Face models used for task execution. Larger models typically have more computational resources and can handle more complex tasks, while smaller models might be more efficient for simpler tasks. Choosing an appropriate model size is crucial for balancing performance and resource consumption. For example, a larger model like GPT-3 could be employed for complex language generation tasks, while a smaller model like Distilbert could be suitable for tasks involving text classification. Temperature is a parameter that controls the randomness or creativity of the model's outputs. Higher temperature values result in more unpredictable and creative outputs, while lower values produce more deterministic and predictable outputs. This parameter is particularly relevant for tasks involving text generation, where it influences the diversity and style of the generated content. For instance, a higher temperature could lead to more unusual and imaginative poems, while a lower temperature might generate more conventional poems. Challenges and fixes. A challenge that can arise is that the model might not understand the user prompt. This can occur if the prompt is ambiguous, lacks context, or uses unfamiliar terminology. To address this, prompt engineering techniques can be employed to provide the model with more explicit instructions and context. This might involve rephrasing the prompt, adding examples, or providing background information relevant to the user's request. Another challenge is that the model might generate incorrect code. This could be due to limitations in the model's understanding of the task, errors in the model's training data, or inconsistencies between the model's output and the expected code format. To mitigate this, using a more powerful model with enhanced code generation capabilities can be beneficial. Alternatively, implementing code verification mechanisms to check the generated code for errors before execution can help ensure correctness. A final challenge is that the model might not be able to execute the code. This could happen if the code requires access to external resources, specific libraries, or certain environment configurations, providing more context to the model, such as the relevant environment variables, dependencies, and execution instructions, can enhance its ability to successfully execute the code. Langchain Experimental Autonomous Agents Hugging GPT Task Planner Planning Output Parser Summary. This component parses the output of a Hugging GPT task planner and provides a structured representation of the plan. The Hugging GPT task planner uses a large language model (LLM) to generate a plan for a given task. This parser takes the output of the planner and converts it into a dictionary containing the plan's description, steps, prerequisites, fine-tuning parameters, and challenges and their corresponding fixes. Inputs. The output of the Hugging GPT task planner, which is a string containing the plan. The plan can be represented as a sequence of steps, each step being a task or a subtask. For example, if the task is to write a blog post, the plan might be to research the topic, write the blog post, edit the blog post, and publish the blog post. Outputs. A dictionary containing the following keys. Description. A description of the plan. This is a summary of the plan, outlining the overall objective and the key steps involved. For example, the description for the plan to write a blog post might be: this plan outlines the steps involved in Writing a blog post on a given topic. Steps: a list of steps to complete the plan. These steps are the individual tasks or subtasks that need to be completed to achieve the overall goal of the plan. Each step should be actionable and specific. For example, the steps for the plan to write a blog post might be: research the topic, write the blog post, edit the blog post, and publish the blog post. Prerequisites: a dictionary of prerequisites for the plan. These are the conditions that must be met before the plan can be executed. For example, the prerequisites for the plan to write a blog post might be access to a computer with an internet connection, access to a blogging platform, and knowledge of the topic. Fine-tune parameters: a dictionary of fine-tune parameters for the plan. These are parameters that can be used to adjust the behavior of the plan. For example, the fine-tune parameters for the plan to write a blog post might be target audience, desired tone, and length of the post. Challenges and fixes: a dictionary of challenges and fixes for the plan. These are potential issues that might arise during the execution of the plan and their corresponding solutions. For example, the challenges and fixes for the plan to write a blog post might be: writer's block, take a break and come back to it later, lack of information, do more research on the topic, and technical issues, contact the blogging platform's support team. Steps: pass the output of the Hugging GPT task planner and extract the relevant information. This step involves identifying the different components of the plan, such as the description, steps, prerequisites, fine-tuning parameters, and challenges and fixes. It may involve parsing the text, identifying keywords and phrases, and extracting the relevant information. Convert the extracted information into a structured format. This step involves organizing the extracted information into a structured format, such as a dictionary. This step ensures that the information is organized in a way that is easy to understand and use. Return the structured format as a dictionary. This step involves returning the structured representation of the plan as a dictionary. This dictionary can then be used by other components of the system, such as the task executor, to execute the plan. Prerequisites: the Hugging GPT task planner must be installed and configured. This prerequisite ensures that the system has access to the necessary tools to generate a plan. The Hugging GPT task planner requires a specific version of Python and other libraries to run successfully. The Hugging GPT task planner must be able to generate a plan. This prerequisite ensures that the system is capable of generating a plan for the given task. The Hugging GPT task planner must be trained on a sufficient amount of data to be able to generate meaningful plans. Fine-tune parameters: the max length parameter can be used to control the length of the generated plan. This parameter allows the user to specify the maximum number of steps in the plan. For example, the user might want to limit the plan to a maximum of 5 steps. This parameter helps to ensure that the plan is concise and manageable. Challenges and fixes: the Hugging GPT task planner may not be able to generate a plan for all tasks. This challenge arises when the task is too complex or the task planner is not trained on sufficient data related to the task. Fix: the task may need to be broken down into smaller subtasks. This involves dividing the task into smaller, more manageable tasks that the task planner can handle. For example, if the task is to write a book, the task could be broken down into smaller tasks such as writing the first chapter, writing the second chapter, and so on. The Hugging GPT task planner may generate a plan that is not feasible. This challenge arises when the plan contains steps that are impossible to execute or involve unrealistic assumptions. fix the plan may need to be manually adjusted. This involves reviewing the generated plan and making necessary adjustments to make the plan feasible. For example, if the plan includes a step that requires access to a specific tool that is not available, the step could be replaced with an alternative step that uses a different tool. Langchain Experimental Autonomous Agents Hugging GPT Task Planner Summary. This is a detailed summary of the task planner for autonomous agents, which utilizes Hugging GPT and Langchain. This planner enables agents to autonomously handle tasks by leveraging the capabilities of both Hugging GPT, a large language model adept at interacting with various tools, and Langchain, a library dedicated to building and deploying applications powered by large language models. Inputs. The input to the task planner is a combination of user input, representing the desired task or goal, and the context, comprising any relevant information or background knowledge pertaining to the task. The context provided to the task planner could include information such as the user's previous interactions, the current state of the system, or any relevant external data that the planner can access. Outputs. The task planner generates a list of tasks that need to be executed to achieve the desired goal or fulfill the user's request. These tasks are meticulously planned, taking into account the available tools and the context of the task. Finally, the task planner produces a comprehensive and human-readable response that summarizes the executed tasks, the results achieved, and any relevant insights gained during the task execution process. Steps. The first step in the task planner's execution is to pass the user input, breaking down the request into its constituent components, and identifying the core intent behind the user's request. Once the user's input has been passed, the task planner identifies the relevant tools that can be employed to fulfill the request. This involves analyzing the task's requirements and selecting appropriate tools from the available toolset. The task planner then plans the sequence of tasks that need to be executed to achieve the desired outcome. This step involves prioritizing the tasks, taking into account the dependencies between them, and ensuring that the chosen tools are optimally utilized. After planning the tasks, the task planner proceeds to execute them in the order specified. This involves interacting with the chosen tools, retrieving necessary data, and performing the required actions. Finally, the task planner returns the final response to the user, summarizing the results of the executed tasks, any insights gained, and the overall outcome of the task execution process. Prerequisites. Hugging GPT, a large language model, is a key prerequisite for the task planner. It plays a crucial role in understanding and interpreting user input, identifying the appropriate tools, and communicating with those tools to execute the planned tasks. Langchain serves as the foundation for the task planner, providing the necessary infrastructure and components for building and deploying the LLM-powered application. It facilitates the interaction between the task planner and Hugging GPT, enabling the seamless integration of various tools and the efficient execution of tasks. Fine-tune parameters. Task prioritization is a crucial parameter that can be fine-tuned to optimize the task planner's performance. This involves adjusting the relative importance of different tasks based on factors such as their urgency, impact, and dependencies on other tasks. Tool selection is another important parameter that can be fine-tuned to improve the task planner's efficiency and accuracy. This involves customizing the criteria for selecting the most Appropriate tools for each task. Based on factors such as the tool's capabilities, availability, and cost. Challenges and fixes. Task ambiguity. A common challenge in natural language processing can arise when the user's request is unclear or open to multiple interpretations. This can be addressed by employing conversation-based clarification techniques to unambiguously determine the user's intent. Selecting the right tools for each task can be challenging, especially when the available tools are diverse and complex. To address this challenge, the task planner utilizes a combination of a knowledge graph and a large language model. The knowledge graph provides a structured representation of the tools and their capabilities, while the LLM assists in interpreting the task's requirements and selecting the most appropriate tools from the knowledge graph. Task execution may encounter errors or unexpected issues, which can lead to task failures. To handle such situations, the task planner implements error handling mechanisms that attempt to resolve the errors and retry failed tasks. This ensures that the task execution process is resilient and can handle unforeseen challenges. Generating a response that is both comprehensive and human-readable is crucial for effective communication with the user. The task planner addresses this challenge by generating responses that clearly summarize the executed tasks, the results obtained, and any relevant insights gained during the task execution process. The response is tailored to be understandable by a human user, without requiring specialized knowledge or technical expertise. Langchain Experimental Autonomous Agents Hugging GPT Task Planner. Task Planner is a component in the Hugging GPT framework. Used for planning tasks, it takes a user's goal and the current context as input and generates a list of tasks to achieve the goal. The tasks are decomposed, prioritized, and assigned to specific tools. For example, if the user's goal is to write a blog post, the task planner could decompose it into subtasks like researching the topic, writing the post, editing it, and publishing it. The task planner could then assign these subtasks to different tools, such as a search engine for research, a text editor for writing, and a social media platform for publishing. Inputs. The user's goal is the desired outcome or objective that the user wants to achieve. It could be a simple task like find a restaurant in New York City or a complex goal like write a research paper on artificial intelligence. The current context refers to the relevant information or knowledge available to the task planner. This could include information about the user's preferences, past interactions, or the environment. For instance, if the user has already expressed interest in Italian food, the current context could include information about Italian restaurants in New York City. Outputs. The output of the task planner is a list of tasks that are generated to achieve the user's goal. These tasks are typically organized in a logical order and can be assigned to specific tools for execution. For example, the task planner might output a list of tasks like search for Italian restaurants in New York City, read reviews for the restaurants, make a reservation, and go to the restaurant. Steps. The first step in task planning is to decompose the user's goal into a series of subtasks. This involves breaking down the goal into smaller, more manageable tasks that can be completed individually. For instance, if the goal is to write a research paper, the subtasks might include gathering research, outlining the paper, writing the introduction, writing the body paragraphs, and writing the conclusion. Once the goal has been decomposed into subtasks, the next step is to prioritize them. This involves determining the order in which the subtasks should be completed to achieve a overall goal most effectively. Some subtasks might be more critical than others, or some might need to be completed before others can be started. For example, in writing a research paper, gathering research might be prioritized over writing the introduction. The final step in task planning is to assign each subtask to a specific tool. This involves identifying the appropriate tool or resource for completing each subtask. The task planner can draw from a wide range of tools, including search engines, text editors, translation tools, and more. For instance, the task of gathering research for a research paper could be assigned to a search engine, while the task of writing the paper could be assigned to a text editor. Prerequisites. The Hugging GPT model is a large language model (LLM) that serves as the foundation for the task planner. It provides the knowledge and understanding required to decompose tasks, prioritize them, and assign them to specific tools. The Hugging GPT model is trained on a massive dataset of text and code, allowing it to understand natural language, generate text, and perform various tasks. Fine-tune parameters. The model size is one of the important parameters that can be fine-tuned for the task planner. It refers to the number of parameters in the Hugging GPT model. A larger model generally has a higher capacity to handle more complex tasks and understand nuanced language. However, it also requires more computational resources and can be slower to train. Challenges and fixes. One challenge in task planning is that the task planner may not be able to decompose a complex goal into subtasks effectively. This can happen when the goal is very abstract, ill-defined, or requires a deep understanding of a specific domain. For example, if the goal is to become a successful entrepreneur, the task planner might struggle to decompose it into meaningful subtasks. One way to address this challenge is to train the task planner on more complex goals. This can involve providing it with examples of complex goals that have been successfully decomposed into subtasks. By learning from these examples, the task planner can improve its ability to handle complex goals. Another challenge is that the task planner may not be able to prioritize subtasks correctly. This could be due to a lack of understanding of the user's preferences, the importance of different subtasks, or the dependencies between them. For instance, the task planner might incorrectly prioritize writing the introduction of a research paper over gathering research, leading to an incomplete paper. To address this challenge, the task planner can be trained on data that includes task priorities. This could involve providing it with examples of goals and their corresponding subtasks, where the subtasks are labeled with their priorities. By learning from these examples, the task planner can improve its ability to prioritize tasks effectively. Finally, the task planner may not be able to assign subtasks to the correct tools. This could be due to a limited understanding of the capabilities of different tools, a lack of knowledge about which tools are available, or an inability to identify the best tool for a given subtask. For example, the task planner might incorrectly assign the task of writing a research paper to a translation tool instead of a text editor. To address this challenge, the task planner can be trained on data that includes tool assignments. This could involve providing it with examples of goals and their corresponding subtasks, where the subtasks are labeled with the tools that are best suited for completing them. By learning from these examples, the task planner can improve its ability to assign tasks to the correct tools. Langchain Experimental Autonomous Agents Auto GPT Prompt Generator Get Prompt Summary This agent generates a prompt for AutoGPT based on inputs and desired outputs. Inputs: the current context, situation, or knowledge related to the task. For example, if the task is to find the best restaurant in a city, the input could be the city name, the type of food desired, and the user's budget. The desired outcome or goal of the task. For example, if the task is to find the best restaurant in a city, the desired outcome could be a list of top-rated restaurants with their addresses, phone numbers, and reviews. Outputs: a prompt that is fed to AutoGPT. This prompt will be specific to the task and will include all of the necessary information for AutoGPT to complete the task. Steps: gather information about the task and its context. This includes understanding the user's intent, the available resources, and the desired outcome. Analyze the inputs and outputs to identify the required actions. This involves breaking down the task into smaller steps and determining which actions AutoGPT needs to take to achieve the desired outcome. Craft a prompt that outlines the task, context, and desired outputs. The prompt should be clear, concise, and specific. It should guide AutoGPT towards completing the task successfully. Prerequisites: an AutoGPT instance, which is a large language model (LLM) that can be used to automate tasks. AutoGPT is available as an open-source project and can be set up on a personal computer or cloud server. A clear understanding of the task and its desired outputs. This includes knowing what the user wants to achieve and what the expected outcome should look like. Fine-tune parameters. The length of the prompt. A longer prompt can provide more context and detail, while a shorter prompt can be more concise and to the point. The specificity of instructions. More specific instructions can help AutoGPT complete the task more accurately, while less specific instructions can give AutoGPT more freedom to explore different options. Challenges and fixes. The prompt being too general. Provide more specific instructions and context. For example, instead of asking AutoGPT to find the best restaurant in the city, specify the type of food desired, the budget, and the location within the city. The prompt being too complex. Break down the task into smaller subtasks. For example, instead of asking AutoGPT to write a blog post about a specific topic, break the task down into smaller steps, such as researching the topic, outlining the blog post, writing the blog post, and editing the blog post. The prompt being ambiguous. Reword the prompt for clarity. For example, instead of asking AutoGPT to find information about a specific topic, specify the type of information desired, such as research papers, news articles, or blog posts. Langchain experimental autonomous agents Hugging GPT response generator load response generator. Summary. This component is a response generator within the Hugging GPT framework. It leverages Hugging Face models to generate text responses based on user prompts. The component essentially acts as an interface between the user input and the chosen Hugging Face model. Inputs. This refers to the text prompt that is provided to the Hugging GPT response generator. It acts as the initial input, prompting the model to generate a response based on the context and intent expressed within the text. An example of this could be a question, a request for a summary, or a creative writing prompt. Outputs. This refers to the generated text output produced by the Hugging Face model based on the input prompt. It is a textual response tailored to the input prompt and guided by the model's training data and parameters. For instance, if the prompt is a question, The output would be a textual answer. If the prompt is a creative writing prompt, the output would be a generated story or poem. Steps. This step involves loading the specified Hugging Face model into the component's memory. It entails fetching the model's weights and architecture from Hugging Face's repository and preparing the model for processing the input prompt. The model is selected based on the requirements of the task and the desired response style, like generating code, summarizing text, or translating languages. The model chosen could be a pre-trained model like BART or GPT-2. Or it could be a fine-tuned model trained on a specific dataset. This step involves processing the input prompt using the loaded Hugging Face model. It entails feeding the prompt to the model, allowing it to interpret the prompt's context and intent. The model then generates a text response based on its internal representation of language and its training on a massive dataset of text. The model predicts the most likely sequence of words that aligns with the input prompt, ensuring a coherent and relevant response. Prerequisites. This refers to the necessary components and resources required to successfully execute the Hugging GPT response generator. The core prerequisite is the presence of a Hugging Face model, specifically one that aligns with the desired functionality and response style. This model should be available within the Hugging Face repository, allowing the component to access its weights and architecture. This refers to the specific name of the Hugging Face model that will be used by the component. It acts as a reference to a unique model within the Hugging Face repository. The model name often reflects the model's architecture, like BART, GPT-2, or a specific fine-tuned version of the model. For instance, Facebook BART Large CNN refers to the BART model fine-tuned on CNN news articles. Challenges and fixes. This refers to an error that might occur during the initial loading of the Hugging Face model. This can be caused by issues like network connectivity problems or the model being unavailable within the Hugging Face repository. This refers to verifying the availability of the specified Hugging Face model within the Hugging Face repository. It involves checking if the model exists, if it is correctly identified, and if there are any issues with accessing it. This step is crucial to ensure that the component can successfully load the model and proceed with the text generation process. This refers to errors that might occur during the text generation process, where the loaded Hugging Face model fails to generate a response despite being successfully loaded. This could be due to issues with the model's configuration or the input prompt itself. This refers to examining the model's configuration parameters, such as the maximum sequence length or temperature, which influence the model's text generation behavior. It involves reviewing these parameters and ensuring they align with the requirements of the input prompt and the expected response style. A misconfigured parameter, like a very short sequence length, could result in truncated responses or the model's inability to generate the expected output. This refers to reviewing the input prompt provided to the Hugging GPT response generator. This involves analyzing the prompt structure, clarity, and potential ambiguity. It ensures that the prompt is well-formed, unambiguous, and provides enough context for the model to understand the desired response. An unclear prompt, lacking context or expressing multiple intents, could result in a response that deviates from the user's expectations or a model failure to understand the prompt's intended meaning. Langchain experimental, autonomous agents, Hugging GPT, Task Planner, Load Chat Planner. This function loads a chat-based planner from a file. A chat-based planner is a type of planner that utilizes a conversational approach to plan tasks. These planners are often implemented using large language models (LLMs) like GPT 3.5 Turbo, which can generate plans based on prompts and conversation history. Inputs. The path to the planner file is a string representing the location of the planner file on your system. For example, planner, JSON or home user planner, YAML. Optional arguments are parameters that can be passed to the planner to customize its behavior. These arguments may include things like the desired format of the output plan, the level of detail in the plan, or the specific LLM to use for generating the plan. Outputs. The output of this function is an instance of the chat-based planner. This instance can be used to interact with the planner to generate plans and manage tasks. Steps. Reading the planner file involves retrieving the planner data from the specified path using file handling functions. The data typically contains information about the planner's structure, configuration, and any predefined steps or actions. Parsing the planner file means interpreting the structure and content of the file. The planner data is processed and translated into a representation that can be understood by the planner object. This step may involve validating the file format, extracting relevant information, and creating necessary data structures to store the planner's configuration. Prerequisites. Hugging GPT is an open-source Python library that enables interaction with various large language models for tasks such as text generation, translation, summarization, and question answering. It is often used in conjunction with other libraries like Langchain to build complex agents and workflows. The pip command is used to install Python packages. It acts as a package manager, allowing you to download and install libraries and their dependencies directly from the Python package index PyPI repository. In this context, pip install Hugging GPT downloads the Hugging GPT library and its required components to your system. A valid planner file is a file that adheres to the expected format and structure defined by the load chat planner function. This file typically contains instructions, rules, and configuration details that define how the planner operates. Existence refers to the requirement that the file must actually be present in the specified location on your computer's file system. Fine-tune parameters. The planner type refers to the approach used by the planner in generating plans. Zero-shot implies that the planner does not require any specific training examples or past experiences to generate a plan. It relies solely on the prompt and its understanding of language to generate a plan. Few-shot suggests that the planner may benefit from a few examples of past plans or task scenarios to refine its understanding and improve plan generation. This can lead to more tailored and accurate plans. The planner model is the specific large language model that will be used to power the chat-based planner. GPT 3.5 Turbo is a powerful language model developed by OpenAI. It can understand and generate human-like text, making it suitable for tasks like generating creative content, translating languages, writing different kinds of creative text formats, and answering your questions in an informative way. Challenges and fixes. An invalid planner file format occurs when the file does not meet the requirements of the planner's structure and format. This can happen if the file uses an incorrect syntax, contains missing data, or has a structure that does not comply with the planner's expectations. A valid planner file format is crucial for the planner to correctly parse and interpret the information within the file. Using a valid planner file format involves adhering to the specific structure and syntax rules defined by the load chat planner function. This might involve ensuring the file is in a specific format like JSON JavaScript object notation or YAML YAML int markup language. A planner file not found error occurs when the specified file path does not lead to an existing file on your system. This means the file you are trying to load cannot be located at the provided path. It could be due to a typo in the file name, an incorrect path, or the file simply not being present. Ensuring the file exists at the given path requires verifying the correctness of the path you have provided and checking if the file is actually present in that location. You may need to double-check the file name, the directory structure, or use a file explorer to verify the file's location. A planner model not found error arises when the planner cannot locate the specified LLM that is supposed to be used for plan generation. This could be because the model is not installed or is not available in the environment where the planner is running. Installing the required planner model involves obtaining and installing the necessary LLM library or package on your system. This might involve using package managers like pip or conda to download and install the specific model you need. Langchain Experimental, Autonomous Agents, Hugging GPT, Task Planner, Step Summary. Langchain Experimental, Autonomous Agents, Hugging GPT, Task Planner, Step Summary. A step in a Hugging GPT Task Planner agent. It is a fundamental building block of the Hugging GPT agent, responsible for executing a specific task, updating the context, and potentially generating a subsequent task. Inputs: the current task, representing the action the agent is currently working on. This can be anything from fetching information, summarizing text, to generating creative content. It's the driving force behind the agent's actions. The current context, which is a compilation of all the relevant information gathered and processed so far. This includes the initial task, previous results, and any relevant external knowledge retrieved during the execution. Outputs: the next task, which is the new action the agent should execute after completing the current task. This could be a related task based on the current task's outcome, or a completely different task determined by the context and the agent's overall objective. The next context, which is the updated context, incorporating the results of the current task, any new information gathered, and potentially other relevant data. This updated context serves as the foundation for the subsequent tasks and ensures the agent maintains a consistent and relevant understanding of the situation. Steps: 1. Get the current task retrieves the currently assigned task from the agent's task queue. 2. Get the current context retrieves the current context, which is the accumulated knowledge relevant to the ongoing task execution. 3. Call the Hugging GPT model to get the next task and context interacts with the Hugging GPT modeler. Large language model specialized for planning and execution. Passing in the current task and context. The model then uses its understanding of the task and the available information to generate the next task and the corresponding updated context. 4. Return the next task and context outputs the next task and the updated context to the agent. This allows the agent to seamlessly transition to the next task and continue its execution with the most relevant information. Prerequisites: a Hugging GPT model. This refers to the Hugging GPT model, a large language model specifically trained to perform planning and execution tasks. This model is the core component of the Hugging GPT agent, responsible for generating the next task and updating the context. Fine-tune parameters. None. There are no specific parameters to fine-tune for this step, as the core functionality is handled by the Hugging GPT model. which has its own tuning process. Challenges and fixes. The Hugging GPT model may not be able to generate a valid next task or context. It's possible that the model might fail to generate a coherent and relevant next task or context due to ambiguity, lack of information, or errors in the model's understanding. Try using a different Hugging GPT model if the current model struggles to generate valid outputs. Experimenting with different Hugging GPT models, each with its strengths and biases, could potentially yield better results. This involves choosing a model known for its performance in similar tasks or exploring models specifically trained for planning and execution. The Hugging GPT model may generate a task or context that is not relevant to the current task. The model's understanding of the context and its ability to predict relevant tasks may be limited, leading to irrelevant outputs. Try providing more context to the Hugging GPT model to improve the model's ability to generate relevant outputs. Enriching the context with more specific information can be crucial. This involves providing the model with a more detailed description of the current task, relevant background information, or any prior knowledge related to the task's domain. This helps guide the model towards generating more pertinent tasks and contexts. Llama 2 Chat Wrapper Summary. This wrapper provides a concise description of the Llama 2 chat model and its use cases. It outlines the input and output of this wrapper and the steps involved in using it. It also highlights the prerequisites, fine-tuning parameters, and potential challenges and their solutions. Inputs. The user provides a question or prompt as input to the model. For example, what is the capital of France? The wrapper takes this input and passes it to the Llama 2 chat model. The chat history stores the previous conversation turns, allowing the model to maintain context and provide consistent responses. This helps in creating more engaging and coherent conversations. Outputs. The model generates a text response based on the user input and chat history. The response can be an answer to the question, a continuation of the conversation, or a creative text piece based on the prompt. Steps. The Llama 2 chat object is initialized. This step sets up the model and prepares it for processing user input. The predict method is called with the user input and chat history. This method utilizes the Llama 2 model to generate the response. Prerequisites. Install the Langchain and Transformers libraries using the following command: pip install Langchain. Transformers. These libraries are essential for interacting with the Llama 2 model and managing the chat history. Install the Llama 2 model using the Transformers library pip install Transformers. This command installs the necessary components to load and use the Llama 2 model. Fine-tune parameters. The temperature parameter controls the randomness of the generated text. Higher temperature values result in more creative and unpredictable responses, while lower values produce more predictable and conservative outputs. The top P parameter limits the probability distribution of the next token to be generated. A lower value restricts the model to more probable words, while a higher value allows for more diverse and less predictable outputs. Challenges and fixes. The model might generate repetitive or nonsensical responses. This can be addressed by adjusting the temperature or top P values, effectively controlling the model's randomness and probability distribution. The model might not be able to access external information. To address this, use a different wrapper that supports external information retrieval. This allows the model to access knowledge bases, search engines, or other external resources to provide more comprehensive and accurate responses. Langchain Experimental Chat Models.llm Wrapper Mixtral Summary. A Langchain wrapper for the Mixtral large language model. This wrapper allows you to use the powerful Mixtral language model in your Langchain applications. Inputs. Text. Input the text you want to provide to the Mixtral model. For example, you can input a question, a request for a summary, or a creative writing prompt. Outputs. Text. Output. The generated output from the Mixtral model, based on the input text. This could be a response to a question, a summary, or a creative piece of writing. Steps. Initialize the Mixtral model. The wrapper sets up the Mixtral model. Send the input to the model. The input text is sent to the initialized Mixtral model for processing. Return the output from the model after processing the input. The Mixtral model generates an output, which is returned by the wrapper. Prerequisites. Install the Mixtral library. Install the Mixtral library using the command pip install Mixtral. This allows you to use the Mixtral model in your Python environment. Install Langchain. Install the Langchain library using the command pip install Langchain. This provides the framework for interacting with and managing language models. Fine-tune parameters. Temperature controls the randomness of the output. A higher temperature value will result in more creative and unexpected outputs, while a lower value will lead to more deterministic and predictable outputs. Top K limits the number of possible tokens to be considered during text generation. This helps to constrain the model's outputs to a more focused range of possibilities. Challenges and fixes. Error model not found. If you encounter this error, it means that the Mixtral library is not installed. You can fix this by installing the Mixtral library using pip install Mixtral. Incorrect output format. If you are experiencing issues with the output format, you can specify the desired format by using the format argument of the Mixtral class. For instance, you can specify JSON, text, or HTML to control the output format. Langchain experimental chat models.llm wrapper. Llama 2 chat summary. This wrapper provides access to Llama 2 chat models. Llama 2 is a large language model developed by Meta that excels in conversational tasks. This wrapper enables developers to integrate Llama 2 into their applications for natural language understanding and generation. Inputs. Textual input provided to the Llama 2 model. This can be a question, a prompt, or a conversational turn in a dialogue. Outputs. Textual output generated by the Llama 2 model in response to the provided input. This can be an answer, a generated text, or a continuation of the conversation. Steps. Initialize the LLM. The wrapper first requires the user to provide the name or path of the Llama 2 model they want to use. This step sets up the connection to the chosen model. Load the model. After initialization, the wrapper loads the Llama 2 model into memory, making it ready to process user input. Prerequisites. Llama.cpp installation to utilize the Llama 2 chat model. Llama.cpp is a crucial component. It enables the model to be run locally without the need for a large cloud infrastructure. The installation is straightforward with the command pip install llamasp python. Model weights. Llama 2 model weights are necessary for the model to function. These weights are a set of parameters that the model has learned during its training. Meta provides these weights for various versions of Llama 2 on its official website. Fine-tune parameters. Temperature. This parameter controls the randomness and creativity of the model's output. A higher temperature value leads to more diverse and potentially unexpected responses, while a lower temperature value produces more predictable and consistent results. Top K. This parameter restricts the set of possible words the model can choose from at each step of text generation. A smaller top K value limits the model's vocabulary, making its output more concise and focused. A larger value provides more flexibility and potential for creative expression. Top P. This parameter controls the probability distribution of possible words that the model can select from at each step. It uses a method called nucleus sampling, which ensures that the model only considers a subset of the most probable words. This helps to avoid generating unexpected or nonsensical outputs. Challenges and fixes. Model loading error. One common issue that users may encounter is a model loading error. This can be caused by missing prerequisites, incorrect model paths, or incompatible versions of llama.cpp or the model weights. To resolve this, ensure that llama.cpp is installed correctly and that the model weights are located in a specified directory. It's also essential to double-check the compatibility between the llama.cpp version and the model. Slow inference speed. The time it takes for the model to process input and generate output can be a challenge, especially when dealing with large and complex models. Users may experience slow inference speeds if they are running the model on a machine with limited resources. To address this, using a GPU can significantly improve performance. Optimizing the llama.cpp configuration by adjusting parameters like the number of threads and memory usage can also enhance speed. Langchain experimental chat models.llm wrapper Ocker summary. This wrapper allows the use of the Ocker language model from Microsoft within the Langchain framework. It acts as a bridge, enabling interaction with the Ocker model's capabilities through Langchain's API. Inputs. The input to the Ocker model is text, which can be a question, a prompt, or any text requiring processing by the model. For example, if you want to generate a summary of a news article, you would provide the article text as input. Outputs. The output from the Ocker model is also text, which may be a summary, a response to a question, a generated piece of text, or any other output that the model is capable of producing. The specific output depends on the nature of the input and the task that the model is asked to perform. Steps. The wrapper initializes the Ocker model by loading the necessary resources, setting up the model's configuration, and preparing it for processing input. This involves specifying the model's parameters, such as the version or variant of the Ocker model being used. The input text is then passed to the initialized Ocker model. This step involves converting the input text into a format that the model can understand and processing it using the model's algorithms. The Ocker model produces an output based on the input text. This output is then returned by the wrapper, making the results available to the user or for further processing within the Langchain framework. Prerequisites. Langchain is a library that provides a framework for building and deploying language model applications. It simplifies the process of integrating large language models into applications and offers tools for working with various models, tasks, and data sources. Transformers is a library developed by Hugging Face that provides tools and infrastructure for working with transformers-based language models. It facilitates training, fine-tuning, and deploying a wide range of pre-trained models, including Ocker. Fine-tune parameters. Fine-tuning refers to the process of customizing a pre-trained language model for a specific task. For example, fine-tuning an Ocker model could involve providing it with a set of training examples related to a particular domain or task, such as summarizing legal documents or writing creative stories. In this case, the Ocker model wrapper does not offer any fine-tuning options. The wrapper focuses on providing a basic interface for using the Orca model without modification. Challenges and fixes. The availability of the Orca model may vary depending on the region or location of the user. If the model is not accessible in a particular region, it's recommended to switch to a different model or use a different region. For instance, if the Orca model is not accessible in Europe, a different model or a region where the Orca model is accessible can be used. The Orca model may not be able to handle all types of input, particularly if the input text is formatted in a way that the model does not recognize or understand. Ensuring that the input text is in a format the model can process is crucial for successful interaction. For example, if the input text is a code snippet, it should be formatted in a way that the Orca model understands, such as using a specific code highlighting syntax or delimiters. The Orca model, like any language model, can sometimes produce incorrect or nonsensical outputs. This can happen due to various factors, such as ambiguity in the input text, the model's limitations, or unexpected variations in the training data. If the model's output is not satisfactory, consider using a different model that is better suited for the task or providing more context in the input. For example, instead of asking what is the meaning of life, one could provide more context by asking what is the meaning of life according to the philosophy of Aristotle. Langchain experimental chat models LLM wrapper Vicuna. Vicuna is a wrapper for the Vicuna large language model LLM, enabling its integration and utilization within the Langchain framework. It serves as an interface that allows Langchain to interact with Vicuna LLM, leveraging its capabilities for various natural language processing tasks. Inputs: a prompt string, representing the textual input provided to the Vicuna LLM. The prompt serves as the initial instruction or query that the LLM processes to generate a response. For example, a prompt could be write a short story about a cat who goes on an adventure. Outputs: the textual response generated by the Vicuna LLM in response to the provided prompt. This output may consist of multiple sentences or paragraphs, depending on the complexity of the prompt and the LLM's capabilities. For instance, in response to the prompt write a short story about a cat who goes on an adventure, the LLM might output a narrative that describes a cat's journey through a forest, encountering various obstacles and characters along the way. Steps: the prompt string is sent to the Vicuna LLM for processing. This involves the LLM analyzing the prompt and understanding its intent and context. The Vicuna LLM generates a textual response based on the input prompt. This response is generated by the LLM using its internal language model, trained on a massive dataset of text and code. The generated text response is returned as the output of the wrapper. This output is then available for further processing or use within the Langchain framework. Prerequisites: Vicuna LLM installed and accessible. This means that the Vicuna LLM software needs to be installed on the system and configured correctly for use. This may involve downloading and installing the necessary software packages, configuring environment variables, and setting up connections to any required external services. For example, one might install the Vicuna LLM from its official website and configure it to run on a local machine, ensuring that all dependencies are met. Install Vicuna LLM through the official channels. This involves obtaining the necessary software packages and following the installation instructions provided by the Vicuna LLM developers. The process may involve using package managers like pip or conda, depending on the chosen operating system and LLM version. Configure the LLM to run on your system. This step involves setting up the LLM environment to ensure it functions correctly on the target system. This might include configuring environment variables, setting up necessary dependencies, and ensuring access to any required resources like GPUs or cloud computing services. For instance, one might configure the LLM to use a specific GPU for accelerated processing, if available, or connect it to a cloud storage service for accessing data. Langchain installed and configured. Langchain is a framework that provides tools and utilities for building and working with language models, including LLM wrappers. Installing and configuring Langchain is necessary for using the Vacuna LLM wrapper. This typically involves installing the Langchain package using a package manager like pip and configuring it to work with the installed Vacuna LLM. Install Langchain using pip install Langchain. This command installs the Langchain package from Python package index pypi. Initialize Langchain and configure the required components. This involves setting up the Langchain environment by importing necessary modules and configuring its components, such as the LLM wrapper, to interact with the Vacuna LLM. Fine-tune parameters. Temperature controls the randomness of the generated text. A higher temperature value leads to more creative and unpredictable responses, while a lower value results in more deterministic and consistent outputs. For example, a temperature of 0.5 might produce responses that are more focused on the prompt's intent, while a temperature of 1.0 could lead to responses with greater variability and potentially unexpected elements. Top P probability threshold for sampling words from the vocabulary. It determines the range of words considered during text generation. A lower top P value narrows the range, resulting in more predictable and conservative outputs, while a higher value widens the range, allowing for more diverse and potentially surprising word choices. For instance, a top P of 0.8 might lead to outputs where the LLM prioritizes words that are highly probable within the context, while a top P of 0.95 could allow for a broader selection of words, potentially including less common but still contextually relevant choices. Top K number of most likely words to consider during sampling. It influences the diversity of the generated text by limiting the number of potential words for the LLM to choose from. A smaller top K value restricts the options, leading to more predictable outputs, while a larger value allows for more variation and potentially unexpected word choices. For instance, a top K of 10 might focus on the most probable words, producing outputs with a higher level of predictability, while a top K of 50 could introduce a greater range of possible words, leading to more diverse and potentially creative responses. Max length, maximum length of the generated text. It sets a limit on the number of tokens or words that the LLM can generate in response to a prompt. This parameter helps control the length of the output, preventing excessively long or short responses. For example, a max length of 100 could limit the LLM to generating a maximum of 100 words, while a max length of 500 would allow for a longer output. Repetition penalty. Penalty for repeating words or phrases within the generated text. This parameter discourages the LLM from generating repetitive text by penalizing the repeated use of words or phrases. A higher repetition penalty value increases the penalty, resulting in less repetitive outputs, while a lower value decreases the penalty, allowing for more repetition in the generated text. For example, A repetition penalty of 1.2 might discourage the LLM from repeating certain words or phrases, while a repetition penalty of 0.8 might allow for a higher degree of repetition. Challenges and fixes. Challenge 1. The LLM may generate irrelevant or inaccurate information. This challenge arises from the nature of language models, which rely on statistical patterns and may not always be able to accurately interpret or represent real-world knowledge. For instance, a prompt asking for information about a specific historical event might result in an output that includes inaccurate details or misrepresents the event. Ensure that the prompt is clear and specific to guide the LLM to generate accurate responses. A well-defined prompt with precise instructions and relevant context can help the LLM understand the desired output and minimize the risk of generating inaccurate information. For example, instead of a vague prompt like "Tell me about the American Revolution," a more specific prompt like "Describe the key events that led to the American Revolution" is more likely to elicit accurate information. Utilize prompt engineering techniques to enhance the quality of generated text. Prompt engineering involves crafting prompts that guide the LLM towards generating accurate and relevant responses. This includes techniques like providing context, using specific keywords, and structuring prompts in a way that helps the LLM understand the desired output. For instance, a prompt like "Write a short biography about Abraham Lincoln," highlighting his key achievements, uses specific keywords and provides context to guide the LLM in generating a relevant and accurate response. Challenge 2. The LLM may struggle with complex reasoning and knowledge-intensive tasks. Language models are often trained on vast amounts of text data, but their ability to perform complex reasoning and knowledge-intensive tasks may be limited. For instance, a prompt asking the LLM to solve a complex logic puzzle or provide an in-depth analysis of a scientific concept might exceed its capabilities. Consider using a specialized language model for complex tasks. For tasks requiring specialized knowledge or reasoning abilities, a language model trained specifically for that domain might be more suitable. For instance, a language model trained on medical literature could be better suited for answering questions about healthcare, while a language model trained on legal documents could be more effective for providing legal advice. Combine Vicuna with other tools and techniques to augment its capabilities. Integrating Vicuna with other tools and techniques, such as knowledge graphs, search engines, or external APIs, can enhance its ability to handle complex tasks. For example, combining Vicuna with a knowledge graph could provide it with access to a vast repository of structured information, enabling it to answer more complex questions. Challenge 3. The LLM may produce biased or offensive text. Language models are trained on massive datasets of text, which may contain biases and prejudices present in the real world. This can lead to the LLM generating text that reflects these biases, potentially causing harm or offense. For instance, a prompt asking the LLM to write a story about a doctor might result in an output that reinforces gender stereotypes. Ensure that the LLM is trained on a diverse and inclusive dataset. Training the LLM on a dataset that is representative of diverse perspectives and experiences can help mitigate bias in the generated text. This involves ensuring that the dataset includes text from a wide range of sources, authors, and perspectives, representing different cultures, languages, and backgrounds. Employ bias detection and mitigation techniques to reduce bias in generated text. Techniques such as bias detection algorithms and prompt engineering can help identify and address bias in the generated text. Bias detection algorithms can analyze text outputs for potential biases, while prompt engineering techniques can help mitigate bias by crafting prompts that are more inclusive and equitable. Challenge 4. The LLM may generate text that is not coherent or grammatically correct. Language models are trained to predict the next word in a sequence. And while this is effective for generating fluent text, it may not always result in perfectly coherent or grammatically correct outputs. For instance, the LLM might generate sentences with incorrect grammar or introduce inconsistencies in the overall narrative. Use prompt engineering techniques to improve text quality. Prompt engineering can help guide the LLM towards generating more coherent and grammatically correct text. This includes techniques like providing clear instructions, using specific keywords, and structuring the prompt in a way that encourages the LLM to produce well-written outputs. Consider integrating a language editing tool to enhance coherence and grammar. A language editing tool, such as a grammar checker or a style guide, can be integrated with the LLM wrapper to automatically review and improve the generated text for coherence and grammatical accuracy. This can help ensure that the final output is of a high standard, even if the LLM's initial response contains errors or inconsistencies. Prompt Generator Get Prompt Summary. This module is responsible for creating instructions for AutoGPT, a powerful AI agent that can automate tasks. The prompt generator takes context and a defined task as input. Inputs. Context. This refers to the overall background information and details related to the task AutoGPT needs to accomplish. It provides a comprehensive understanding of the situation and the desired outcome. An example of context would be: write a Python script to access the Weather API and retrieve current weather data for New York City. Task. This defines the specific action or objective AutoGPT needs to achieve. It should be clear, concise, and well defined. For instance, a task could be retrieve weather data for New York City using OpenWeatherMap API. Outputs. Prompt a thoughtfully constructed set of instructions for AutoGPT that guide it to complete the assigned task successfully. The prompt should be formatted in a way that AutoGPT can easily understand and execute. Here's an example of a prompt: use the OpenWeatherMap API to access current weather data for New York City. Retrieve data for temperature, humidity, and wind speed. Steps. Analyze context and task. Carefully examine the provided context and task to understand the overall objective and identify any essential information or requirements. Identify relevant information for the prompt. Extract specific details from the context and task that are crucial for AutoGPT to understand and execute. For instance, if the task involves using an application programming interface API, ensure the prompt includes API name, endpoint URLs, and required parameters. Structure prompt with clear instructions. Compose a clear and concise prompt with explicit instructions for AutoGPT. Use simple language. Break down complex tasks into smaller steps, and provide any necessary examples or guidelines to ensure successful completion. Prerequisites. Context. A clear and concise description of the task that provides all the necessary background information. It should be well defined, avoiding ambiguity and ensuring a clear understanding of the goal. For example, instead of analyze the market, Provide a more specific context like analyze the current market trends for electric vehicles in the United States. Task a specific and achievable goal that AutoGPT can accomplish within its capabilities. It should be well defined, with a clear objective and scope. An example of a well-defined task would be generate a report on the market trends for electric vehicles in the United States, including sales data, consumer preferences, and industry growth projections. Fine-tune parameters. Prompt length. This parameter determines the desired length of the generated prompt, depending on the complexity of the task and the amount of information required. The prompt length can be adjusted accordingly. For instance, a complex task may require a longer prompt to provide detailed instructions, while a simple task might be sufficiently described with a shorter prompt. Prompt complexity. This parameter refers to the level of detail and complexity required in the generated prompt. A higher prompt complexity would involve more detailed instructions, specific guidelines, and possibly multiple steps to ensure accurate execution. Conversely, a lower prompt complexity might focus on a more straightforward approach with fewer steps and less detailed instructions. Challenges and fixes. Challenge 1. Ambiguous or unclear context. If the provided context is unclear or ambiguous, it can lead to inaccurate or incomplete prompts. For example, a context like analyze the market is too broad and lacks specific information. To address this challenge, clarify the context by providing specific details, such as the target market, time frame, or specific aspects to be analyzed. Challenge 2. Unrealistic or overly complex task. If the assigned task is overly complex or unrealistic, it might be difficult for AutoGPT to complete successfully. For instance, a task like cure cancer is overly ambitious and outside the capabilities of AutoGPT. To resolve this, simplify the task by breaking it down into smaller, more manageable steps. Alternatively, consider reframing the task to focus on a specific aspect or subproblem that is within the scope of AutoGPT's abilities. Langchain Experimental Chat Models LLM Wrapper Mixtral Summary. This document provides a detailed explanation of the Langchain wrapper for the Mixtral Large Language Model. Langchain is a powerful framework for building and deploying language models, and this wrapper enables seamless integration of Mixtral into Langchain workflows. Inputs. This refers to the text data that is provided as input to the Mixtral model. For example, a user's query, a piece of text to summarize, or a prompt for generating creative content. Outputs. This represents the output generated by the Mixtral model in response to the provided input. The output could be a summarized version of the input text, a generated creative text, or a response to a user's question. Steps. This step involves setting up the Mixtral model within the Langchain environment. This typically involves using the Langchain wrapper to load the Mixtral model and configure it for use. This step involves providing the text input to the Mixtral model. The input could be provided directly to the model or through a Langchain chain that manages the input and output flow. This step involves receiving the output generated by the Mixtral model and processing it as needed. This might involve formatting the output, extracting relevant information, or integrating it into a larger application. Prerequisites. This refers to the necessary software libraries that need to be installed for using the Langchain wrapper with the Mixtral model. Langchain provides a unified interface for working with different language models, making it easier to integrate Mixtral into your projects. This refers to the specific library that provides the Mixtral model and its associated Functionalities. Installing this library is essential for using the Mixtral model with Langchain. Fine-tune parameters. These are the settings and configurations that can be adjusted to tailor the behavior of a Mixtral model for specific tasks or domains. Fine-tuning allows you to optimize the model's performance for specific use cases by customizing its parameters. For instance, you can adjust the model's temperature for controlling the randomness of the generated text or change the top K parameter for filtering the model's vocabulary. Challenges and fixes. Integrating Mixtral with Langchain might come with challenges, like setting up the model correctly and ensuring smooth communication between the two frameworks. However, there are solutions to address these issues and optimize the integration process. This refers to troubleshooting steps involved in ensuring the Mixtral model is properly set up and functioning within the Langchain environment. This might involve checking if the necessary libraries are installed, verifying the compatibility of Langchain and Mixtral versions, and resolving any conflicts or dependencies between them. The Mixtral model, like any large language model, might have limitations and biases inherent in its training data and architecture. These issues can impact the model's performance and output quality. It is important to understand and address these challenges to ensure the model produces accurate and reliable results. This refers to the steps taken to address potential issues related to the performance and quality of the Mixtral model's outputs. These steps could include investigating the model's limitations and biases, exploring alternative model parameters or fine-tuning strategies to improve its performance, or considering using alternative language models or techniques if the Mixtral model does not meet specific requirements. Langchain Experimental Comprehend Moderation Base Summary. A Langchain tool that leverages Amazon Comprehend's moderation capabilities to assess the suitability of text content. This tool utilizes Amazon Comprehend's moderation features to analyze text and identify potentially inappropriate or harmful content. It leverages the power of Amazon Comprehend to help developers and organizations ensure that their text content adheres to community guidelines and policies. Inputs. Text to be moderated. This refers to the text content that needs to be evaluated for its suitability. It could be a comment, a post, a review, or any other form of text content. Outputs. Moderation labels with associated confidence scores. These are the labels assigned to the text based on its content, along with a confidence score indicating the likelihood of the label being accurate. For example, the tool might assign labels like hate speech, violence, or sexual content, with a confidence score ranging from 0 to 1. Steps. Send text to Amazon Comprehend for moderation analysis. This step involves sending the input text to Amazon Comprehend's moderation API. Amazon Comprehend will then analyze the text using its machine learning algorithms to identify any potential issues. Receive moderation labels and confidence scores. Once Amazon Comprehend finishes analyzing the text, it will return a set of labels and confidence scores. The labels represent the potential issues identified in the text, and the confidence scores indicate how likely it is that the label is accurate. Prerequisites. AWS account. An AWS account is required to use Amazon Comprehend's moderation API. This is the central account on the Amazon Web Services platform, providing access to various services like Amazon Comprehend. AWS credentials configured for access to Amazon Comprehend. This refers to the access keys and secret keys associated with your AWS account. These credentials grant your application the necessary permissions to interact with the Amazon Comprehend API. Fine-tune parameters. Language code for text analysis e.g. N. FR. This parameter specifies the language of the input text. It's crucial to provide the correct language code for accurate moderation analysis. As Amazon Comprehend uses different models for different languages. Threshold for confidence scores to consider a label as applicable. This parameter determines the minimum confidence score required for a label to be considered a valid match. It allows you to customize the sensitivity of the moderation process, depending on your specific requirements and risk tolerance. Challenges and fixes. Rate limits on Amazon Comprehend. API calls. Amazon Comprehend imposes rate limits on the number of API calls you can make per second or per minute. Exceeding these limits can result in API throttling, slowing down your application or even preventing it from accessing the service. Handling potential errors during API calls. API calls can sometimes fail due to network issues, service outages, or other unexpected factors. It's important to implement robust error handling mechanisms to gracefully handle such situations, preventing application crashes and ensuring a smooth user experience. Langchain experimental comprehend moderation base moderation config moderation prompt safety config. Inputs. Text that is input to the model, for example, a user prompt or a query. Text that is generated by the model in response to the input. For example, a response or a generated text. Outputs. A categorization of the safety of the input and response, indicating whether the text contains potentially harmful or inappropriate content. Steps. The input text is provided to the system, which is typically a language model or a chatbot. The model processes the input text and generates a response. The input text and the model response are compared using a predefined set of criteria, analyzing the content for potential risks. Based on the comparison, the system outputs a safety categorization, assigning a label that reflects the level of risk associated with the text. Prerequisites. Amazon Comprehend, a service provided by Amazon Web Services (AWS), is configured and available for use. Fine-tune parameters. Threshold values are set for different safety categories, defining the level of risk that triggers a particular categorization. Challenges and fixes. The system may incorrectly categorize content as safe or unsafe, resulting in false positives or negatives. The threshold values for different safety categories can be refined to improve the accuracy of the categorization, aiming to minimize false positives and negatives. The system may not be able to identify all potential safety risks due to the limitations of its current categorization system. New safety categories can be added to the system, expanding its ability to identify and categorize a wider range of potential risks. Langchain experimental chat models LLM wrapper Mixtral. A detailed description of the Mixtral LLM wrapper, including its capabilities, inputs, outputs, steps involved, prerequisites, fine-tuning parameters, and potential challenges and fixes. Inputs. The input to the Mixtral LLM wrapper is a text prompt, which is the text that the user wants the model to generate a response to. For example, the user may provide a prompt such as write a poem about a cat. Outputs. The output of the Mixtral LLM wrapper is a generated text response based on the input prompt. The generated text can take many forms, including poems, stories, articles, summaries, and translations. The response is determined by the model's training data and the specific parameters used during generation. Steps. The first step in using the Mixtral LLM wrapper is to initialize the Mixtral model. This involves loading the model's weights and parameters into memory, which allows the model to be used for text generation. Once the Mixtral model is initialized, the user's text prompt is sent to the model. The model then processes the prompt and uses its knowledge to generate a corresponding response. The final step is to receive the generated text from the Mixtral model. This text is then returned to the user as the output of the LLM wrapper. Prerequisites. Python is a widely used, high-level programming language known for its readability and versatility. It's a key requirement for utilizing the Mixtral LLM wrapper, as it provides the necessary environment for running the wrapper's code. The Mixtral library is a Python library that provides access to the Mixtral language model. It allows users to interact with the model and perform tasks like text generation, translation, and summarization. Having this library installed is essential for leveraging the capabilities of the Mixtral LLM wrapper. Fine-tune parameters. Temperature is a hyperparameter used in language models to control the creativity and randomness of the generated text. A higher temperature value increases the model's tendency to generate more unpredictable and diverse outputs, while a lower temperature value results in more predictable and consistent responses. For example, a higher temperature might encourage the model to explore more unconventional word choices or sentence structures, while a lower temperature might lead to a more conservative and predictable output. Top K is a parameter that limits the number of possible words the model considers at each prediction step during text generation. For example, with a top K value of 10, the model would only consider the 10 most likely words at each step, effectively limiting the potential output space. This parameter can help control the diversity and quality of the generated text, potentially reducing the risk of generating nonsensical or repetitive content. Top P is a parameter that controls the probability distribution of the model's word predictions during text generation. It works by setting a threshold, P, and selecting words whose cumulative probability exceeds that threshold. For example, with a top P value of 0.9, the model would select words whose cumulative probability reaches 90 or more, effectively excluding low probability words from the prediction space. This helps to ensure that the model generates more relevant and coherent text, reducing the likelihood of generating nonsensical or irrelevant content. Challenges and fixes. A common challenge when working with language models is that they may not always generate coherent and meaningful text. This could be due to factors like the model's training data, the complexity of the prompt, or the parameter settings used during text generation. Adjusting temperature, top K, and top P parameters can significantly influence the quality and coherence of the generated text. Temperature controls the model's creativity. Top K limits the vocabulary, and top P influences the probability distribution of word choices. By experimenting with these parameters, users can find settings that produce more coherent and relevant responses. For example, lowering the temperature might result in more predictable and well-structured text, while increasing top K could introduce more diverse word choices, potentially enhancing creativity. Another challenge is that language models, especially large ones, can take a significant amount of time to generate responses. This can be attributed to the complexity of the model's calculations and the extensive processing required to generate meaningful text. One potential fix for this is to reduce the length of the input prompt. A shorter prompt can simplify the task for the model, leading to faster generation times. Additionally, if possible, users can consider Using a smaller language model. Smaller models generally require less computational resources and can therefore generate responses more quickly. For example, if the prompt is complex and requires a lot of processing, using a smaller model or shortening the prompt could significantly reduce generation time. Moderation toxicity config summary. A Langchain moderation config for assessing the toxicity of text. This configuration defines the input, output, steps, prerequisites, fine-tuning parameters and challenges along with their fixes for moderating text content based on its toxicity. Inputs. Text to be moderated. The text that will be analyzed for potential toxicity. This input is the raw text content that needs to be moderated. Outputs. Toxicity score. This is a numerical score representing the level of toxicity detected in the text. A higher score indicates more toxic content. Moderation labels. These are labels indicating specific types of toxicity detected in the text. For example, hate speech, violence, or sexual content could be detected. Steps. Tokenize input text. This involves breaking down the input text into individual words or units called tokens. This is necessary for most natural language processing tasks, including toxicity detection. Send tokens to moderation API. The tokens are then sent to a moderation API, which is a service specifically designed to analyze text for toxicity. Receive toxicity score and labels. The moderation API returns a toxicity score and associated labels based on the provided tokens. This information provides a comprehensive assessment of the text's toxicity. Prerequisites. Amazon Comprehend API key. This is a unique identifier that grants access to the Amazon Comprehend API, which provides natural language processing capabilities, including toxicity detection. It is used for authenticating requests sent to the Amazon Comprehend API. Your Amazon Comprehend API key. This is the specific API key you have obtained from Amazon Comprehend to access its services. It's crucial to ensure this key is valid and securely stored. Amazon Comprehend API endpoint. The API endpoint is the specific address of the Amazon Comprehend API service. This is where your requests are directed for processing. It's important to have the correct endpoint to ensure successful communication with the API. Your Amazon Comprehend API endpoint. This is the specific API endpoint you use to interact with the Amazon Comprehend API. It is usually a unique URL provided by Amazon Comprehend. Fine-tune parameters. Threshold. The toxicity score threshold for triggering moderation. This determines the level of toxicity that triggers moderation actions, such as blocking or flagging the content. Labels. A list of moderation labels to check for. This specifies the particular types of toxic content that you are interested in detecting. For example, you might want to check for hate speech, violence, or sexual content. Challenges and fixes. Incorrect API key. This happens if the provided API key is invalid, expired, or does not have the required permissions to access the Amazon Comprehend API. Ensure the API key is correct and has the necessary permissions. Double-check the API key you are using and make sure it's valid and has the right permissions for accessing the Amazon Comprehend API. Incorrect API endpoint. This occurs if the API endpoint used in the request is incorrect or inaccessible. Ensure the API endpoint is correct and accessible. Make sure you are using the correct endpoint provided by Amazon Comprehend. Verify that the endpoint is accessible and that there are no network issues preventing communication. Rate limiting. This happens when the number of requests sent to the API exceeds the allowed rate limit. Implement a rate limiting mechanism to avoid exceeding the API request limit. To avoid exceeding the API request limit, you can implement a rate limiting mechanism to control the number of requests sent per unit of time. This can involve adding delays or queuing requests to ensure you stay within the API's limitations. API errors. These are errors that may occur during communication with the Amazon Comprehend API, such as network issues, server errors, or authentication failures. Handle API errors gracefully and retry requests if necessary. When handling API errors, it's crucial to implement appropriate error handling mechanisms. This involves catching and logging errors gracefully. For transient errors, you may want to retry the request after a short delay. Langchain experimental, comprehend moderation, base moderation exceptions, moderation toxicity error. This error is raised when the text provided for moderation is detected as containing toxic content. Toxicity can refer to various forms of harmful language such as hate speech, threats, bullying, or obscenities. The detection is performed by a machine learning model trained to identify such content. Inputs. The text input for this error is the content that needs to be moderated. This could be a user comment, a social media post, or any other text that needs to be evaluated for its potential toxicity. Outputs. The output of this error is an error message that indicates that the text was detected as toxic. The message might include additional information about the specific type of toxicity detected or the confidence level of the detection. Steps. The moderation toxicity error is raised after a series of steps. The provided text is first analyzed for toxicity by a machine learning model. This model has been trained on a large dataset of text and its associated toxicity labels. If the model determines that the text is toxic, based on its training and analysis, it will raise the moderation toxicity error. Prerequisites. For this error to be raised, the Amazon Comprehend service needs to be properly configured. Amazon Comprehend is a natural language processing service that provides various functionalities, including sentiment analysis, entity recognition, and moderation. To effectively use the moderation capabilities, the service must be set up and configured with the appropriate access credentials. Fine-tune parameters. The threshold for toxicity detection is a key parameter in the moderation process. It determines the sensitivity of the model to identifying toxic content. A higher threshold indicates that the model needs a higher level of confidence to classify text as toxic, resulting in fewer false positives but potentially missing some harmful content. Conversely, a lower threshold makes the model more sensitive, detecting more toxic content but potentially leading to more false positives. Fine-tuning this threshold allows you to balance between sensitivity and accuracy in your moderation system. Challenges and fixes. False positive detection. When the moderation system incorrectly labels non-toxic text as toxic, it's known as a false positive. This can be a problem because it can lead to the censorship of legitimate content. To mitigate false positives, one can review the moderation parameters, such as the threshold for toxicity detection. Adjusting the threshold can improve the model's accuracy and reduce false positives. Error handling. Robust error handling is crucial in a moderation system to ensure smooth operation and graceful handling of unexpected issues. When the moderation process encounters an error, the system should have a mechanism to gracefully handle the exception. This might involve logging the error, attempting to retry the moderation, or providing a fallback mechanism. Implementing proper error handling prevents the system from crashing and ensures a seamless user experience. Langchain experimental comprehend moderation base moderation exceptions moderation P error. This exception is raised by the moderation process when it detects potentially personally identifiable information P within the input text. This signifies that the text might contain sensitive data like names, addresses, or financial details, which should not be shared publicly or without proper authorization. Inputs. The input text that is being analyzed by the moderation process. This text could be a user-generated comment, a social media post, or any other type of text that requires moderation. Outputs. An error message is generated to signal the presence of P within the input text. This message typically includes information about the detected P, such as the type of information identified and its location within the text. Steps. The input text is subjected to analysis using Amazon Comprehends P detection capabilities. Amazon Comprehend is a natural language processing service from Amazon Web Services (AWS) that can identify various types of information within text, including P. If the P detection process identifies any potentially sensitive information within the input text, the moderation P error is raised. This indicates that the text requires further review or action before it can be shared or used. Prerequisites. Amazon Comprehend must be properly configured and accessible to the moderation process. This involves setting up an Amazon Comprehend account, granting the necessary permissions, and ensuring that the service is running and available. The moderation process itself must be enabled and configured to utilize Amazon Comprehends P detection capabilities. This involves specifying the appropriate settings for the moderation process, such as the sensitivity level for P detection and the actions to be taken when P is detected. Fine-tune parameters. There are no specific fine-tune parameters available for this exception. Challenges and fixes. If P is detected within the input text, it is essential to take steps to address the issue. Review the input text carefully to identify the specific instances of P. This may involve manually inspecting the text or using tools to highlight potentially sensitive information. Once the P has been identified, consider the following options. Remove the P from the text entirely. This is the most straightforward approach, especially if the P is not crucial to the message. Mask or redact the P. This involves replacing the sensitive information with characters or symbols, such as asterisks. This approach allows you to maintain the context of the text while protecting the P. Obtain consent from the individuals whose P is included. In some cases, it may be necessary to obtain permission from the individuals whose P is included in the text before sharing or using the text. False positive P detection can occur when the moderation process mistakenly identifies non-sensitive information as P. Adjust the moderation settings to reduce the likelihood of false positives. This may involve increasing the sensitivity threshold for P detection or configuring custom P entities that match the specific types of information that should be flagged as P. Configure custom P entities to provide more precise guidance to the moderation process. This involves defining specific patterns or keywords that should be recognized as P, allowing for more accurate detection and reducing the occurrence of false positives. For instance, you could define a custom P entity to identify specific formats for phone numbers or email addresses, reducing the chance of mistakenly flagging common text strings as P. This helps the moderation process to focus on truly sensitive information, improving accuracy and efficiency. Langchain experimental comprehend moderation prompt safety comprehend prompt safety. A moderation tool that utilizes Amazon Comprehend for content analysis and filtering. It evaluates text for potentially harmful or inappropriate content based on predefined categories. Inputs: the text that needs to be checked for moderation. For example, a user comment, social media post, or website content. Outputs: the results of the moderation process, indicating whether the text is considered safe or unsafe based on the defined categories. Steps: the input text is sent to the Amazon Comprehend service via the application programming interface. API: Amazon Comprehend analyzes the text and identifies potential issues based on the preconfigured moderation categories. The results of the analysis, including any flagged issues and their severity, are returned to the user. Prerequisites: an AWS Amazon Web Services account with necessary credentials to access and utilize Amazon Comprehend. This includes an access key ID and a secret access key, which are used for authentication. The Amazon Comprehend service needs to be enabled and properly configured within the AWS account. This includes setting up the necessary permissions and ensuring that the service is active. Fine-tune parameters: the threshold for moderation, which determines the level of severity required for a content item to be flagged as unsafe. A higher threshold means only highly offensive content will be flagged. A lower threshold will result in more content being flagged. The list of categories to moderate. Defining the types of content to be flagged. This could include categories like hate speech, violence, sexual content, or spam. The user defines this list according to their specific needs. Challenges and fixes: if the provided AWS access keys are incorrect or expired, the tool cannot connect to Amazon Comprehend. To resolve this, verify the keys and update them with the correct values. If the tool lacks the necessary permissions to interact with Amazon Comprehend, it cannot analyze the content. Granting appropriate permissions to the tool will address this issue. If the Amazon Comprehend service is unavailable, the tool cannot complete its tasks. Check the service status and attempt to retry later. If there are delays in communication with Amazon Comprehend, the moderation process might become inefficient. Optimize the code to improve communication efficiency and reduce latency. If the moderation categories are not accurately defined, the tool may fail to identify specific types of inappropriate content. Update the list of categories to reflect the desired moderation criteria. If the threshold for moderation is set too high, the tool may miss potentially harmful content. Adjust the threshold to a lower value to increase sensitivity. If the threshold is set too low, the tool may flag harmless content as unsafe. Increase the threshold to reduce the number of false positives. If the tool exceeds the rate limits of the Amazon Comprehend service, its functionality may be restricted. Implement a rate limiting strategy to ensure that requests are sent within the defined limits. Langchain Voyage AI Embeddings. NAN. A tool for generating embeddings using the Voyage AI application programming interface. Embeddings are numerical representations of text that capture the semantic meaning of the text. They can be used for various natural language processing tasks, such as text similarity search, clustering, and classification. Inputs: the text to be embedded. This could be a sentence, a paragraph, or a whole document. For example, the quick brown fox jumps over the lazy dog. The name of the Voyage AI model to be used for embedding generation. Voyage AI offers various models with different levels of accuracy and performance, each designed for specific tasks. For example, text embedding ADA002. Outputs: a list of numbers representing the embedding of the input text. Each number in the list corresponds to a specific dimension in the embedding space, which is a multidimensional space where similar texts are located closer to each other. Steps. The tool first receives the input text. Then, it sends the text to the Voyage AI application programming interface along with the specified model name. Finally, it receives the embeddings from the Voyage AI application programming interface and outputs them. Prerequisites. A Voyage AI application programming interface key is required to access the Voyage AI application programming interface. You can obtain a key by signing up for a Voyage AI account. This key is used for authentication and authorization. For example, SK your API key. The name of the Voyage AI model that you want to use for embedding generation. For example, text embedding ADA 002. Fine-tune parameters. The specific Voyage AI model used for embedding generation. For example, text embedding ADA 002. The number of dimensions in the embedding space. A higher dimension generally leads to a more detailed embedding but can increase computational cost. For example, 1536. Challenges and fixes. The Voyage AI application programming interface has rate limits in place to prevent abuse. If you exceed the rate limit, you will be temporarily blocked. For example, you have exceeded your rate limit. Please try again later. Contact Voyage AI support for assistance in resolving this issue. An invalid or incorrect Voyage AI application programming interface key will result in an error. For example, invalid API key. Verify the accuracy of your API key. If you provide an invalid model name, the tool will be unable to find the model and will generate an error. For example, model not found. Ensure the model name is valid. Network connection issues or problems with the Voyage AI application programming interface endpoint can cause errors during API requests. For example, connection refused. Ensure you have a stable internet connection. Check if the Voyage AI application programming interface endpoint is available. Retry the request after some time. Upstage Vector Store for Langchain Community. A summary of its features and usage. A vector store based on Upstage Redis. A fully managed in-memory data store with persistent storage. Upstage Redis offers high performance, scalability, and reliability, making it an ideal choice for vector search applications. Inputs. Embeddings. Numerical representations of text data. Embeddings are generated by embedding models, such as OpenAI's text embedding ADA 002, which map text to high-dimensional vectors. These vectors capture the semantic meaning of the text and allow for efficient similarity searches. Text data. The textual content to be stored in the vector store. This can be anything from documents, articles, code, or even chat messages. Outputs. Vector representations of the data. The generated embeddings of the text data, stored in the vector store for efficient retrieval. Similar documents based on the query. When a query is submitted, the vector store finds the documents with the most similar embeddings to the query's embedding. This enables relevant document retrieval based on semantic similarity, rather than exact keyword matching. Steps. Create an Upstage Redis instance. Provision an Upstage Redis instance, which provides the underlying storage for the vector store. Configure Upstage Vector Store. Initialize the Upstage Vector Store object with the necessary configuration parameters, such as the Upstage Redis connection details and embedding function. Add or update text data with embeddings. Store the text data in the vector store, along with their corresponding embeddings. You can either add new data or update existing data with new embeddings. Search for similar documents. Submit a query to the vector store. The store will then use the query's embedding to find the most similar documents from the stored data based on their embeddings. Prerequisites. Upstage Redis account. A user account with Upstage Redis to access and manage the Redis instances. Create a free account. Register for a free Upstage account at https://ups-com to get started with Upstage Redis. Upstage Redis connection details the necessary credentials to connect to your Upstage Redis instance. Obtain from Upstage Redis dashboard. Access your Upstage Redis dashboard to find your Redis connection details, including the URL, token, and namespace. Fine-tune parameters. Embedding function. The embedding model used to generate vector representations of the text data. This is typically an embedding API, such as OpenAI's text embedding ADA002 or a local embedding model. Redis URL. The URL of your Upstage Redis instance. This is used to establish a connection to the Redis server. Redis token. An authentication token used to access your Upstage Redis instance. Redis namespace. A unique identifier to distinguish your vector store data from other data in the Redis instance. Challenges and fixes. Incorrect Redis connection details. Verify that the provided Redis connection details are correct. Ensure you are using the correct URL, token, and namespace. Check for typos or inconsistencies in the connection details. Verify connection details. Verify the connection details in your Upstage Redis dashboard and ensure they match the ones used in your code. Embedding errors. Check the embedding function and input data. Ensure that the embedding function is correctly configured and the input data is compatible with the function. Check embedding function and input data. Review the embedding function's documentation, input requirements, and any error messages generated during the embedding process. Search performance issues. Optimize the Redis instance for better performance. Consider scaling the instance to handle larger datasets or optimizing the search queries for efficiency. Optimize Redis instance. Use Upstage's configuration options to adjust Redis settings, such as increasing memory capacity or optimizing indexing strategies. Redis connection timeout. Increase the connection timeout limit to allow for more time to establish a connection. Increase timeout limit. Adjust the connection timeout settings in your code or configuration files to provide sufficient time for the connection to be established.